Welcome. Over the next 5 hours, we are going to cover the advanced LeetCode and DSA patterns for coding interviews. We will be covering patterns for trees, graphs, dynamic programming, backtracking, heaps, and greedy algorithms. These are the topics that come up most frequently in coding interviews and are the ones that require most preparation. So let us get started. So in coding interviews at companies like Google, Amazon, Meta, and many other tech companies, the most important LeetCode DSA problems tend to fall into three categories. The first category is trees and graphs. So problems like traversing a binary tree, finding the shortest path in a graph, detecting cycles, and working with connected components. These come up pretty constantly. The second category is dynamic programming. These are the optimization problems where you need to break the problem down into smaller subproblems and then build up the answer. Problems like longest common subsequence, coin change problem, and knapsack variation problems are examples of that. The third category is advanced techniques like backtracking, heaps, greedy algorithms, and interval problems. Things like generating, let's say, all permutations, finding the top k elements problem, or merging overlapping intervals problem are examples of that. Now the good news is that all of these problems, they follow recognizable patterns. Once you learn the pattern and understand when it applies, even a problem you may have not seen before becomes a variation of something you already know. And that is exactly what this course is built to, cover that. Now here's exactly what we'll be covering in this course today. For each pattern, we follow the same structure. First, the recognition signal, so you know when this pattern applies. Then the brute force approach and why it is too slow. Then the optimized technique with real code. Then a step-by-step trace walking through the solution with actual values. And finally, the common mistakes candidates make and what interviewers are specifically looking for. Now here are the sections. We'll start with 60 minutes on tree patterns covering DFS, BFS, path problems, tree construction, and common interview problems like lowest common ancestor and maximum path sum problem. Then 60 minutes we'll be spending on graph patterns covering graph traversals, shortest path algorithms, topological sort, union find, and problems like core schedule and number of islands problem. Then we'll spend 45 minutes on heap intervals and greedy algorithms, patterns that are covering top k problems, merge k sorted list problem, interval merging and scheduling, and also greedy selection strategies. Then for 45 minutes, we'll be spending on backtracking patterns covering permutations, combinations, subset generation, and constraint satisfaction problems like n-queens and Sudoku solver. And then the longest section, which is, we'll be spending roughly 75 minutes on dynamic programming patterns, where we'll be covering 1D dynamic programming, 2D dynamic programming, knapsack variations, string dynamic programming, and decision-making patterns. And finally, we will wrap it up, with the pattern recognition summary and as well as reference and cheat sheets that tie everything together into a decision framework that you can use then as part of your interview preparation. Now, every section also includes worked LeetCode problems, interview tips, and a reference cheat sheet for quick revision. Trees are one of the most heavily tested data structures in coding interviews, and there is a good reason for that. A tree is essentially a linked list that has branches. Instead of a single next pointer, each node has a left pointer and a right pointer. That one change going from one path forward to two changes everything about how we traverse and reason about the data structure. With a linked list, a simple while loop was enough to visit every node. However, with a tree, iteration alone is not sufficient. The branching structure means we need recursion or an explicit stack or queue to explore all the paths. And beyond traversal, we need to think carefully about what information flows downward from parent to child and what information returns upward from child to parent. Now here's the good news. Most tree problems reduce to a single decision. Should I use DFS, which is depth first search, which means going deep first, or BFS, which means breadth first search, which means going level by level. And for DFS, the follow-up question is this. What do I pass down as parameters and what do I return up as return values? Once you can answer those two questions for any tree problem, then the code just flows naturally. In this section, we'll cover tree terminology, recursive DFS with the three traversal orders, and the critical concept of returning values upward in recursion, And also then we'll cover Iterative DFS with an Explicit Stack, BFS level order traversal, BST invariance and validation, and finally we'll cover the tree path problems and lowest common ancestor. So these pattern appears, they're everywhere in interviews. Whether it's large tech companies, you'll often see problems like diameter of binary tree, validating BST, and lowest common ancestor. So they're pretty common interview problems here. At mid-sized companies as well, maximum depth, level order traversal, and path sum are very common interview questions. And also at startups, tree problems show up when interviewers want to test your recursive thinking. So this section is high value regardless of where you're interviewing and regardless which size of company or which sector, whether it's tech, telecom, or banking, and you're interviewing for. So the core idea is to keep in mind throughout this section is this. The most tree problems are DFS or BFS plus a decision about what information flows down through the parameters and what information returns upward through the return values. So before we solve any tree problems, we need to make sure the terminology is locked in. So interviewers assume you know these terms, and confusing even one of them will signal a gap in the fundamentals. So the root is the topmost node in the tree. It has no parent. A leaf is the opposite, a node at the bottom with no children, meaning both its left and right pointers are null. An edge is a connection between a parent and child. Every parent-child relationship is essentially one edge. Now, two terms that are often commonly confused are depth and height. So depth measures how far a node is from the root. The root has a depth 0, its children have depth 1, their children have depth 2, and so on. Height measures how far a node is from its deepest leaf descendant. A leaf has height 0, and the height increases as you move upward. So depth counts down from the root, and height counts up from the leaves. Getting these two mixed up in an interview is a common mistake, so you should please avoid it. A subtree is a node plus all the descendants. So this is an important concept because many tree problems ask you to compute something for every subtree, not just the whole tree. A binary tree is a tree where each node has at most 2 children. A binary search tree or BST adds an ordering constraint. Every value in the left subtree is strictly less than the node's value, and every value in the right subtree is strictly greater. A balanced tree is one where the height difference between left and right subtrees is at most 1 at every node. And a complete tree is one where every level is fully filled except possibly the last, which fills from left to right. Now let's look at the standard node definition in Python. So here's the tree node class with 3 fields: val for node's value, left for the left child, and right for the right child. Both left and right default to none. The mental model to carry through this section is this. Think of every tree problem as a set of decisions made at each node. At each node, you can look at the value, recurse into the left subtree, recurse into the right subtree, combine the results from left and right, and return something upward to the parent. The order in which you do these operations determine whether it is a pre-order, in-order, or post-order traversal. And this is exactly what we'll cover next. So there are 3 ways to visit nodes in a tree using depth first search, and the only difference between them is when you process the current node relative to its children. So in pre-order traversal, you process the current node first, then recurse into the left subtree, then the right subtree. The order is node, left, and right. In pre-order is useful when you need to process a node before its children. Common examples are copying a tree or serializing it. In in-order traversal, you recurse into the left subtree first, then you process the current node, then you recurse into the right subtree. The order is left, node, right. In-order has a special property on binary search tree. It visits the nodes in sorted order. This makes it the right choice whenever you need sorted output from a BST. In post order, you recurse into both subtrees first and process the current node last. The order is left, right, and node. Post-order traversal is the correct choice when you need results from the children before you can compute anything at the current node. Computing height and computing diameter are both post-order problems because the parent's answer depends on what the children return. Now, the code templates for all 3 are pretty identical. Each one starts with the base case. If the node is null, we return. The only difference is where the process step goes relative to the recursive calls. In pre-order traversal, process comes before both calls. In in-order traversal, process goes between the left and the right calls. In post-order traversal, process comes after both calls. So one property that is worth highlighting is this. If you perform an in-order traversal on a valid BST, the values come out in ascending order. This property is the foundation for validating whether a tree is a valid BST and also for finding the kth smallest element in a BST. We will use both of these later in the section. And here is something important for interviews. When an interviewer asks you to traverse a tree and does not specify which order, you should definitely consider pre-order. It is the most intuitive, but if a tree is BST and the problem involves ordering, you should consider in-order traversal. The traversal order you choose signals to the interviewer whether you understand the problem structure. Using post-order for a hide problem and in-order for a BST problem shows you're thinking about the information flow, not just applying a memorized template. So let us put the recursive pattern into practice with one of the simplest and most common tree problems, which is maximum depth of a binary tree, and that is the LeetCode problem number 104. So essentially the problem goes like this. Given the root of a binary tree, we have to return its maximum depth. The maximum depth is the number of nodes along the longest path from the root to a leaf. Now, essentially, as you can see on the screen, the solution is 4 lines. If the root is null, we return 0. Otherwise, recursively compute the depth of the left subtree and the depth of the right subtree. The answer to the current node is a maximum of 2 depths, plus 1 for the current node itself. Now let us trace this on a sample tree. Let's say the root is 3 with left child 9 and right child 20. Node 20 has children 15 and 7 and node 9 has no children. So now the recursion will start at node 3. It calls max depth on node 9. Node 9 has no children, so both recursive calls return 0 and max depth of 9 returns max 0 of 0 plus 1, which is 1. Now we're back at node 3. We call max depth on node 20. Node 20 calls max depth on 15th, which returns 1, and max depth on 7, which also returns 1. So max depth of 20 returns max of 1 and 1 plus 1, which is 2. Finally, we are back at node 3. Then we return max of 1 and 2 plus 1, which is 3. Now notice, why is this a post-order traversal? At each node, we need the depths of both children before we can compute the depth of the current node. The children are processed first and the current node is processed last. So that is post-order. Now the base case is a standard tree recursion base case. When the node is null, we return 0. A null node contributes nothing to the depth. This base case appears in almost every tree recursion problem, and it is the first thing you should write when starting any tree recursive function. Maximum depth is often the first tree question in an interview, so it establishes the pattern that applies to nearly every DFS tree problem, which is to recurse left, recurse right, combine the results, and then you return upward. Everything that follows in this section now builds on this exact pattern. So this is a very important concept in tree problems. If you internalize what is covered on this slide, every tree problem from this point forward becomes a variation of the same idea. Now in tree recursion, information flows in 2 directions. Parameters carry information downward from parent to child. Return values carry information upward from child to parent. Choosing what to return upward is a key design decision in most tree problems. Now let us look at how different problems use this. In maximum depth problem we just solved, each recursive call returns the height of its subtree and the parent combines them with max left and right plus 1. In the diameter problem, which we'll cover next, each call also returns the height, but the parent uses it differently. The diameter at a node is left height plus right height. In checking if a tree is balanced, now each call returns the height or -1 as a signal that the subtree is unbalanced. In the path sum problem, each call returns true or false, indicating whether a valid path exists. In lowest common ancestor problem, each call returns the LCA node if found in that subtree or none otherwise. So now the pattern across all of these is the same. For each problem, we ask 2 questions. First, What does each recursive call need to return? Second, how does the current node combine the results from its left and right children? If you can answer these two questions, then the code will write naturally. Now, there is one common mistake to watch out for: using a global variable to track state instead of returning values upward. Global variables work, but they make the code harder to reason about and easier to break. Returning values upward is much more cleaner, more functional, and what interviewers actually expect. There are exceptions where a global tracker is necessary, and we'll see one in the very next slide, but the default should always be to return values upward. So this slide actually describes a very important skill in tree problems. Every tree problem from this point forward in this course uses a return upward pattern. So make sure this is clear as we before move on. Now let's look at a problem that adds a twist to the return upward pattern, which is the diameter of a binary tree problem, LeetCode number 543. The diameter of a binary tree is the length of the longest path between two nodes, measured in number of edges. The path does not need to pass through the root. Now here's the key insight. At every node, the longest path that passes through that node equals the height of its left subtree plus the height of its right subtree. So that gives us the path that goes all the way down the left side through the current node and all the way down through the right side. The diameter of the entire tree is the maximum of this value across all nodes. But here's the twist. Each recursive call returns the height of its subtree because this is what the parents need. But the answer to the problem, the diameter, is not the height. The answer is left height plus right height, and we need to track the maximum of that across all nodes. So we need a separate variable to track the global maximum. So in the code, we create a list containing 0 called max diameter. We define a nested function called height that computes the height of each subtree. At each node, it gets the left height and the right height from its children. It updates the max diameter with left height plus right height if that is larger than the current maximum. And then it returns the max of left height, right height plus 1, which is the height for the parent to use. The reason max diameter is a list and not a plain integer is a Python specific detail. In Python, a nested function cannot reassign a variable from the enclosing scope without the non-local keyword. Using a list with a single k element is a common workaround. Alternatively, in Python 3, you can declare non-local max diameter and use a plain integer. And again, if you use any other languages other than Python like Java and C++, so you can use the local that programming language specific implementation. Now the time complexity for this is O of n since every node is visited once. The space complexity is O of h for the recursion stack, where h is the height of the tree. Now this is a very commonly asked tree problem. And this is the very first problem that candidates encounter where the return value is different from the answer. The function returns height, but the answer is diameter. Understanding this distinction is critical for the next slide, where we will trace through exactly how these two values flow through the tree. So now let us trace the diameter computation step by step on a concrete tree. Let's say we have a tree as shown on the screen, which is 1, 2, 3, 4, 5. So the root is 1 with left child 2 and right child 3. And then node 2 has children 4 and 5. We start at node 1 and recurse left to node 2. Node 2 recurses left to node 4. Node 4 has no children, so both recursive calls return 0. The diameter at node 4 is 0 plus 0, which is 0. The max diameter stays at 0, and then node 4 returns max of 0 and 0 plus 1, which is 1, as it's the height. Now we are back in node 2. We recurse right to node 5, same situation. Node 5 has no children, diameter is 0, and returns height 1. Now node 2 has left height 1 and right height 1. The diameter through node 2 is 1 plus 1, which is 2, so that represents the path from node 4 through node 2 to node 5. Max diameter updates to 2. Node 2 now returns max of 1 and 1 plus 1, which is 2 as its height. Now back at node 1, we recurse right to node 3. Node 3 has no children, returns height 1 and diameter 0. Now node 1 has left height 2 and the right height 1. The diameter through node 1 is 2 plus 1, which is 3. So that represents the path from the node 4 through node 2 through node 1 to node 3. Max diameter updates to 3, so the final answer is 3. So now let's look at the table of values at each node. Node 4 returns height 1 upward but has diameter 0. Node 2 returns height 2 upward but has diameter 2. Node 1 returns height 3 upward but has diameter 3. At every node, two separate computations are happening in the same recursive call. The height goes upward for the parent to use. The diameter is computed locally and compared against the global maximum. These are two different values serving two different purposes. This is something you should note it down. In many tree problems, the value returned upward is not the final answer. The return value serves a parent. The answer is tracked separately, often in a global variable or a closure. Recognizing when the return value differs from the answer is the single most important insight for tree recursion. This pattern will appear again in problems like binary tree maximum path sum, which is one of the very hard problems in tree data structures that you'll encounter in tree interviews. Now here's also something where interviewers specifically test for. Can you explain why the function returns height but the answer is diameter? Being able to articulate this dual purpose recursion separates strong candidates from someone who might not be able to do that well in the interviews. So you should please prepare for this scenario as well. So now let us test what we have covered so far. For each problem, we try to identify what the recursive call should return before reading the answer. So here's the practice problem 1. Let's say given a binary tree, we have to determine if it is tree height balanced. A height balanced tree is one where every node's left and right subtree height differs by at most 1. So now, what should each recursive call return? The answer is the height of the subtree or -1 as a sentinel value indicating the subtree is unbalanced. At each node, we compute the left and the right heights. If either is -1 or if the difference between them exceeds 1, we return -1. Otherwise, we return max of left and right plus 1. At the end, we should check if the root result is not -1. There is the same height computation from maximum depth with an added check for balance. Now let's look at practice problem number 2, which is given a binary tree, we invert it so it becomes a mirror image. Now every left child becomes a right child and vice versa. So now what should each recursive call return? The root of the inverted subtree. So for example, at each node, recursively invert the left and right subtrees, then swap them. We set the node.left to the right result and node.right to the left result, and then we return the node. This is a pre-order operation, so you swap first and the recursive calls handles the subtrees below. Now here's the practice problem number 3. Given two binary trees, check if they are the same tree, meaning identical structure and identical values. So now, what should each recursive call return, true or false? The base cases are, if both nodes are null, we return true. If one is null and the other is not, we return false. For the recursive case, the values must match and both the left subtrees and the right subtrees must be identical. Return the p.val equals q.val and same, p.left, q.left. So, and same, and inside that we put p.right and q.right. All three of these problems follow this return upward pattern from slide 5. The skill is identifying what to return before you start writing the code. So this is something you should make a habit. For every tree problem, answer the question, what does each recursive call should return? Before you actually proceed in the problem. So far for every DFS solution has been recursive. Recursive DFS uses a call stack implicitly and it works well for most interview problems. But there's a limitation. For very deep trees where the depth exceeds the language's recursion limit, recursive DFS can cause a stack overflow. So Python's default recursion limit is around 1000. So a skewed tree with let's say 100,000 nodes would crash on that. Now Iterative DFS solves this by using an explicit stack data structure which can grow as large as the available memory allows. Now the iterative pre-order template works like this. If the root is null, we return an empty list. Otherwise, we create a stack and push the root onto it. While the stack is not empty, we pop a node, process its value, and then push its children. Now here's the important detail. Push the right child first and then the left child. Why? Because the stack is last in, first out. If you push right first, then left is on the top of the stack and gets popped and processed next. This gives you the correct pre-order sequence, which is node, then left subtree, then right subtree. Now, iterative in order is much more complex. You need to go as far left as possible before processing any node. So you use a different pattern. You maintain a current pointer and a stack. While current is not null or the stack is not empty, we keep pushing current onto the stack and moving left. When you cannot go left anymore, we pop from the stack, process that node, and move to its right child. The inner while loop handles the go as far as left as possible step. So now, when should you use iterative versus recursive? For interviews, the default is recursive. It is simpler to write, easier to explain, and interviewers accept it in almost all cases. Use iterative DFS when the tree might be very deep, let's say for example 100,000 nodes, when the interviewer explicitly asks you for an iterative solution, or when you need fine-grained control over the traversal order. Being able to write iterative DFS when asked actually shows a deeper understanding of how recursion works under the hood. So now that we have covered depth first search thoroughly, let us talk about the other major traversal strategy, which is breadth first search or BFS. The recognition signal for BFS is straightforward. If the problem mentions levels, layers, depths, or requires processing all nodes at the same depth before moving deeper, BFS is the right tool. Words like, let's say, level by level, shortest path in an unweighted tree, or layer all points to BFS. So BFS on a tree works using a queue. Start by adding the root to the queue, then while the queue is not empty, remove a node from the front, process it, and add the children to the back. Because the queue is first in, first out, all nodes at depth D are processed before any node at depth D plus 1. This gives you level by level processing automatically. The decision between BFS and DFS usually comes down to the structure of the problem. Use BFS when you need to process nodes level by level, when you need the shortest path in an unweighted tree, when you need to find something at the minimum depth, or when you need level-specific operations like zigzag ordering. Use DFS when you need to explore, full paths, for example, from root to leaf, when you need to return information upward, when you need to check properties of the subtrees, or when you are computing height, diameter, or path sums. And here's an important, interview tip. So if the problem mentions level, depth, layer, or shortest like keywords, you should default to BFS. If it mentions keywords and phrases like path, height, subtree, or validate, you should consider defaulting to DFS. Now, one more thing to note is that BFS on trees is simpler than BFS on graphs. Trees have no cycles, so there is no need for a vested set. When you encounter a graph, BFS later on, the only addition is tracking which nodes have already been visited. So mastering tree BFS here makes graph BFS straightforward to learn later. Now here's the BFS template that you will use for nearly every level order tree problem. The function takes the root as input. If the root is null, we return an empty list. So create a queue, for example, here in this example, using Python's dequeue and add the root. The main loop returns while the queue is not empty. At the start of each iteration, we capture the current length of the queue into a variable called level size. Then we run an inner for loop that iterates exactly level size times. In each iteration, we pop a node from the front of the queue with pop left, process it, and add its non-null children to the back of the queue. After the inner loop completes, one full level has been processed. Now the key trick in this template is that level size line. At the start of each level, length of queue actually tells you exactly how many nodes are at the current level. You process exactly that many nodes, and as you do, you add their children to the queue. But those children will not be processed in this iteration of the outer loop. They will be processed in the next iteration, which represents the next level. This is how the two loop structure separates nodes by level. So why do we use DQ instead of a regular list? The list.pop0 operation is O of n because after removing the first element, every remaining element has to shift left by one position. The dq.popleft operation is O of 1 because dq is implemented as a doubly linked list. For a tree with n nodes, using a list turns BFS from O of n to O of n square. So always use dq for BFS queues. And this is something you should note down as well. The BFS template has two loops. The outer while loop runs once per level. The inner for loop runs once per node at that level. If you need per level results like a list of lists, collect the nodes inside the inner loop and append the collected list after the inner loop completes. This two loop structure is the foundation for every BFS variant. And here's something important for interviews as well. Without the level size trick, you cannot separate nodes by level. That makes level specific operations like zigzag ordering, level averages, and right side view impossible to implement cleanly. This one detail unlocks an entire family of problems. So let us apply the BFS template to binary tree level order traversal problem, which is LeetCode number 102. So the problem asks you this. Given the root of a binary tree, return the level order traversal as a list of lists. Now let's take this tree for example. So here the root is 3 with left child 9 and right child 20. Node 20 has children 5, 15 and 17. And the expected output is 3 and then 9, 20 and then 15 and 7. Now let us trace through the template here. So we start with the queue containing just node 3. So for level 1, level size is 1. We pop node 3, add it to the current level, and push its children 9 and 20 into the queue. After the inner loop, current level is 3. And then we append it to the result. The queue now contains 9 and 20. Now let's look at level 2. Now level size is 2. We pop node 9, which has no children. Then we pop node 20 and push its children 15 and 7. After the inner loop, current level is 920 and we append it, so the queue now contains 15 and 7. Now let's look at level 3. So now level size is 2. We pop node 15 and node 2, neither of which has children. After the inner loop, current level is 15, 7. The queue is now empty, so the outer loop ends. Now the result is 3, 920, 15, 7, which is exactly the expected output. Now here is what makes this template so powerful. So for example, as you can see in the slide here, so these are the at least 5 common variants of this problem, and every single one uses the same template. For zigzag level order problem, you reverse every other level's list. For binary tree right side view problem, you take only the last node of each level. For average of levels problem, you compute the mean instead of collecting values. For largest value in each row problem, you take the max. The only thing that changes between these variants is what you do with the current level after the inner loop completes. The BFS structure is identical. So the level order traversal problem that we just covered is a pretty common LeetCode interview problem, and once you know this template, all the 5 variants become pretty easy modifications to do. So this is exactly the kind of pattern-based thinking that turns interview preparation from having to memorize like hundreds of solutions into actually learning a handful of templates and patterns that can apply much more broadly. Binary tree with an ordering constraint and unlocks very powerful operations. So what makes a BST special is one rule applied recursively. For every node in a BST, all values in its left subtree are strictly less than the node's value, and all values in its right subtree are strictly greater than and greater than. And both the left and right subtrees are themselves valid BSTs as well. So this is a BST invariant. Now several useful properties follow from this invariant. So first is an in-order traversal of BST visits nodes in an sorted ascending order. This is because in-order visits the left subtree first, which contains smaller values, then the current node, then the right subtree, which actually contains the larger values. This property is the basis of validating a BST and for finding the kth smallest element. Now, second is Search in BST takes O of h time, where h is the height. At each node, you compare the target with the node's value. If the target is smaller, go left. If it is larger, go right. Each comparison eliminates an entire subtree, just like binary search eliminates half an array. For a balanced BST, h is O of log n, so search is O of log n. For a skewed BST, h is O of n, so search degrades to O of n. Now, third is the minimum value in a BST is always the leftmost node. So you keep going left until you reach null. Similarly, the maximum is the rightmost node. So both operations are also O of h. Fourth, the in-order successor of a node, meaning the next larger value, is the leftmost node in its right subtree. This is because the right subtree contains all the values greater than the current node, and the smallest of those is the leftmost one. Now, the BST search node is essentially binary search on a tree structure. If the node is null, the target is not in the tree. If the target matches the node's value, you return the node. If the target is less than the node's value, you search the left subtree. Otherwise, you search the right subtree. In interviews, BST properties are assumed knowledge. If the problem states, let's say, binary search tree, every one of these properties is available to exploit. Missing the sorted in order property in a BST problem is one of the very common interview mistakes. So here is the validate binary search tree problem, which is LeetCode problem number 98, and it's a very frequently asked tree problem. So the problem essentially asks that, okay, given the root of a binary tree, we have to determine if it's a valid BST. And this problem has a trap that catches a lot of candidates, so you please pay attention to this. So the trap essentially is the naive approach, which is that checking that each node's left child is smaller and right child is larger. This seems correct, but it's actually not. Consider a tree where the root is 5, left child 1 and right child 6. Node left has left child 3 and right child 7. The naive check will be passes at every node, so 1 is less than 5, 6 is greater than 5, 3 is less than 6, 7 is greater than 6. But this tree is not a valid BST. Node 3 is in the right subtree of node 5, which means it must be greater than 5, but 3 is less than 5. Naive approach will only check the immediate parent, not all ancestors. Now the correct approach uses range-based validation. So every node has a valid ranges of value it can hold. The root can be anything, so its range is negative infinity to positive infinity. And then when we go left, the upper bound tightens to the parent's value. When we go right, the lower bound tightens to the parent's value as well. These constraints propagate downward, narrowing the valid range at each level. Now the code here defines a helper function called validate that takes a node, a low bound and a high bound. If the node is null, we return true. If the node value is less than or equal to low or greater than or equal to high, we return false. Otherwise, recursively we validate the left subtree with the upper bound updated to the node's value and validate the right subtree with the lower bound updated to the node's value as well. The initial call passes negative infinity and positive infinity as its bound. The time complexity for this is O of n because every node is visited once. The space complexity is O of h for the recursion stack. So again, this is a very commonly asked tree problem, and interviews use it specifically because the naive approach is essentially wrong and a lot of candidates do it. This question tests whether you understand BST constraints applied to entire subtrees and not just immediate children. So let us trace the range-based validation on the same tree that broke the naive approach. The root is 5, left child is 1, right child is 6, and node 6 has left child 3 and right child 7. So we start with validate 5, negative infinity, positive infinity. Node 5 is within the range, so we continue. We recurse left with validate 1, negative infinity, 5. Node 1 is within that range and both its children are null, so it returns true. Now we recurse right with validate 6, 5, positive infinity. So node 6 is within the range, which is 6 is greater than 5, so we continue. We recurse left with validate 3, 5 and 6. Here is where the naive approach failed and the range-based approach catches the error. Node 3 must be in the range 5 and 6, meaning strictly greater than 5 and strictly less than 6. But 3 is not greater than 5, so the function returns false. This propagates upward and the final result is false. Now, let's look at how the range narrows as we go deeper. So for example, the root has range negative infinity to positive infinity. Node 1 being the left of 5 has range negative infinity to 5. Node 6 being right of 5 has range 5 to positive infinity. Node 3 being left of 6 but in the right subtree of 5 inherits the lower bound 5 from the root and the upper bound 6 from its parent. The range correctly captures the constraint that everything in the right subtree of 5 must be greater than 5. Now there is also an alternative approach using in-order traversal. Since in-order traversal of a valid BST produces sorted values, you can do an in-order traversal and check that each value is strictly greater than the previous one. This works by maintaining a reference to the previous value visited, so if any value is less than or equal to the previous, the tree is not a valid BST. So both approaches are O of n in time complexity here and O of h in space complexity. The range-based approach is more commonly expected in interviews, but being able to discuss both approaches and pivot from one to another approach when asked actually shows flexibility and depth during the interviews, so you should please be ready for that. So let us test what we have covered on BFS and BST with 3 practice problems. For each one, we identified the approach before essentially reading the answer, so please do that. So practice problem 1 is, given a binary tree, return the values of nodes visible from the right side, meaning the rightmost node at each level. So what approach applies here? BFS with the level order template from slide 10. At each level now, the last node in current level is the right side visible node. You run the same BFS template and simply take the last element from each level's list. There is also a DFS alternative where you traverse right child first and track the first node seen at each step, but BFS is much more intuitive for this problem. Now let's look at practice problem number 2, which is, given a BST and 2 values P and Q, we have to find the lowest common ancestor. Both values are guaranteed to exist in the tree. So now what approach applies here? This is different from a general binary tree LCA problem. In a BST, the ordering property tells you exactly which subtree to search. If both P and Q are less than the current node, the LCA must be in the left subtree. If both are greater, the LCA must be in the right subtree. If they split, meaning one is less and one is greater, the current node is the LCA. This runs in O of h time, which is faster than the general LCA approach that requires O of n. Now let's look at practice problem number 3, which is, given a BST, we have to find the kth smallest element. So what approach applies here? So that is in-order traversal. Since in-order on a BST gives you sorted order, the kth element in the in-order sequence is the kth smallest element. You can use either recursive or iterative in-order and count nodes as you process them. When the count reaches k, so that is your answer. So these 3 practice problems essentially demonstrate 3 different uses of the BST properties. The first uses level structure, which is BFS. The second exploits the ordering to direct the search, making it more efficient than a general tree solution. And the third practice problem here leverages the sorted in-order property. Recognizing which property to exploit for which problem is a key skill for BST problems. Now let us talk about a family of problems that appear frequently in medium and hard level LeetCode tree problems, which is the path problems. The recognition signal is pretty straightforward actually. If the problem mentions a path from one node to another, or asks about sums or properties along a root to leaf path, or requires finding a specific path through the tree, it is a path problem. So path problems comes in several flavors. Root to leaf paths, they start at the root and they end at a leaf. Examples include path sum problem and root to leaf numbers problem. Any paths, they go between any 2 nodes, so passing through the lowest common ancestor. The diameter and binary tree maximum path sum problems, they fall into this category. Then there are paths with a target sum, so where you need to find a path whose node values add up to a specific target. And finally, longest to shortest path problems, where you need the path with the maximum or minimum length. So now the critical question for any path problem is this: which direction does information need to flow? From root to leaf paths, information flows downward. You pass the running sum or the path so far or the remaining target as a parameter. At each leaf, you check whether the condition is met, so the mechanism is function parameters. For any to any paths, information flows upward. Each recursive call returns something like a height or a partial sum, and the parent combines the left and right results to compute the path metric at that node. The mechanism is the return values. Now, for problems that need both, like some advanced path sum variants, information flows in both directions. You pass constraints downward through parameters and return results upward through return values. So this decision whether information flows down, up, or both determines the entire structure of this recursive solution. Getting this right is the first and most important step. Once you know the direction, the code follows the template, so we have already covered, so then it gets much more easier to implement. Let's work through path sum problem, which is LeetCode number 112. The problem asks, okay, let's given a binary tree and a target sum, determine if the tree has a root to leaf path where all the node values add up to the target. So for example, as shown on the screen here, let's take a tree where the root is 5, with left child 4 and right child 8. Node 4 has left child 11, node 11 has children 7 and 2, node 8 has children 13 and 4, and node 4 on the right has right child 1. The target sum is 22. So now the path 5, 4, 11, 2 actually adds up to 22, so answer is actually true. So the approach is to pass the remaining sum downward. So at each node, like subtract the node's value from the target. When you reach a leaf, check if the remaining sum is 0. If it is, then a valid path exists. So the code is clean. If the root is null, if we return false, subtract the current node's value from target sum. Check if the current node is a leaf. If it has no left child and no right child, we return whether target sum is 0. Otherwise, we recurse into the left subtree and right subtree with a reduced target sum and return true if either subtree finds a valid path. Now let us trace the path to node 2. We call the has path sum, with the function with 5 and 22 as values. So the remaining becomes 17. We go left to node 4, remaining becomes 13. We go left to node 11, so remaining becomes 2. We go left to node 7, remaining becomes -5. Node 7 is a leaf and -5 is not 0, so it returns false. Then we go right to node 2, remaining becomes 0. Node 2 is a leaf and 0 equals 0, so it returns true. This true propagates upward through all the parent calls. Now there is a common mistake on this problem that is worth addressing. Many candidates actually write the base case as, okay, if the node is null, then return whether target sum equals 0. But unfortunately that is incorrect. A null node is not a leaf. A leaf is a node that exists but has no children. The null check would trigger on the null children of leaf nodes, which could give a false positive if one child is null and the other is not. The check must be on the node itself, which is it a leaf and its remaining sum is 0? Getting the edge case right is the main thing Intuit is evaluate for this problem. Now let's cover the next problem, which is lowest common ancestor problem, which is LeetCode number 236. It's a very commonly asked tree problem. So this is the problem asks. Let's say given a binary tree and two nodes P and Q, we have to find their lowest common ancestor. The LCA is the deepest node that has both P and Q as descendants, and a node is allowed to be a descendant of itself. So the key insight is this: search both subtrees. If P is found in the left subtree and Q is found in the right subtree or vice versa, then the current node is LCA. If both are found in the same subtree, the LCA is deeper in that subtree. Now the code is pretty concise actually, which is only roughly 8 lines, but every line here matters. First is the base case. So if the root is null or the root equals P or the root equals Q, we will return the root. Then we recurse into both subtrees, set left to the result of the recursive call on the root.left and right to the result on the root.right. If both left and right are non-null, the current node is LCA, so we return root. If only one is not null, we return that one, passing the result upward for the parent to use. Now let us think about why this works by considering the scenarios. If P is in the left subtree and Q is in the right subtree, the left call returns something non-null, let's say it found P, and the right call returns something non-null, it found Q. Both are non-null, so the current node is the LCA. If both P and Q are in the left subtree, and the left call returns the LCA of P and Q within that subtree, and the right call returns null, we pass the left result upward. If the current node itself is P or Q, we return it immediately. The other target is either below us or in a different branch, and the parent will combine the results correctly. Now the time complexity is O of n because the worst case we have to visit every node. The space complexity is O of h for the recursion stack. Now the problem tests the return upward and combined pattern, which is pretty important. So the solution is short but requires a solid understanding of how recursive results propagate upward and combine at each node. So let us trace through two examples to make sure the LCA logic is fully clear. First, find the LCA of nodes 5 and 1 in a tree where the root is 3 with left child 5 and right child 1. Node 5 has children 6 and 2, node 2 has children 7 and 4, node 1 has children 0 and 8. So we call LCA 351, at node 3 we recurse left, LCA 551, the root equals P, so we return 5 immediately. Back at node 3, left is 5, so we recurse right. Now LCA 151, which is the root equals Q, so we return 1 immediately. Back at root node 3, right is 1. Both left and right are non-null, so the node 3 is LCA. The answer is 3. Now for the second example, let's say we have to find the LCA of nodes 5 and 4 in the same tree. We call LCA 354, at node 3 we recurse left. LCA 554, the root equals P, so we return 5 immediately. Back at node 3, left is 5, we recurse right. LCA, then we do on 154, so we have to recurse into node 0, which finds nothing and returns null. We recurse into node 8, which also finds nothing and returns null. Now both are null, so LCA 154 returns null. Back at node 3, left is 5 and right is null, so we return the non-null result, which is 5. The LCA of 5 and 4 is 5 itself because node 5 is an ancestor of node 4. Now the second example highlights an important edge case. When one target node is an ancestor of the other, the ancestor itself is LCA. The early return on root equals P or root equals Q handles this case automatically. Without that early return, the recursion would continue into node 5 subtree, find node 4, return it upward, and the logic would still work, but less efficiently now. The early return is both a correctness feature and an optimization. Now a common mistake is that it's not handling some like a condition like this. Let's say one node is an ancestor of other. So for example, what happens in this is that let's say the early return handles it, and walking through this trace is a common whiteboard exercise in the interviews. Interviewers are generally asking you to step through the recursion to verify you understand how the base case is and recursive combination produces a correct answer. So at this point we have covered both DFS and BFS in depth. So the natural question is now this: for any given tree problem, how do you decide which one to use? Now here's a decision framework. You should use DFS when the problem mentions things like height or depth of a tree, because computing height requires going all the way to the leaves. Now you should use DFS for root to leaves path because DFS naturally follows paths from root to leaf. You should also use DFS when you need to validate a property of subtrees because you need the subtree results before you can validate the parent. And again, you should use DFS for diameter or longest path problems because you need heights from both subtrees. You should also use DFS for serialization because pre-order DFS gives a natural serialization order. And you should also use DFS for comparing two trees structurally because the comparison is naturally recursive. Now let's talk about when to use BFS. So you should be using BFS when the problem says things like okay, level by level, because essentially BFS processes one level at a time. You should also use BFS for the shortest path in an unweighted tree because BFS finds the shortest path by exploring nodes in order of distance. You should also use BFS for right side view or left side view because you need the last or first node at each level. You should also use BFS for zigzag or spiral order because those require level aware processing. And you should also use BFS when you need to connect nodes at the same level, because that requires level grouping. Now, when neither BFS nor DFS is clearly better, you should also default to DFS. There are three reasons. DFS is simpler to write, usually fewer lines of code, and no need to import a queue. DFS uses O of H space complexity for the recursion stack, while BFS uses O of W space for the queue, where W is the maximum width of the tree. And DFS also handles the majority of tree problems essentially effectively. Now, choosing the wrong traversal does not mean you cannot solve the problem, but it makes the solution much more harder to write and signals to the interviewer that you maybe did not recognize the problem structure correctly. So spending approximately roughly 10 seconds on this decision before you start coding will save you many much more longer time implementation, and will actually be better for their interviews. Go through the most common mistakes candidates make on tree problems, because these are the primary reasons people they don't do well on tree problems during interviews despite knowing the patterns. Now, the first mistake is confusing local and global state. If you use a local variable where you need a closure or a return value, each subtree gets its own copy, and the results do not combine correctly. The fix is to return values upward for per subtree results and use a closure or a mutable container like a list for values that need to be shared across the entire recursion. The second mistake is not defining the base case clearly. Every tree recursive function should start with, if not root, return some default value. Missing this causes the recursion to crash when it reaches the null node. The default value depends on the problem: 0 for depth, true for validation, and none for search. The third mistake is checking only immediate children when validating a BST. As we saw in the validate BST problem, the constraint applies to the entire subtree, not just the direct children. The fix is the range-based approach. Pass valid low and high bounds downward and check every node against those bounds. The fourth mistake is using list.pop0 for BFS instead of dq.popleft. As we discussed, list.pop0 is O of n per operation, which turns an O of n BFS into a O of n squared. Always use collections.dq with popleft for O of 1 removals from the front. The fifth mistake is not handling the case in LCA, where one target node is an ancestor of the other. The root equals p or root equals p, q actually early return handle this automatically, so without it the solution may miss the edge case. And now here's an important interview tip. Before writing an tree recursion problem, answer these two questions out loud. What does each recursive call return, and what is the base case when the node is null? If you can answer both, the code follows directly. If you cannot answer both, stop and think before you start coding. These two questions are the foundation of every tree solution. Now, tree problems have a very high pass rate among well-prepared candidates because the patterns are consistent. The mistakes above are the primary reasons people they don't do well on tree problems despite knowing the patterns. So you should please work on avoiding these mistakes. Now here's your reference cheat sheet for this entire section. The slide is designed to be screenshotted essentially and used for quick revision before the interviews. So the post order DFS template is this: if the node is null, return a base value. Recurse left and right, combine the results with the node's value, and return the combination. This handles maximum depth, diameter, is balance problem, and any other problem where the parent needs children's results. The BFS level order template uses a DQ. While the queue is not empty, you capture the level size, loop through exactly that many nodes, pop each from the front, process it, and add its children. This handles level order problem, zigzag problem, right side view problem, level averages problem, and every level based problem as well. Now the BST validation template passes a low and high bound downward. If the node is null, we return true. If the node's value is outside the valid range, we return false. Recurse left with the upper bound tightened to the node's value, and recurse right with the lower bound tightened to the node's value. The lowest common ancestor template has three base cases: null returns null, root equals p returns root, and root equals q returns root. Recurse both subtrees. If both return not null, the current node is LCA. Otherwise, return whichever is not null. The path sum template subtracts the node's value from the remaining target. At a leaf, we check if the remaining is 0, otherwise recurse left or right, and return true if either finds a valid path. For complexities, DFS in any order is O of n time and O of h space complexity for the recursion stack. BFS is O of n time and O of w space for the queue because where w is the maximum width. BST search is O of h time complexity and O of h space complexity. BST validation is an LCA and both are O of n time complexity and O of h space complexity. Now, one important distinction for interviews is this. H is O of log n for balanced trees and O of n for skewed trees. Stating this when discussing space complexity shows the interviewer that you understand the difference between best case and worst case tree structure. Now let us step back and look at everything we have covered in this section. We start with tree terminology and the mental model of decisions at each node. We covered recursive DFS with its 3 traversal orders and learned that the traversal order you choose reflects the information flow of the problem. We learned the return upward pattern, which is the single most important concept in tree problems. We covered iterative DFS for when recursion is not an option. Then we learned BFS with the level size trick for level by level processing. And then we also covered BST invariance and the range-based validation approach. We worked through the path problems and the question of whether information flows down, up, or both. And then we covered the lowest common ancestor, which combines the return upward pattern with elegant base cases. Now, recursion signals are consistent. If you need to explore full paths or compute subtree properties, you should use, recursive DFS. If each node is, needs information from its children, you return value upward. If the tree is very deep or you need explicit control, you use iterative DFS with the stack. If the problem mentions levels, layers or shortest path, you use BFS with the level size trick. If the tree is BST, exploit the sorted in order property and O of h search. If you need to validate the BST invariant, you use the range-based approach. If the problem involves a root to leaf path with a target, subtract the node value and check at the leaves. If you need the deepest common ancestor, you search both trees and combine. Now, these patterns can connect directly to what comes next. So DFS recursion reappears in graph problems with the addition of a visited set. BFS with a queue is the same template in the graph BFS, again plus a visited set. BST binary search is the same binary search principle applied to a tree structure. The return upward pattern reappears in backtracking, and the pass down return up structure appears in some dynamic problems on the trees. Now, the tree problems they cover roughly around roughly 15% of interview problems that you'll see in a typical on-site day loop, making them a very common interview category after arrays, obviously. So combined with arrays, two-pointer, and hashmap patterns, now you have the tools to handle roughly approximately 60% of LeetCode problems. So now in the next section, we cover graph patterns where we will be covering, so trees are the special cases of graphs, right? They're connected, acyclic, and have a single root. Graphs remove all 3 of those constraints. Now they can be disconnected, they can have cycles, and they have no designated root. This means we'll need a visited set to avoid infinite loops and will need to handle multiple connected components. But the core traversal strategies, DFS and BFS, carry over directly from what we have just learned. So in the previous section, we covered trees. So trees give us a clean, predictable structure, one root, no cycles, and every node reachable by exactly one path from the top. However, graphs, they remove all of those guarantees. A graph can be disconnected, meaning there are nodes that cannot reach each other at all. A graph can have cycles, meaning a traversal that starts at a node A, and let's say node A, and can travel through other nodes and arrive back at node A. And also a graph has no designated route, so there's no single starting point for traversal. So these differences have real consequences for the code we write. Without trees, we could traverse freely without worrying about visiting the same node twice. With graphs, if we do not track where we have been, we can just keep looping forever. With trees, a single traversal from the root visits everything. With graphs, we may need to start multiple traversals to reach disconnected parts. The good news is that the graph problems, despite their reputation, follow a small and repeating set of patterns. In this section, we'll cover 9 of them. So that will be graph representations, BFS and DFS adapted for graphs, the visited set, treating grids as graphs, connected components, multi-source BFS, cycle detection, topological sort, and union find. These patterns cover the vast majority of graph questions that appear in the coding interviews. Now problems like number of islands, course schedule, and accounts merge problems are very frequently asked problems across all companies of all sizes, and all of them map directly to one of these 9 patterns. If you understand the pattern, the specific problem becomes an application rather than an invention. So now let us start with the most fundamental decision, which is how to represent a graph in code. So before we can traverse a graph or run any algorithm on it, we need to decide how to store it in memory. There are 2 standard approaches, and the choice between them affects both performance and code simplicity. The first is the adjacency list. So in an adjacency list, each node maps to a list of its neighbors. If node 0 connects to nodes 1 and 2, then the entry for node 0 contains the list 1, 2. The space this uses is proportional to the number of vertices plus the number of edges, which is O of V plus E. This is efficient for sparse graphs where the number of edges is much smaller than the maximum possible. The second is adjacency matrix. So there is a 2D grid where row I, column J contains a 1 if there is an edge from node I to node J and a 0 otherwise. The space this uses is O of V squared regardless of how many edges exist. The advantage is that checking whether a specific edge exists takes O of 1 time, just a direct lookup at position I and J. In an adjacency list, that same lookup requires scanning through the neighbors list, which takes O of degree time. Now, so when should each of these 2 approaches should be used? For getting all the neighbors of a node, the adjacency list wins. It returns only the actual neighbors in O of degree time. The matrix has to scan an entire row of V entries. For checking if a specific edge exists, the matrix wins with this O of 1 lookup. Adding an edge is O of 1 in both representations. Now, in practice, almost every graph interview problem uses an adjacency list. Interview graphs tends to be more sparse, and the operations you perform most often are things like get all neighbors and things like, let's say, traverse the graph, so both of which actually favor the adjacency lists. So one important skill is building an adjacency list from the input format the problem gives you. Problems often provide edges as a list of pairs like 0, 1, 1, 3, 0, 2. So the build graph function on this slide takes those pairs and constructs the adjacency list. For an undirected graph, each edge is added in both directions. If 0 connects to 1, then 1 also connects to 0. For a directed graph, the edge is added in one direction only. This conversion step is always the first thing to write in the graph problem. Get the representation right and the traversal code follows naturally. But if you get it wrong, then every subsequent step will produce incorrect results. Now that we have a way to store the graph, let us talk about the 2 fundamental ways to traverse it. So BFS and DFS both visit every reachable node exactly once. The difference is in the order in which they visit them, and that order determines which problems each one can solve. DFS, which is depth first search, goes as deep as possible along one path before backtracking. It uses a stack, either the call stack through the recursion or an explicit stack. When DFS reaches a node, it immediately explores one of the node's unvisited neighbors, and it continues deeper and deeper until it reaches a node with no unvisited neighbors. Then it backtracks and tries the next branch. However, BFS, which is breadth first search, it explores all neighbors at the current distance before moving further away. It uses a queue, so when BFS processes a node, it adds all of that node's unvisited neighbors to the queue. Because the queue is first in, first out, all nodes at distance 1 are processed before any node at distance 2. So all nodes at distance 2, then they get processed before all nodes at distance 3 and so on. So this level by level property is what makes BFS the correct choice for shortest path problems in unweighted graphs. If every edge has the same cost, the first time BFS reaches a node, it has found the shortest path to that node. DFS has no such guarantee. DFS might find a path, but it could be a long, winding one rather than the shortest one. Now, so when should you use DFS? DFS is the right choice when you need to explore all paths or all components, detect cycles, perform topological sort, or backtrack through choices. DFS naturally explores one complete branch before trying alternatives, which maps well to these problem types. And when should you use BFS? So for BFS is the right choice, when you need the shortest path in an unweighted graph, when you need level by level processing, when you are spreading, from multiple sources and simultaneously, or when you need the minimum number of steps or move to reach a target. The choice between BFS and DFS is the first decision in any graph problem. Making that choice correctly and explaining the reasoning to your interviewer signals pattern recognition and saves significant implementation time. And this is exactly where the visited set comes in, the mechanism that makes both traversals safe on graphs with cycles. So with trees, we never worried about this visiting the same node twice. The structure of a tree guarantees that there is exactly one path from the root to any node. But graphs can have cycles. Node A connects to node B can connect back to node A. So without a mechanism to remember where we have already been, a traversal will bounce between A and B forever. So to solve this, we have a concept called the visited set. So essentially it is a set data structure that stores every node we have already seen. Before processing any neighbor, we check, okay, is this neighbor already in the visited set? If yes, we skip it. If no, we add it to the visited set and process it. Now, but there is a subtle and critical detail about when to add a node to the visited set, and this is where many candidates actually make mistakes that that is not ideal for interviews. So in BFS, the current time to mark a node as visited is when you add it to the queue, not when you remove it from the queue. So this distinction matters. For example, if you consider node C that is a neighbor of both node A and B, if A and B are both in the queue and we only mark C as visited when we pop it for processing, then both A and B will add C to the queue when they are processed. So now C ends up in the queue twice. This wastes time and in shortest path problems can produce incorrect distance calculations. So the correct BFS pattern actually checks, whether a neighbor is visited before adding to the queue and marks it as a visited at the same moment. This guarantees each node enters a queue exactly once. For recursive DFS, the correct time to mark a node as visited is at the beginning of the recursive call before exploring any neighbors. This prevents the cycle from causing infinite recursion. For iterative DFS using Explicit Stack, the correct time is when you pop the node from the stack. This handles the case where a node might be pushed onto the stack multiple times from different paths. Now, forgetting the visited set entirely is the single most common bug in graph problems. It causes infinite loops on cyclic graphs and time limit exceeded errors on large inputs. In any graph traversal, the visited set should be the first thing you should write, not an afterthought, so the very first thing. Now let us apply these traversal fundamentals to the most common format graph problems appear in during interviews, which is 2D grids. Now, one of the most important recognitions in graph problem solving is that a 2D grid is a graph. When a problem gives you a grid of values and asks about connected regions, shortest paths, or spreading effects, you're solving a graph problem. The grid just happens to be the graph's representation. Each cell in the grid is a node. The edges are the adjacency relationships between cells. In most problems, a cell is adjacent to its 4 neighbors, up, down, left, and right. Some problems use a directional adjacency, which adds the 4 diagonals. The key advantage of grid is that you don't need to build an explicit adjacency list. The grid itself is a representation. So to get the neighbors of cell, let's say row call, you apply 4 offsets, 0, 1 for right, 0, -1 for left, 1, 0 for down, and -1, -1, 0 for up. For each resulting position, you check that it is within the bounds. This direction array pattern appears in every grid graph solution. Now, As you can see here, the getNeighbors function on this slide encapsulates that pattern. So it takes a cell's position and the grid dimensions, applies each offset, checks bounds, and yields valid neighbor positions. Writing this as a helper function keeps the main traversal code clean and avoids repeating bound checks. So the grid traversal then follows the exact same DFS or BFS templates from the previous slides. The only difference is that instead of looking up neighbors in an adjacency list, you compute them using the direction array. And instead of tracking visited nodes by their integer ID, you track them by their row call coordinates. Now, here is what makes this recognition very powerful. Many different grid problems share the same traversal structure. Number of islands problem, for example, it asks you to count connected regions or land cells. Routing oranges problem asks how long it takes for a process to spread across the grid. Shortest path and binary matrix problem asks for the minimum moves from one corner to another. Pacific Atlantic waterfall problem asks which cells can drain to both edges. So basically, different questions, but all of them use the same grid as a graph modeling with the same direction array and the same BFS or DFS traversal. Now, let us walk through the most commonly asked of these problems to see the pattern in action. So, number of islands problem is a very commonly asked graph problem in coding interviews. If you solve one grid-based graph problem before your interview, you have to make it this one. The problem gives you a 2D grid where each cell is either a 1 representing land or a 0 representing water. An island is a group of land cells connected horizontally or vertically. So the question is, how many islands are there? Looking at the example grid over here, there are 3 separate clusters of land cells. The 2 cells in the top left form one island, the single cell in the middle forms another, and the 2 cells in the bottom right form a third. So the answer is 3. The approach is a direct application of connected components. So you scan every cell in the grid from top left to bottom right. When you find a cell that contains 1 and has not been visited yet, that cell is part of a new island. Increment your island count by 1 and then run DFS from that cell to visit every land cell connected to it. This marks the entire island as visited, so you do not count it again. Now, the DFS function, which is mark island, takes the current position and checks 3 things. Is this position within the grid bounds? Is this cell land? Has it already been visited? So if any checks fails, it returns immediately. Otherwise, it marks the cells as visited and recurses in all 4 directions. Now, a clever optimization in this solution is using the grid itself as a visited set. Instead of maintaining a separate set of visited coordinates, we change each visited land cell from 1 to 0. Once a cell is set to 0, the DFS will skip it just as it skips water cells. This saves OFN space but modifies the input. If an interviewer asks about this, mention the trade-off here, that it is more space efficient but it destroys the original data. If the input must be preserved, then you have to use a separate visit set. Now the time complexity is O row times calls, which is because each cell is visited at least once. The space complexity is also O row times call in the worst case for the recursion stack when the entire grid is land. The problem is the gateway to all grid-based problems. Solving this problem actually cleans and quickly sets the tone for harder variant problems, which we'll be covering soon. So both DFS and BFS produce the correct answer for number of islands. The difference is in the practical behavior, and knowing both versions gives you flexibility during an interview. The BFS version replaces the recursive DFS with an iterative approach using a queue. When we find an unvisited land cell, we add it to the queue and mark it as 0. Then we process cells from the queue one at a time, checking all 4 neighbors and adding any unvisited land cells to the queue. The entire island is visited level by level rather than depth by depth. Now the DFS version is simpler to write. It is fewer lines of code and the recursive structure maps naturally to the problem, but it has a critical practical limitation. Now consider a grid that is 500 rows by 500 columns and the entire grid is land. DFS will recurse through every cell, reaching a recursion depth of 250k. So if you're using Python language as part of your interviews, Python's default recursion limit is 1000. This means the DFS solution will crash with Stack Overflow on large, fully connected grids. And if you're using other programming languages, you can also run into similar Stack Overflow problems there as well. Now, BFS avoids this problem entirely. So you don't face the same problem in BFS because it uses an explicit queue, not the call stack. The queue's maximum size is bounded by O of min of rows and calls for a rectangular grid, which is much more manageable than the worst case recursion path. The practical strategy for interviews is to start with DFS, because it's faster to write and easier to explain, but you have to proactively mention the Stack Overflow risk for larger grids and offer to switch to BFS if the interviewer raises concerns about input size. This demonstrates awareness of practical constraints that matter in production systems, not just theoretical correctness. Most candidates only know one approach, so knowing both approaches and being able to discuss when each of them is appropriate to use will make you a much more better candidate in interviews, and it's a clear differentiator. Now that we have seen connected components on a grid, let us generalize the pattern to any graph. The connected components pattern is a number of island problem generalized to any graph, not just grids. A connected components is a group of nodes where each node in the group can reach every other node through some path. In an undirected graph, the number of connected components tell you how many separate clusters exist. Now this algorithm is identical in structure to number of islands problem. However, in this one, you have to iterate over all the nodes. For each node that has not been visited, you start a DFS or BFS traversal from the node. That traversal visits the entire component. Increment your component count, and then you continue to the next unvisited node. Now, as you can see here in the slide, the cloud components function, shows this pattern. First, you build the agency list from the edges. Then loop through all the node IDs from 0 to n-1. For each unvisited node, increment the count and run DFS to visit everything in that component. So this pattern surfaces in many interview problems that do not look like graph problems at first glance. Number of provinces problem asks how many friend groups each exist, given a matrix of friendships. Now, for example, each friend group is a connected component. Account merges problem, it actually asks you, okay, which email accounts belong to the same person, and each person's set of accounts is a connected component. Graph valid trees problem, it actually asks you whether a graph is a valid tree, and a valid tree has exactly one connected component and exactly n-1 edges. So the key insight is that once you recognize the problem is asking you to count, identify, or process separate groups, the connected components pattern applies. Build the graph from whatever input format the problem gives you, and the traversal is the same every time. Now let us look at another graph traversal problem that adds a twist, which is, what if you need to create a copy of the graph rather than just count components? So now clone graph problem actually asks you to create a deep copy of a connected undirected graph. So here you receive a reference of one node, and you need to return a completely new graph where every node is a fresh object with the same values and the same neighbor relationships. The challenge here is cycles. In a connected undirected graph, cycles are common. If node A has node B as a neighbor and node B has node A as a neighbor, a naive cloning approach that follows neighbors recursively will loop forever between A and B. Now the solution here uses a hash map that serves two purposes simultaneously. It acts as a visit set, so telling you which nodes have already been cloned, and it acts as a lookup table, mapping each original node to its clone so you can wire up the neighbor references correctly. And here's how the DFS works. When you visit a node, first check if it already exists in the hash map. If it does, you return the existing clone. If it does not, you create a new node with the same value, immediately add it to the hash map, and then recurse into each neighbor. The clone of each neighbor gets appended to the current clone's neighbor list. Now the critical detail is the order of operations. You must add the clone to the hash map before recursing into neighbors. If you recurse first and add to the map after, a cycle will cause infinite recursion. When DFS follows a cycle back to a node that is currently being processed, the hash map check caches it and returns the existing clone, breaking the loop. The time complexity is O of V plus E because each node and each edge is processed once. The space complexity is OV for the hash map. This same pattern of using a hash map as both a visited set and a reference lookup appears in other problems such as copy list with random pointer problem. The underlying principle is the same. When cloning a structure with cycles or arbitrary references, you need a way to say, okay, I have already created a clone for the original, now here it is. So let us test what we have covered so far with 3 practice problems that all build on the patterns we have just discussed. The first practice problem is this. Given an m by n grid where cells are either 0 for open or 1 for obstacle, find the shortest path from the top left corner to the bottom right corner moving in 8 directions. So what traversal approach should you use and why? The answer is BFS. Anytime a problem asks for the shortest path in an unweighted graph, BFS is the right tool. BFS explores all cells at distance d before any cell at distance d plus 1, which guarantees the first time you reach the destination is via the shortest path. DFS would find a path, but it could be a long winding one. The only difference from number of variance problem is that you use an 8-direction array instead of 4 to handle diagonal movement. Now here's the second practice problem. Given an undirected graph with n nodes and a list of edges, we have to determine if the graph is a valid tree. So now, what conditions define a valid tree? A valid tree must satisfy 2 conditions. First, it must have exactly one connected component, meaning the graph is fully connected. Second, it must have exactly n-1 edges, meaning there are no cycles. And you should check both. Run BFS or DFS from node 0, verify that all n nodes are visited, and verify the edge count equals n-1. If either condition fails, it is not a valid tree. Now here's the third practice problem. Let's say given a grid of 1s and 0s, we have to find the maximum area of an island. And what changes from number of islands problem here? So the traversal is identical, but what changes is what you track during the traversal. Instead of just counting components, you count the number of cells visited during each component's DFS. Each time you complete a component, you compare its size to the current maximum. And then you return the maximum at the end. All 3 practice problems essentially share the core traversal, so the difference is what you measure, whether it's shortest distance, connectivity and edge count, or component size. This is a recurring theme in graph problems. You have to master the traversal once and then adapt the tracking for each specific problem. And now this leads us directly to a powerful variation of BFS that handles problems where spreading happens from multiple starting points at the same time. Now routing origins problem is a pretty common asked problem as well, and introduces a pattern called multi-source BFS. So this problem gives you a grid where each cell is either empty, which is represented by 0, a fresh orange which is represented by 1, or a rotten orange which is represented by 2. Every minute any fresh orange that is adjacent to a rotted orange becomes rotten. The question is this: what is the minimum number of minutes until no fresh oranges remain? If some fresh oranges can never be reached, return -1. So now the key realization is that rotting does not spread from a single source. Multiple rotten origins may exist in the grid and they all rot their neighbors simultaneously in each minute. This is not a single source, shortest path problem. It is a multi-source shortest path problem. Multi-source BFS handles this by initializing the queue with all source nodes at time 0. Starting from one rotten orange and running BFS, we find every rotten orange in the grid and add them all to the queue with a timestamp of 0, and then run a single BFS. Each level of the BFS corresponds to 1 minute. So the first level processes all the initially rotten oranges and rots their fresh neighbors. The second level processes those newly rotten oranges and rots their neighbors, and so on. The algorithm here starts by scanning the grid to find all rotten oranges and counting all fresh oranges. If there are no fresh oranges, the answer is 0 immediately. Otherwise, we process a BFS queue. For each rotten orange, we check its 4 neighbors. If a neighbor is a fresh orange, we mark it rotten, decrement the fresh count, and add it to the queue with time +1. We track the maximum time seen. After the BFS finishes, if the fresh count is still greater than 0, some oranges could not be reached by any rotten orange. They are isolated by empty cells, so we return -1. Otherwise, we return the total minutes. The time and space complexity are both over rows time calls, so every cell is processed at most once. Now let us understand why all rotten oranges starting in the queue at time 0 gives the correct answer. In a single source BFS, we start from one node and measure how far every other node is from the starting point. Multi-source BFS is mathematically equivalent to creating a virtual supersource node that connects to all the real sources with zero cost edges. BFS from this supersource gives the correct minimum distance from any source, not just one. In practice, we do not actually create the supersource node, we simply put all the real sources into the queue at time 0. The effect is the same. Now let us trace through the example here. The grid starts with one rotten orange at position 0, 0 and 6 fresh oranges. At minute 0, we process the rotten orange at 0, 0. It rots the fresh orange at 0, 1 and 1, 0. So fresh count drops from 6 to 4. At minute 1, we process 0, 1 and 1, 0. Position 1, 0, 1 rots 0, 2 and 1, 1. Position 1, 0 tries to rot 1, 1, but it is already rotten. Fresh count, it drops to 2. At minute 2, 1, 1 rots, 2, 1. So fresh count drops to 1. And at minute 3, 2, 1 rots to 2. So fresh count drops to 0. So that is total 4 minutes. Now, a common mistake is actually running separate BFS from each rotten orange independently and taking the minimum time across all runs. This gives incorrect results because it does not account for the simultaneous spreading from all sources. Two rotten oranges spreading toward each other, or they meet in the middle. So separate runs would not capture that correctly. Multi-source BFS handles it naturally because all sources contribute to the same BFS wavefront. When an interviewer asks you, let's say for example, what if there are multiple starting points? The answer follows the same pattern. Put all the starting points in the queue at time 0 and run a single BFS. This applies to walls and gates problem, 0-1 matrix problem, shortest bridge problem, and many other problems as well. Now let us look at a problem that takes multi-source BFS in a completely different direction, which is starting from the boundaries instead of from specific cells. So Pacific Atlantic waterfall problem actually tests whether you can think about graph traversal but in reverse. The problem gives you a grid of elevation heights. So the Pacific Ocean touches the top and left edges. The Atlantic Ocean touches the bottom and right edges. Water flows from a cell to any adjacent cell with equal or lower elevation. So the question is this: find all cells from which water can flow to both oceans. The brute force approach would be to start from every cell and run a DFS or BFS to check whether water can reach both the Pacific border and the Atlantic border. For an m by n grid, that would be O of m and time n traversals, so each potentially visiting the entire grid. That is far too slow actually. Now the key insight is that to reverse the direction of the flow, instead of asking, okay, can water from this cell reach the ocean, you should be asking, okay, can the ocean reach this cell? Start from the ocean borders and flow inward, moving to cells with equal or greater height. This is the reverse of the downhill flow. We are, tracing the path water could have taken to reach the border. Now, here we run two separate multi-source BFS traversals. The first starts from all Pacific border cells, which are the entire top row and the entire left column. It builds a set of all cells reachable from the Pacific. The second starts from all Atlantic border cells, the entire bottom row and the entire right column. It builds a set of cells reachable from the Atlantic. Now, the answer is the intersection of these two sets. Any cell that appears in both the Pacific reachable set and the Atlantic reachable set is a cell from which water can flow to both oceans. This reverse flow technique turns an O of m squared times n squared brute force approach into O of m times n. Two BFS traversals, each visiting every cell at most once. Now the broader question is pretty powerful. When a problem asks you, okay, can x reach y for every starting point, you should consider reversing the direction. start from y and compute reachability backward. And this often converts a quadratic approach into a linear one. This technique actually appears in several other graph problems and is a sign of mature problem solving ability as well. So now we have covered traversal, grids, connected components, and multi-source BFS. Now let us move to a different category of graph problems, which is those involving direction and dependencies. So the first concept we need is cycle detection. So cycle detection and directed graphs answer a fundamental question. Are there any circular dependencies? So if task A depends on task B depends on task C, and task C depends on task A, then no valid execution order exists. Detecting this situation is essential before attempting any topological sort. So the approach uses DFS with 3 states for each node instead of a usual 2. This is a critical distinction from undirected graphs, where a simple visited set with 2 states, which is visited or not visited, would have been sufficient. Now the 3 states are white for unvisited, meaning the node has not been discovered yet, gray for the in the current DFS path, meaning we are currently exploring this node's descendants and have not finished, black for fully processed, meaning all of this node's descendants have been completely explored. Now the algorithm over here, it runs DFS from each unvisited node. When entering a node, you have to mark it gray. Then visit each neighbor, and if the neighbor is white, recurs into it. If a neighbor is gray, we have found a back edge, an edge pointing back to a node that is currently on our DFS path. So that is a cycle. If a neighbor is black, it is safe. That node and all its descendants have already been fully explored without finding a cycle. When DFS finishes processing all of a node's neighbors, you mark the node as black. It is now fully processed. So why can't a simple two-state visited set work here? Because in a directed graph, we need to distinguish between 2 situations. First, we reach a node that is currently being explored in our active path, so that is a cycle. Second, we reach a node that was explored in a previous complete DFS call, that is safe. A 2 system cannot tell these apart. It would report both as already visited, which would either miss cycles or report false positives. Now, this 3-color approach is a foundation for course schedule and every other problem that asks whether a valid dependency ordering exists. Understanding it well actually gives you both cycle detection and topological sort in the same framework. So topological sort answers a very specific question, which is, let's say given a set of items with dependencies between them, in what order should I process them so that every item comes after the items it depends on? So formally, it is a linear ordering of nodes in a directed acyclic graph, which is also termed as DAG, such that for every directed edge from U to V, node U appears before node V in the ordering. Now the word acyclic is essential. Topological sort only works on DAGs. If the graph has a cycle, no valid ordering exists because every node in the cycle would need to come before the others. The ordering is also not unique. When multiple nodes have no remaining dependencies at the same step, any of them can come next. This means the graph can have many valid topological orderings, and the problem is satisfied by returning any one of them. So the recognition signals for topological sort and interview problems are very reliable. If the problem mentions prerequisites, dependencies, ordering, or scheduling, and describe relationships where one thing must come before another, model those relationships as directed edges and apply topological sort. Now, for example, the course schedule problem over here, it uses courses as nodes and prerequisite as edges. Build systems, problem, it actually uses compilation units as nodes and import dependencies as edges. Now, task scheduling problem, it uses tasks as nodes and the condition which is must do X before Y constraints as edges. And package installation problem, it also uses packages as nodes and dependency requirements as edges. And even the spreadsheet evaluation problem, for example, it uses cells as nodes and formula references as edges. So for example, if cell A3 reference cell B1, then B1 must be evaluated before A3. Now there are 2 standard algorithms for topological sort, The first one is Kahn's algorithm, which is BFS based, and a DFS based approach. So Kahn's algorithm is more commonly used in interviews because it is iterative, it avoids recursion depth concerns, and it naturally detects cycles as part of the process. So now let us look at Kahn's algorithm in much more detail. So Kahn's algorithm works by repeatedly finding and removing nodes that have no remaining dependencies. The mechanism it uses for this is in-degree tracking. The in-degree of a node is the number of incoming edges and the number of other nodes that must have come before it. A node with in-degree 0 has no dependencies and can be processed immediately. So the algorithm over here has 4 steps. First, we compute the in-degree of every node. Second, we add all the nodes with in-degree 0 to a queue. So these are the starting points, items with no prerequisites. Third, we process nodes from the queue. For each node you remove, we look at its neighbor and the nodes that depend on it. You reduce each neighbor's in-degree by 1 because one of their dependencies has been satisfied. If any neighbor's in-degree reaches 0, all of its dependencies are now satisfied, so add it to the queue. Fourth, we check the result. If the number of processed nodes equals the total number of nodes, you have a valid topological ordering. If fewer nodes are processed, some nodes were never reached in degree 0, which means they are part of a cycle. The cycle detection is built directly into the algorithm over here. So nodes in a cycle always have at least one incoming edge from another node in the cycle. Their in-degree never reaches 0, so they are never added to the queue. They are never processed, so if len order, in the code here is less than the total node count, cycle exists. Now the time complexity for this is O of v plus c. So each node is processed once and each edge is examined once when reducing the in-degrees. The space complexity for this is O of v plus c for the graph and the in-degree array. Now Kahn's algorithm is the preferred approach in the interviews for 3 main reasons. Number 1, it is iterative, so there are no recursion depth limits. It produces a topological sort directly as a list, and it detects cycles naturally without needing a separate cycle detection pass. So now let us trace through a concrete example to see each step more clearly. So let us trace through Kahn's algorithm on a course prerequisite problem. So we have 4 courses numbered 0 to 3. The prerequisites are 1, 0, meaning course 0 must come before 1, 2, 0, meaning course 0 must come before 2, 3, 1, meaning course 1 must come before 3, and 3, 2, meaning course 2 must come before course 3. Now the graph has edges from 0 to 1, from 0 to 2, from 1 to 3, and from 2 to 3. The in-degrees are course 0 has 0 incoming edges, course 1 has 1, course 2 has 1, and course 3 has 2. Now step 1, we have to find all the nodes with in-degree 0. Only course 0 will qualify, so the queue starts at 0. Step 2, we process course 0, remove it from the queue, and add it to the order. Course 0 has outgoing edges to courses 1 and 2, so we reduce the in-degrees by 1. Course 1 drops from 1 to 0, course 2 drops from 1 to 0. Both reach 0, so both are added to the queue, so the queue now looks as 1 and 2, and the order is 0. Now for step 3, we process course 1. We reduce course 3's in-degree from 2 to 1. Course 3 is not 0 at 0 yet, so it stays out of the queue. The order now is 0, 1. Then for step 4, we process course 2. We reduce course 3's in-degree from 1 to 0. Now course 3 enters the queue. The order is 0, 1, 2. For step 5, we process course 3. It has no outgoing edges, so the order now is 0, 1, 2, 3. So at this point, we have processed all 4 nodes, so there is a valid topological ordering. Take course 0 first, then course 1 and 2, and then in either order, and then you can take course 3. Now consider what happens if we add a cycle. If we add an edge from course 3 back to 0, creating the cycle 0 to 1 to 3 to 0, then course 0's in-degree starts as 1 instead of 0. No node has in-degree 0, the queue starts empty, no nodes are ever processed, the length of the order is 0, which is less than 4, so the cycle is detected. Now this trace over here is worth practicing because interviewers often ask candidates to walk through the algorithm step by step on a small example. So the course schedule problem is a very commonly and frequently asked interview problem. So essentially it asks, given a number of courses and a list of prerequisites, can you finish all courses? Now this is directly a cycle detection problem on a directed graph. So the prerequisite graph contains a cycle. Some set of courses each require another course in the set as a prerequisite. None of them can be taken first, so it is impossible to finish all courses. If the graph is a DAG with no cycles, a valid ordering will exist. Now the solution applies Kahn's algorithm exactly as we discussed. So we build the adjacent list and compute the in degrees from the prerequisites, initialize the queue with all the courses that have in degree 0, then we process the queue reducing the in degrees and adding newly free courses, and at the end we check whether the number of completed courses equals the total number of courses. So the time complexity for this is O of V plus E, where V is the number of courses and E is the number of prerequisite pairs. The space complexity is the same for the graph and the in degrees array. Now the follow-up problem for this, which is course schedule 2, essentially asks you to return the actual ordering instead of just a boolean. The code for that is nearly identical. So instead of counting completed courses, you complete them into a list and return it. If the list length does not equal the total course count, we return an empty list to indicate a cycle. But there's a trap in this problem that catches many candidates and is worth its own discussion. So let's cover that in the next slide. The most common mistake in course schedule problem is reversing the edge direction. The input format is prerequisites I equal to AB, which means to take course A, you must first complete course B. The dependency goes from B to A. The directed edge should be B pointing to A. So now many candidates indistinctively actually build the edge from A to B, which is backwards. This gives incorrect in degrees, produces an incorrect topological order, and returns wrong results. Now let us walk through the correct mapping. So the pair 1, 0 means take course 0 before course 1. The edge is 0 pointing to 1. Course 1's in degree increases by 1. The pair 3, 1 means take course 1 before course 3. The edge is 1 pointing to 3. So course 3's in degrees increases. So in the code over here, it loops as it, for examples. So like for the course in prerequisites, we have to build the edge as graph prereq.append course and increment in degree course. The prerequisite actually, it points to the dependent course, not the other way around. So the edge direction mistake is so frequent that interviewers, specifically watch for it. Getting it right on the first attempt without backtracking and correcting is a quiet but clear signal that you read problems carefully, so you should demonstrate that in an interview. Now here's something important for interviews. When building a dependency graph, you should verbalize the direction out loud. You should say something like, okay, B must come before A, so the edge goes from B to A, and A's in degree increases. This verbal confirmation prevents the most common bug and shows the interviewer that you're thinking deliberately rather than just coding from memory. Now let us practice these patterns with few more practice problems. So let us test what we have covered with 3 practice problems that all use topological sort as the core technique. So the first practice problem is, given a number of courses and prerequisites, we have to return a valid order to take all courses. If no valid order exists, we have to return an empty list. Now this is a course schedule 2 problem. So the approach is identical to Kahn's algorithm template from slide 35. The only change from course schedule 1 is returning the order list instead of a boolean. If the length of the order list equals the number of courses, we return it. Otherwise the cycle exists and you return an empty list. Now the second practice problem is, let's say given a list of words sorted in an alien language, determine the order of characters in the alien alphabet. So this is an alien dictionary problem, as they say. So for example, in this, the insight is that comparing adjacent words reveal character ordering. If the two adjacent words are ABC and ABD, the first differing character is at a position 2, so C versus D. This tells us that in this alien alphabet, C comes before D. This is a directed edge from C to D, so we compare every pair of adjacent words, extract the first different character, build edges, and run topological sort on the characters. If a cycle exists, the order is invalid, returning an empty string. Now here's a third practice problem. Let's say you have n tasks and dependencies. So you find the minimum number of semesters to complete all tasks, given that you can take any number of independent tasks per semester. So the answer maps directly to the level structure in BFS based topological sort. So each BFS level represents one semester because all tasks at that level have their prerequisites already completed. The number of levels is the minimum number of semesters. So this is the exact same level tracking technique we used in tree BFS back in slide 10, applied to the topological sort. And now all three practice problems here use the same Kahn's algorithm. What changes is how you build the graph and what you extract from the traversal result. Recognizing topological sort in these different problem wrappers is a real skill being tested. So now let us cover a data structure that handles a different category of graph problems entirely, which is union find. So union find, also called disjoint set union, solves problems about grouping, merging, and querying connectivity. The recognition signal is clear. The problem asks you to dynamically merge a group of elements and answer whether two elements belong to the same group. The union find supports two operations, so the find operation answers which group does element X belong to. It returns the root or representative of X's group. The union operation merges the groups containing elements X and Y into a single group. Now internally it works like forests or trees. Each element starts as its own tree, its own group. The parent of each element points to itself, so when you call find X, you follow parent pointers from X upward until you reach a node whose parent is itself. That node is the root, the representative of the group. When you call XY, union on XY for example, you find the roots of both elements. If they have different roots, they are in different groups, and you connect one root to other, merging the two trees into one. The basic template on this slide over here, it shows that this exact structure. So the parent array is initialized so that each element is its own parent. The find function follows parent pointers to the root. The union function finds both roots and connects them. So when should you use union find instead of BFS or DFS? Union find is the right tool when edges are added incrementally and you need to query connectivity after each addition. BFS and DFS, they work best when the graph is fully known upfront. If the problem involves merging groups over time and checking are X and Y in the same group now, union find is likely the better choice. But the basic version has a performance problem. In the worst case, the tree can become a long chain, making the find take overfind time complexity. So two optimizations in the next slide will fix this. Third optimizations, union finds find operation can degrade to overfind in the worst case. Imagine elements 0 through 999 chained in a line. 0's parent is 1, 1's parent is 2, all the way to 999. Finding the root of element 0 requires following 999 parent pointers. This is unacceptable for large inputs. So two optimizations bring the amortized cost down to nearly O of 1. The first optimization is path compression. So during a find operation, after you have traced the path to the root, you go back and update every node along the path to point directly to the root. The next time any of those nodes calls find, they reach the root in a single step. In the recursive implementation, there is a single line, self.parent x equals self.find, and inside that you put self.parent x. The recursive call finds the root and the assignment flattens the path. The second optimization is union by rank. So when merging two groups, you need to decide which root becomes a child of the other. Union by rank keeps a rank value for each root, roughly approximately the tree height. When merging the root with the lower rank becomes a child of the root with the higher rank. This keeps the tree balanced and so for example, if both roots have the same rank, you have to pick one as a new root and then increment its rank by 1. So now with both optimizations together, the amortized time per operation is O of alpha of n, where alpha is the inverse Ackermann function. This function grows so slowly that for all practical purposes, for any input size you will ever encounter, it is effectively constant time. So one useful detail in the optimized union function is that you have to return a boolean. It returns true when a merge actually happened, meaning the two elements were in the different groups, it returns false when they are already in the same group. This is helpful for counting connected components. So you start with n components. Each time union returns true, the component counts decreases by 1. This also helps detect redundant edges and graph connectivity problems. Now always use the optimized version in interviews. So the basic version can receive time limit exceeded on large inputs. The optimized version is the only few additional lines and demonstrates that you understand the performance implications. Now let us see the union find applied to one of the most commonly asked problems that uses it. So account merge is the most frequently asked union find problem in coding interviews. And the problem gives you a list of accounts where each account contains a name followed by one or more email addresses. Two accounts belong to the same person if they share at least one email address. The task is to merge all accounts belonging to the same person and return the consolidated list. Now the example has 3 accounts for John. The first account has emails John1 and John2. The second has John3. The third has John1 and John3. So the first and third accounts share John1, so they belong to the same person. The merge group now contains John1, John2, and John3. The third account shares John3 with the same second account, so the second account also joins the group. Now all 3 John accounts merge into one. So this approach maps each email to a unique integer ID, then uses union find on all those IDs. So for example, for each account of them, union all emails in that account together. If the first email is an account is John1 and the another email is John2, so we union their IDs. When a later account also contains John1 and John3, union John1's ID with John3's ID. Through the transitivity of union find, John1, John2, and John3 all end up in the same group. After processing all accounts, group the emails by their root ID using the find operation. Each group represents one person, so you attach the person's name and sort the emails alphabetically as the problem requires. So the time complexity for this is O of n times alpha of n for the union operations plus O of n log n for sorting the emails in each merge account. The space complexity is O of n for the mappings and the union find structure. So the reason this problem tests union find specifically rather than BFS or DFS is that the connections between accounts are discovered incrementally as you process each account. Union find handles this incremental merging naturally. You could also solve it with BFS or DFS by building an explicit graph of email connections and finding connected components, but union find is a more natural and efficient fit. Now that we have covered all 4 major graph tools, let us build a decision framework for choosing which one to use when. So at this point, we have 4 tools in our graph toolkit: BFS, DFS, Topological Sort, and Union Find. Knowing the implementation of each is necessary, but knowing which one to reach for on an ungiven problem is more important. And now here's the decision framework. If the problem asks for the shortest path in an unweighted graph, you use BFS. BFS guarantees the shortest distance through its level-by-level expansion. If the problem asks you to explore all paths or find all connected components, you use DFS or BFS. Either of the approaches works, so DFS tends to be simpler to implement recursively. Now, if the problem involves spreading from multiple sources simultaneously, you should use multi-source BFS. Put all the sources in the queue at time 0. Then, if the problem involves dependencies, prerequisites, or ordering constraints, you should use topological sort with Kahn's algorithm. And then, if the graph is directed and you need to check for cycles, you should use DFS with 3 colors or check whether Kahn's algorithm processes all nodes. If the problem involves dynamically merging groups and querying whether 2 elements are connected, you should use union find. And for the grid problems with connected regions, either DFS or BFS works equally well. So all 4 tools run in O of V plus E time or time complexity, or even better. BFS and DFS, they both use O of V space complexity. Topological sort uses O of V plus E for the graph and n degrees array. Union find uses O of V with nearly constant normalized operations. So if your graph solution has nested loops over all nodes and all edges, resulting in O V times Z or O V squared complexity, you should stop and check whether BFS, DFS, or union find gives a better approach. In almost all interview problems, there is a linear time solution using one of these four tools. The practical value of this decision framework is speed. In an interview, let's just stating your tool choice and reasoning within the first 30 seconds signals confidence and pattern recognition to the interviewer. So it actually tells the interviewer that, okay, you have identified the problem category and you know the approach behind it. Now, before we wrap up this section, there is one more fundamental distinction that affects every graph solution, which is whether the graph is directed or undirected. So the distinction between directed and undirected graphs is not just theoretical. It changes how you build the graph, how you detect cycles, how you identify components, and whether topological sort applies. Getting this distinction wrong produces subtle bugs that are difficult to debug under interview pressure. Now, in an edge representation, undirected graphs add each edge in both directions. If there is an edge between A and B, you add B to A's neighbor list and A to B's neighbor list. Directed graphs, they add the edge in one direction only. If the edge goes from A to B, you add B to A's neighbor list, but not the reverse. In cycle detection, undirected graphs can use a simple two-state system, visited or not visited. The only adjustment is tracking the parent node. In an undirected graph, if you are node B and you came from node A, seeing A and B's neighbor list is not a cycle. It is just the same edge traversed in reverse. You check whether the neighbor is visited and it's not the parent. Now, directed graphs, they require three-state system we have covered earlier, which is white, gray, and black. Any edge back to a gray node is a genuine cycle because direction matters. Now, for connected components in undirected graphs, they are pretty straightforward. You run DFS or BFS from each unvisited node. In directed graphs, the concept splits into weakly and strongly connected components, which require more sophisticated algorithms. Now, topological sort applies only to directed graphs, specifically DAGs, so undirected graphs, they have no concept of direction, so ordering nodes by dependency does not apply here. A common and costly mistake is applying directed graph algorithms to undirected graphs or vice versa. In an undirected graph with an edge between A and B, traversing from A to B and seeing A and B's neighbor list is normal. It is the same edge in a directed graph. If the edge exists from A to B and from B to A, those are two separate edges and they form a cycle. So the first question to answer for any graph problem is this: is this graph directed or undirected? That single determination shapes the edge construction, the cycle detection method, and the available algorithms. Failure rate of any category in coding interviews. But the root causes are not advanced graph theory. There are a small set of implementation mistakes that can be eliminated with disciplined setup. The first and most common mistake is this: forgetting the visited set. This causes infinite loops on any graph with cycles and time limit exceeded errors on large inputs. The fix for this is pretty simple. You add the visited set as the first line of any graph traversal before writing anything else. The second mistake is this: marking a node as visited when processing it instead of when enqueuing it in BFS. This allows the same node to enter the queue multiple times, wasting computation and potentially producing incorrect shortest path calculations. The fix for this is that you should mark visited when adding to the queue, not when popping out of it. The third mistake is reversing edge direction in the core schedule problem. The prerequisite pair A, B means B must come before A. So the edge goes from B to A. Many candidates in the interview actually they build it backwards. So the fix for that is you should read the problem statement carefully and verbalize the direction out loud during the interview. The fourth mistake is this: using a two-state visited set for cycle detection in directed graphs. A two-state system cannot distinguish a path from already which has been processed. So the fix for that is to use the three-color approach: white for unvisited, gray for the incorrect path, and black for fully processed. The fifth mistake is running DFS or BFS from only one node when the graph might be disconnected. If there are multiple connected components, a single traversal from one node misses all the other components. The fix for that is you should loop over all the nodes and start a new traversal from each unvisited one. And here's something important for interviews as well. For any graph problem, follow a 4-step setup before writing the traversal. First, you determine if the graph is directed or undirected. Second, you build the agency list. Third, you initialize the visit set. And fourth, you choose BFS or DFS based on the problem type. This setup takes about 60 seconds and prevents the majority of graph bugs. Interviewers notice when a candidate methodologically sets this up, the graph infrastructure, before diving into the traversal logic. It also signals experience, to interviewers and also reduces errors. Here's a reference card for this entire section. This slide is designed to be, screenshotted, taken in notes, and you essentially use it for revision before the interviews. So the DFS template adds the current node to the visit set, then iterates over its neighbors. For each neighbor not in the visit set, it recurses. That is a complete pattern for recursive DFS with the visit set. The BFS template, it initializes the queue with the start node and adds it to the visit set. Then it processes the nodes from the queue. So for each neighbor not yet visited, it marks the neighbor visited and adds it to the queue. The critical detail is this: you should mark visited when enqueuing, not when dequeuing. The topological sort template uses Kahn's algorithm, computes in degrees, initializes the queue with all 0 in degree nodes, then processes the queue. For each node removed, he reduces its neighbors in degrees. When a neighbor reaches in degree 0, add it to the queue. At the end, check whether all nodes were processed. If not, a cycle exists. The union find template has find with path compression and union with rank. So find follows parent pointers to the root and flattens the path along the way. Union connects the shorter tree under the taller tree. The grid neighbors template uses a 4 action array with bounds checking. Now, for complexities, BFS and DFS are both O of V plus E time complexity and O of V space complexity. The topological sort, it's O of V plus E time and space both. Union find with both optimization is O of V times alpha of V, V time complexity, so which is effectively O of V and O of V space complexity as well. Now grid traversal is O of row times calls for both time and space complexity, and multi-source BFS is O of V plus E time and O of V space. So if your graph solution runs in O of V times E or O of V squared, there is almost certainly a better approach using one of these patterns. Let's recap the 8 patterns we have covered in this section and the signals that tell you when to use each one. So Graph DFS is a tool for exploring paths, detecting cycles, and finding connected components. It uses recursion with the visit set. Graph BFS is a tool for shortest paths and unweighted graphs and level-by-level processing. It uses a queue with a visit set and the key detail in marking nodes visited when enqueuing. Grid as graph converts any 2D grid problem into a graph problem. Each cell is a node, agency is 4-directional, and the direction array pattern applies. Multi-source BFS handles problems where spreading happens from multiple starting points simultaneously. All the sources start in the queue at time 0. Connected components counts or identifies the separate groups by traversing from each unvisited node, whereas the topological sort handles the dependencies and prerequisites using Kahn's algorithm with in-degree tracking. The cycle detection in directed graphs, they uses the 3-color DFS or checks whether the Kahn's processes had all the nodes, whereas the union find it handles dynamic groups merging and connectivity queries using find with path compression and union with rank. So these patterns, they connect forward to material that we'll cover in the upcoming sections. So the BFS shortest path thinking, it actually reappears in dynamic programming on grids in section 5. DFS with backtracking on graphs is the same structure as section 4, where DFS operates on a decision tree. Topological ordering is used in dynamic programming on DAGs in section 5, where nodes must be processed in dependency order. Union find grouping reappears in some interview problems in section 3, and grid traversal is a recurring structure in many DP problems. So now graph problems account for roughly 12 to 15% of coding interview, like the LeetCode problems. So combined with the previous section on trees, now you have tools to handle a significant more portion of more LeetCode interviews. So the remaining sections are on heaps, intervals, greedy algorithms, backtracking, and dynamic programming. So we'll be covering them in the upcoming sections. Now, in the next section, immediate next section, which is section 3, we'll be covering heap, intervals, and greedy algorithms. So for example, graph algorithm problems, they actually model relationships between entities. Heap problems, they model, okay, a concept basically like, okay, give me the best candidate right now. Whereas the intervals, they model, okay, when do the time ranges overlap? And greedy algorithms, they prove that making the locally optimal choice at each step leads to a globally optimal solution. So now let's get started with the next section right away. So this section brings together 3 patterns that share a single underlying idea, which is making the best decision at each step without needing to examine every possibility. Heaps gives you instant access to the smallest or largest element in a changing collection. So interval problems ask you to reason about overlapping time ranges. Greedy algorithms prove that picking the locally best option at every step leads to the globally best result. These 3 are grouped together because they constantly combine. Interval problems almost always start with sorting, then they apply a greedy strategy. Heaps problem, they often follow a greedy approach, which is like take the best next candidate approach. And so like understanding how these patterns interact is just as important and as understanding each one of them individually. So the core idea for this entire section is this: we use heaps when you repeatedly need the best next candidate from a changing set. We use interval sorting when the problem is about overlap or conflict, or we use greedy when a local choice can be justified as globally optimal. So now let's start with the foundation, which is how heaps work. Now before we use heaps to solve problems, we need to understand what a heap actually gives us and why it is the right tool for certain situations. A heap is a data structure that lets you retrieve the smallest element in a min heap or the largest element in a max heap, and in both of them in O of 1 time complexity. Inserting a new element or removing the top element from both, it takes O of log n. This makes heaps the right choice whenever you need repeated access to the extreme value in a collection that keeps changing. If the collection is static and you just need everything sorted, a regular sort is better. But when elements keep arriving or leaving and you need to know the current minimum or maximum after each change, a heap is a tool. Now in Python, the heap queue module provides a min heap, so there is no built-in max heap. The standard workaround is to negate every value before pushing it onto the heap and negate again when you pop. So let's say if you push -5, -2 and -8, the min heap puts -8 at the top, and when you negate the popped value, you get 8, which is the largest of the original values. Now let me walk you through the key operations and their time complexities. Time and space both complexities. So the heap push function, it inserts an element in O of log n. The heap pop function, it removes and returns the smallest element, also in O of log n. Accessing is the top element with heap at index 0 so of 1, since it just peaks without removing. The heapify function converts an existing list into a heap in O of log n, which is faster than pushing elements one at a time. And heap push pop does a push followed by a pop in a single O of log n operation, which is more efficient than calling them separately. Now, here's the important question: when should you use heap instead of just sorting? So there are 4 scenarios to consider. First, if you need all elements in sorted order, sort the entire collection once in O of log n. A heap does not help here, so you should keep that in mind. The second reason is that if you need only the top k elements, a heap of size k runs in O of n log k, which is faster than a full sort when k is much smaller than n. The third reason is if elements arrive one at a time in a stream, you cannot sort a stream. A heap, however, can handle each new element in O of log n. Fourth is if you need the minimum or maximum after repeated modifications, a heap gives you O of log n per operation, while resorting every time would cost you O of n log n each time. The key interview skill here is to recognize the signals. Whenever a problem mentions something like keywords like top k, k at largest, k at smallest, median of a stream, or merge k sorted, that is a signal to reach for a heap. So top k pattern is one of the most common heap applications in interviews. So the recognition signal is pretty straightforward. The problem asks for the k largest, k smallest, and k most frequent, or the kth ranked element. The critical insight is that you do not need all elements sorted, you only need the top k. So here are the two main approaches. The first one is maintaining a min heap of size k to find the k largest elements. And this might seem counterintuitive at first, so let me explain why a min heap, not a max heap, is needed here. A min heap of size k keeps the smallest of the k largest elements at the root. As you process each new element, you compare it against this root. If the new element is larger than the root, it deserves to be in the top k, so you replace the root with the new element. If it is smaller, it does not belong in the top k, so you skip it. Now after processing all the elements, the heap contains exactly the k largest elements. The root of the heap is the kth largest because it is the smallest among the k largest. Now the time complexity for that is O of n log k because you process n elements and each heap operation on a heap size of k will cost you O of log k. Also space complexity is O of k. Now the second approach is quick select. So this works like quicksort but only recurses into one side. You partition the array around a random pivot. If the pivot lands at position k, you are done. If not, you recurse into the side that contains position k. Now the average time is O of n, which is faster than the heap approach, but the worst case is O of n squared, which can happen with bad pivot choices, though randomization makes this extremely unlikely in practice. For interviews, the strong approach is to mention both. You start with the heap approach because it has a guaranteed O of n log k worst case and is easy to write correctly under time pressure. Then you mention the quick select as an optimization with O of n average time but O of n squared worst case. This shows the interviewer that you understand the trade-offs between guaranteed performance and expected performance. So let us apply the top k pattern to one of the most commonly asked interview problems here in LeetCode, so which is top k frequent elements, which is LeetCode problem number 347. So the problem gives you an integer array and an integer k and asks you to return the k most frequent elements. For example, let's say you're given the array 1, 1, 1, 2, 2, and 3. And k equals 2, so the answer is 1 and 2, because 1 appears 3 times and 2 appears 2 times, making them the two most frequent elements. Now the approach combines two steps. Step 1, we build a frequency map in O of n. We walk through the array and count how many times each element appears. Step 2, we use a min heap of size k to find the k elements with the highest frequencies. For each element and its count, we push the pair onto the heap. If the heap size exceeds k, we pop the smallest. After processing all elements, the heap contains the k most frequent. Now the code pushes tuples of count and the number onto the heap. The count comes first because Python as a programming language compares tuples element by element, and we want the heap ordered by frequency. Whenever the heap grows beyond size k, we pop the element with the lowest frequency, which is exactly the one that should be excluded from the top k. Time complexity is O of n log k for the heap operations on top of O of n for building the frequency map. The space complexity is O of n for the frequency map. Now there's also an alternative approach which is using bucket sort that runs in O of n time. The idea is to create an array of buckets where the index represents the frequency. For each element, you place it in the bucket corresponds to its frequency, then you iterate from the highest bucket downward, collecting elements until you have k. This is faster than the heap approach, but uses more memory and is harder to write correctly under time pressure. So for interviews, knowing both approaches and being able to discuss their trade-offs is a strong signal. The heap approach is O of n log k, but straightforward to implement in an interview. The bucket sort approach is O of n, but it requires careful handling of the bucket array and is more error prone when you have to write quickly during an interview. So now this is another very commonly asked interview question, which is kth largest element in an array, and it's LeetCode number problem number 215. Let's say given an array and integer k, you have to return the kth largest element. Note that this is the kth largest including duplicates, not the kth distinct element. Let's say for example you're given the array 3, 2, 1, 5, 6, 4 and k equals 2, and the answer has to be 5. The two largest elements here are 6 and 5, so the second largest is 5. Now the first approach is a min heap of size k, so exactly the pattern we just covered. You initialize the heap with the first k elements, then for each remaining element, if it is larger than the heap's root, you replace the root. After processing all elements, the root of the heap is the kth largest. The time complexity is O of n log k and the space complexity is O of k. Now the second approach is quick select. The key inside is converting kth largest into an index. The kth largest element would sit at an index n minus k in a sorted array. Quick select partitions the array around a random pivot. If the pivot ends up at the target index, we return it. If the pivot is to the left of the target, we recurse into the right partition. If the pivot is to the right, we recurse into the left partition. The average time complexity is O of n because each recursion cuts the problem roughly in half, giving us n plus n by 2 plus n by 4 and so on, which sums to 2n. The worst case is O of n squared if we consistently pick bad pivots, but random pivot selection makes this likely. Now let me walk you through the trade-offs between the three approaches. The min heap, it gives you O of n log k time and O of k space and a guaranteed worst case. Sorting gives you O of n log n time and O of n space and a guaranteed worst case. It gives you O of n average time, O of 1 extra space since it works in place, and O of n squared is in the worst case. In interviews, start with the heap approach because it is safer and easier to code correctly during interviews when the time is limited. Then you should mention the quick select approach to show depth to the interviewers. Now let us move from finding the best k elements to merging k sorted sequences. There is a different heap pattern with a different recognition signal. So the recognition signal is, the problem gives you k sorted sequences, whether they are lists, arrays, linked lists, or streams, and asks you to merge them into one sorted sequence. Or it asks you to find the kth element across all sequences. The idea behind k-way merge is pretty elegant actually. You have k sorted sequences, and at any point the next element in the merge result must be the smallest among the current front elements of all k sequences. A min heap of size k gives you that smallest element in O of log k. After popping the smallest, you push the next element from the same sequence that the popped element came from. Now, this way, the heap always contains exactly one element from each sequence, and the root is always the global minimum of all current candidates. Now, the time complexity here is O of n log k, where n is the total number of elements across all sequences, and k is the number of sequences. Each of the n elements is pushed and popped from a heap of size k, and each push or pop actually costs you O of log k. Now there's an important implementation detail. The heap stores tuples with three values. The first is the element value used for ordering. The second is the list index, which tells you the sequence, which sequence the element came from, so you can push the next element from that same sequence. The third is the element index within that sequence, which tells you where to look for the next element. Without the list index and element index, you would not know which sequence to advance after popping an element. Now this pattern is not just an interview trick, it actually appears in real-world systems as well. External sort algorithms use k-way merge when the data is too large to fit in memory. Database systems use it to merge unsorted runs during a merge sort pass. Understanding this pattern actually connects interview preparation to actual real-world dev work. So let us apply the k-way merge pattern to merge k-sorted lists with LeetCode problem number 23. Now this is a pretty hard-rated problem, but it becomes straightforward once you know the pattern. The problem gives you an array of k-sorted linked lists and asks you to merge them all into one sorted linked list. The approach is exactly the k-way merge template adapted for linked list. So you start by pushing the head node of each non-empty list onto the heap. Each entry in the heap is a tuple of the node's value, the list index, and the node itself. Then repeatedly pop the smallest, attach it to the result linked list, and push that node's next pointer onto the heap if it exists. Now there is a subtle but critical implementation detail here. Python's heap queue compares tuples element by element. So if two nodes have the same value, Python tries to compare the second element of the tuple to break the tie. If the second element is a list node object, Python throws a type error because list node objects do not support comparison. Including the list index as the second element solves this problem. The list index is a unique integer, so the tiebreaker always resolves before Python ever tries to compare the list node objects. Now let me trace through a small example to make this concrete. Suppose we have three lists, 1 to 4 to 5, 1 to 3 to 4, and 2 to 6. So the heap starts with 3 entries, one from each list. So the tuple 1 0 node, 1 1 node, and 2 2 node. We pop the first 1 0 node because it has the smallest value with the smallest tiebreaker index. We add it to the result and push the next node from list 0, which is the node with value 4. Then we pop 1 1 node and add it to the result, push the next from list 1, which has value 3. We continue this process until all nodes are merged and the final result is 1 1 2 3 4 4 5 6. Now the time complexity for this is O of n log k, where n is the total number of nodes and k is the number of lists. The space complexity for this is O of k for the heap. Now this problem, it combines the heap pattern from this section with linked list manipulation, which makes it a great test of pattern integration. Now let us test the heap patterns we have covered so far with 3 practice problems. For each one, we try to identify which heap variant applies before hearing the answer. Now, let's say there's a practice problem 1, which is to given a list of points on a 2D plane, we find the k log closest points to the origin. The pattern here is top k, but notice the detail here. We want the k closest, meaning the k smallest distances. For the k smallest, you use the max heap of size k, not a min heap. In Python, since there is no built-in max heap, you negate the distances. For each point, you compute the square distance. There is no need for square root since we are only comparing relative distances, and squaring preserves ordering. Now, if the negative distance is larger than the heap's root, which means the actual distance is smaller, we replace the root. After processing all points, the heap contains the k closest, so the time complexity is O of n log k. Now for practice problem 2, let's say you're given a stream of integers and you have to find the median after each insertion. This is the 2 heap pattern, also known as find median from data stream. The idea is to maintain 2 heaps, a max heap for the lower half of the numbers and a min heap for the upper half. The max heap's root is the largest of the smaller numbers and the min heap's root is the smallest of the large numbers. If the total count is odd, the median is the root of the larger heap. If even, the median is the average of both roots. Each insertion requires at most 2 heap operations, so it runs in O of n log n per insertion. Now here's practice problem 3, which is to given k-sorted arrays, let's find the kth smallest element across all arrays. This is a k-way merge but with an optimization. You do not need to merge everything. Just run the k-way merge and stop after popping k elements. The kth element you pop is the answer, so the time is O of k log k, which is much better than merging all n elements when k is small. Now the structural insight across all 3 problems is the same. Every heap problem follows a pattern. Maintain a heap of bounded size, push and pop as you process elements, and the heap's root is always the current answer. So what changes between problems is that what you push onto the heap, whether that is values, distances, or frequencies, and what size constraint the heap operates under. So now that we have covered heap patterns, let us move to a different category, which is interval problems. These have a completely different recognition signal and a different core strategy. The recognition signal for interval problems is any mention of time ranges, meetings, schedules, or pairs of start and end values. So keywords like, in the problem statement you should look out for is like, overlap, conflict, merge, intersect, or schedule. They all point to a possibility of an interval problem. So the universal first step for nearly every interval problem is sorting by start time. The single pre-processing step transforms a chaotic set of intervals into something you can reason about sequentially. Once sorted, you only need to compare each interval with the one immediately before it or with the running state. Without sorting, you would need to compare every interval against every other interval, which will be O of n squared. Now let me define this overlap precisely. 2 intervals overlap if and only if each one starts before the other ends. If interval A goes from time, from time lowercase a to lowercase b, and interval b goes from time, let's say, lowercase c to lowercase d. They overlap when a is less than d and c is less than b. After sorting by start time, this simplifies further. If the current interval start is less than the previous interval's end, they overlap. Now, interval problems, they come in several types, but they all follow the same structure: sort, then linear scan. The merge type combines intervals that overlap. The conflict detection type counts or detects overlapping intervals. The removal type greedily selects which intervals to keep to eliminate overlap. The insertion type finds where a new interval fits and merges if needed. And the gap finding type identifies the spaces between sorted intervals. Each of these is a variation on the same core pattern, which is to sort by start time, then walk through the intervals, comparing each one to the current state. Let us work through a very important interview problem, which is merge intervals problem, which is LeetCode problem number 56. This problem is the basis for every other interval problem. So once you can merge intervals, meeting rooms, insert interval, and non-overlapping interval problems, they all become minor variations. Now, this problem gives you an array of intervals and asks you to merge all overlapping intervals into non-overlapping ones. For example, let's say you're given the intervals 1, 3, 2, 6, 8, 10, 15, 18. Then the result will be 1, 6, 8, 10, 15, 18. The first two intervals overlap because the second one starts at 2, which is before the first one ends at 3. So they merge into 1, 6. Now the approach is to sort by start time, then scan from left to right. You start by placing the first interval into the merge result. For each subsequent interval, you check if its start is less than or equal to the last merge interval's end. If yes, they overlap, so you extend the last merge interval's end to the maximum of the two ends. If no, they do not overlap, so you add the current interval as a new entry in the merge result. Now there is a subtle point about why we take the maximum of the two ends rather than just the current interval's end. Now, consider the intervals, like for example 1, 10 and 2, 5. These overlap, but the second interval is entirely contained within the first. If we just set the end to 5, we would shrink the merge interval. Taking the max ensures that we keep it to 110, which is a correct merge result. The time complexity is O of n log n for the sort, followed by a single O of n scan. The space complexity is O of n for the results array. The sort dominates, so the overall time is O of n log n. We trace through the merge logic step by step to make the overlap detection much more concrete. Starting with the intervals 1, 3, 2, 6, 8, 10, 15, 18, which are already sorted by start time. So we initialize the merge list with the first interval. So merge equals 1, 3 now. Now we look at 2, 6. So it starts with 2, which is less than or equal to the last merge interval's end, which is 3. They overlap, so we update the end to the maximum of 3 and 6, which is 6. Merge is now 1, 6. Then we look at 8, 10. So its start 8 is actually greater than the last merge end 6. So there's no overlap. We append the 8, 10. Merge is now 1, 6, 8, 10. We look at 15, 18. Its start 15 is greater than 10. No overlap. We append the 15, 18. Final result is now 1, 6, 8, 10, 15, 18. Now, let me trace an edge case that catches many candidates. Contain intervals. Consider 1, 10, 2, 5, 3, 7. After sorting, which is already sorted, we start with the merge equals 1, 10. We check 2, 5. Start 2 is less than or equal to 10, so there's no overlap. The max of 10 and 5 is 10, so there's no change. Then we check 3, 7. We start 3 is less than or equal to 10, so no overlap. The max of 10 and 7 is 10. No change again here. Both smaller intervals are completely absorbed, so the result is just 110. Now, common mistake here is using strict less than instead of the less than or equal approach in the overlap check. Intervals like 1, 3 and 3, 5 are touching. One ends exactly where the other begins. These should be merged into 1, 5. Using strict less than would miss this case and incorrectly leave them as separate intervals. This is a frequent interval follow-up question, so getting the boundary condition right matters. So we know how to merge overlapping intervals. The next natural question is, what if we do not want to merge them, but instead want to know how many overlap at the same time. This is the meeting rooms 2 problem, which is LeetCode problem 253. Now, given an array of meeting time intervals, you have to find the minimum number of conference rooms required. For example, given the interval 0:30, 5:10, 15:20, the answer is 2. The meeting from 0 to 30 overlaps with the meeting from 5 to 10, so those two need separate rooms. The meeting from 15 to 20 also overlaps with the 0 to 30 meeting, but it does not overlap with the 5 to 10 meeting, so one of the two rooms is free by then. The approach here is different from merge intervals. Instead of comparing consecutive intervals, we split each interval into two events: a start event that adds one room and an end event that frees one room. We sort all events by time, so when a start and end happen at the exact same time, the end event should come first because the room frees up before the next meeting needs it. In Python programming language, like sorting tuples naturally handles this because -1 is less than the positive 1, so time, -1 becomes before time plus 1. Now, then we sweep through the events here, maintaining a running count of active rooms. At each start event, we increment, and at each end event, we decrement. The maximum value the count reaches during the sweep is the answer. Now let us trace through the example. The events are time 0 start, time 5 start, time 10 end, time 15 start, time 20 end, and also the time 30 end in the end. Now at time 0, rooms go to 1. At time 5, rooms go to 2. This is our peak. At time 10, room drop to 1. At time 15, rooms go back to 2. And at time 20, rooms drop to 1. At time 30, rooms reach 0. So the maximum was 2. So we need 2 rooms. So now this event splitting technique is pretty powerful and generalizes far beyond meeting rooms. It works for maximum concurrent users, peak bandwidth, maximum overlapping ranges, or any problem asking for the peak of simultaneous activity. Once you learned it for meeting rooms 2 problem, you can apply it to an entire family of problems. And this leads us to the third major interval problem type, which is non-overlapping intervals, LeetCode problem number 435. This one asks you, okay, given an array of intervals, what is the minimum number of intervals to remove so that the remaining ones does not overlap? For example, let's say the given intervals are 1, 2, 2, 3, 3, 4, 1, 3. So the answer is 1. Remove 1, 3 and the remaining intervals 1, 2, 2, 3, 3, 4 are all non-overlapping. This is fundamentally a greedy problem. The strategy is you sort by the end time, not the start time. Then you greedily keep every interval that does not conflict with the last interval you kept. When do intervals overlap? Always keep the one that ends earlier. Why? Because an interval that ends earlier leaves more room for future intervals. An interval that ends later blocks more of the timeline and potentially forces more removal downstream. Now let me trace through an example here. After sorting by end time, the order is 1, 2, 2, 3, 1, 3, and 3, 4. We start with the last end at -infinity. We check 1, 2, start 1 is greater than or equal to -infinity, so we keep it. Last end becomes 2. We check 2, 3, start 2 is greater than or equal to 2, so we keep it. Last end becomes 3. We check 1, 3, start 1 is less than 3, so it conflicts, we remove it. Removal count is 1. We check 3, 4, start 3 is greater than or equal to 3, so we keep it. Last end becomes 4. Total removals is 1. Now notice why sorting actually, by start time would not work here. If we had sorted by start time, we would get 1, 2, 1, 3, 2, 3, 3, 4. We would keep 1, 2, then face 1, 3, which conflicts, we remove it. But same result for this example, but for other inputs, sorting by start time produces incorrect results because you might keep a longer interval early on that blocks, multiple shorter intervals later. So the time complexity here is O of n log n for sorting plus O of n for linear scan. The space complexity is O of n extra. Now this is equivalent to the classic activity selection problem from algorithm textbooks, and the greedy choice of keeping the earliest ending interval is the probably optimal choice. Now let us practice recognizing interval patterns with 3 practice problems. Try to identify the approach before hearing the answer here. So the first practice problem is, given a list of non-overlapping sorted intervals and a new interval, insert the new interval and merge if necessary. This is the insert interval problem, LeetCode number 57. The approach has three phases. First, you add all the intervals that end before the new interval starts because those cannot overlap. Second, you merge all intervals that overlap with the new interval by tracking the minimum start and maximum end across all overlapping intervals. Third, you add all intervals that start after the new interval ends. Since the input is already sorted, no sorting step is needed and the entire operation runs in overfan. Now the second practice problem is, let's say given a set of intervals representing employees' working hours across multiple employees. You find all the time periods when every employee is free. The approach is to flatten all intervals from all employees into one list, sort by the start time, merge them using the merged intervals pattern, and then return the gaps between the merged intervals. Those gaps are the times when no employee is working. For practice problem number 3, let's say given an array of meeting intervals, determine if a person can attend all meetings. This is meeting rooms 1 problem, the simpler version of meeting rooms 2. You sort by the start time, then you scan linearly. If any meeting start is less than the previous meeting's end, you return false. There is an overlap, so attending all meetings is impossible. This is a merge interval simplified, so instead of merging, you just detect the first conflict. Now the structural insight is the same across all interval problems. You sort, then you do linear scan. What changes is whether you merge, count, remove, insert, or detect during the scan. The sorting step is never optional, so please keep that in mind. So we have already seen greedy thinking in the non-overlapping intervals problem. Now let us formalize what greedy algorithms are and, more importantly, when they work and when they fail. A greedy algorithm makes a locally optimal choice at each step and commits to it without reconsidering. Unlike dynamic programming, which we'll cover in section 5, greedy does not explore all possibilities. It picks the best option right now and then it moves forward. This only produces correct results when the problem has two properties. The first is a greedy choice property. Making the locally optimal choice at each step actually leads to a global optimal solution. The second is optimal substructure, which means that the optimal solution to the problem contains optimal solutions to its subproblems. If both properties hold, greedy works. If either one fails, greedy may give wrong answers here. Now let us walk through a few examples, where greedy works. So for example, for non-overlapping intervals, the greedy choice is to keep the interval ending earliest because it leaves the maximum room for future intervals. For a jump game problem, the greedy choice is to track the farthest reachable position from any valid position. For assigned cookies problem, the greedy choice is to give the smallest sufficient cookie to each child because using a larger cookie on a child who would be satisfied with the smaller one wastes resources. Now here's the critical part. Examples where greedy approach fails. So for example, for coin change problem, with arbitrary denominations, picking the largest coin first can fail. If you have coins of value 1, 3, and 4 and you need to make 6, greedy picks 4, then 1 for 3 coins. But the optimal answer is 3 plus 3 for 2 coins. For 0-1 knapsack problem, for example, picking items with the best value to weight ratio first can miss the better combinations. For longest increasing subsequence, greedily, extending the current subsequence fails to find the globally longest one. So all three of these require dynamic programming approaches. The hardest part of greedy algorithms in interviews is not about writing the code. The code is usually pretty straightforward. The hard part is proving that the greedy choice is the correct choice. And this is what the next slide will cover. Propose a greedy solution in an interview. The interviewer will always ask that, how do you know this is the correct answer? Having a clear justification separates a strong answer from a weak one, and there are two standard proof techniques. The first is the exchange argument. Start by assuming there exists some optimal solution that does not make the greedy choice at some step. Then show that you can swap that step for the greedy choice without making the solution worse. If every non-greedy choice can be exchanged for the greedy choice without losing quality, then the greedy solution is at least as good as any other solution. Now let me make this concrete, with non-overlapping intervals. The greedy choice is to keep the interval that ends earliest. Suppose the optimal solution keeps interval A, which ends later, instead of interval B, which ends earlier. Since B ends before A, everything that does not conflict with A also does not conflict with B. So swapping A for B keeps at least as many intervals in the solution. Therefore, the greedy choice is at least as good as any alternative. Now, the second technique is the stays ahead argument. Here you show that after each greedy step, the greedy solution is at least as good as any other solution at that point. Since greedy is always ahead or equal at every step, it must be at least as good at the end. In practice during interviews, you do not need a formal mathematical proof, you need a convincing one paragraph explanation. Something like, let's say, you can say to the interviewer that, okay, I sort by end time and greedily keep each non-conflicting interval. This works because keeping the interval that ends earliest always leaves the most room for future intervals. If I kept one that ends later, I could only do the same or worse, never better. If you give that answer in the interview, to the interviewer, that would make sense, and you would not need to provide a mathematical proof. Now, a common mistake candidates make is assuming greedy works without any justification. Let's say if you say something like this in an interview that, okay, it seems like sorting by start time and picking the first would work, that is not a valid argument. You need to state what you're optimizing, explain why the greedy choice does not miss better options, and ideally sketch a brief exchange argument. Even a two-sentence justification elevates the quality of your answers significantly. We have now covered heaps, intervals, sorting, and greedy algorithms individually. Now, the next skill is to knowing which one to reach for when you encounter a new problem. Let me walk you through the decision signals. If the problem mentions keywords like top k or k at largest or k at smallest, you need to use a heap. A heap of size k runs in O of n log k, which beats a full log O of n log n sort, when k is much smaller than n. Let's say if the problem says that, okay, merge k sorted sequences, you use a heap for k-way merge. The heap maintains k pointers, one per sequence, and gives you the next smallest in O of log k. If the problem mentions something like, okay, median of a stream, you use two heaps, a max heap for the lower half and a min heap for the upper half, dynamically maintaining the sorted halves as a new element arrive. Now for interval problems, the signals are different. If you see overlapping time ranges and need to merge them, sort by sort time and do a linear scan, and then if you need the maximum number of concurrent events or minimum rooms, you split each interval into start and end events, sort them and do a sweep. If you need to remove the minimum number of intervals to eliminate conflicts, you sort by end time and greedily select. Now the question that comes up, quite a bit in interviews is that, okay, when does greedy approach fails and when you need dynamic programming instead? So here are three examples for that. For coin change with arbitrary denominations problem, you picking the largest coin, first does not always reach the optimal solution because certain combinations of smaller coins can add up to fewer total coins. For knapsack problem, picking the item with the best value to weight ratio first may not fill the knapsack optimally because it might leave gaps, that smaller items could have filled better. For word break problem, matching the longest dictionary word first may block valid splits that use shorter words. All three of these require dynamic programming, which we'll be covering in section 5. So the test is pretty simple. Like you should ask yourself that, okay, does a locally optimal choice always lead to the global optimum, regardless of what comes later? If yes, then greedy approach works. If the answer depends on future choices you have not made yet, then you need dynamic programming. Before we wrap up, let us go through the most common mistakes candidates make in heap and interval problems. Each of these is preventable with a few seconds of careful thought, so please do that. The first mistake is sorting intervals by start time when the problem requires sorting by end time. For merge intervals, sorting by start time is correct, but for problems that ask you to maximize non-overlapping intervals or minimize removals, you need to sort by end time. Using the sort or wrong sort order produces incorrect results, and it is a subtle bug that is hard to catch during the interview. Now the second mistake is using a max heap of size n for k largest problems. A max heap of size n means you heapify all n elements in O of n, then pop k times for O of k log n, giving O of n plus k log n total. A min heap of size k processes each element O of log k, giving O of n log k. When k is small related to n, the min heap approaches significantly faster. More importantly, it uses O of k space instead of O of n. Now, the third mistake is forgetting the tiebreaker index in heap tuples. In Python programming language, when you push a tuples onto a heap, for example, if two tuples have the same first element, Python compares the second element. If the second element is a list node or some other non-comparable object, Python will throw a type error. The fix for that is to always include a unique integer index as a second element of the tuple, so that would be value, then index, and then the object. The fourth mistake is assuming greedy approach works without justification. As we discussed, a correct greedy solution without an explanation of why it is correct is a weaker answer than one with clear justification. The fifth mistake is using the wrong comparison operator for overlap detection. For merge intervals, you use less than or equal because touching intervals should be merged. But for strict overlap detection, some problems use strict less than. Always clarify with the interviewer. If one meeting ends at the time 5 and another starts at time 5, do they conflict? So this question shows attention to detail and prevents a subtle correctness bug in interviews. Now here's a reference card for this entire section. This slide is designed to be essentially screenshotted and used for quick review before the interviews. Now let me walk you through the 5 core pattern templates. For top k, we initialize a min heap with the first k elements, heapify it, then for each remaining element, if it is larger than the heap root, we replace the root. At the end, the heap contains the k largest. For k, we merge, initialize the heap with one element from each list as a tuple of value, list index, and element index. Repeatedly pop the smallest, add it to the result, and push the next element from the same list. For merge intervals, you sort by start time, then scan from left to right, extending the last merge interval's end on overlap and starting a new interval otherwise. For meeting rooms, split each interval into a start event with +1 and an end event with -1. Then you sort all the events and sweep through tracking the running count and maximum. For non-overlapping, sort by end time, and for each interval, keep it if its start is at or after the last kept interval's end, otherwise you remove it. Now, the key complexities to remember is this. Top k with the heap is O of n log k time and O of k space. K-way merge is O of n log k time and O of k space. Merge intervals, meeting rooms, and non-overlapping intervals are all O of n log n time due to sorting step. Quick select is O of n average time with O of 1 space. So if your solution to any of these problems is slower than these bounds, check whether one of these patterns will apply. Let us recap what we have covered in this section and connect it to what comes next. We have covered 6 patterns. So top k uses a min heap of size k where the root is the kth largest. K-way merge uses a heap with one element per list, always popping the smallest. Merge intervals sort by start time and extends the end on overlap. Meeting rooms uses event splitting with +1 and -1, then a sweep line. Non-overlapping intervals sorts by end time and greedily keeps the earliest ending non-conflicting intervals. And greedy algorithms more broadly make locally optimal choices justified by an exchange argument. So these patterns connect to many other parts of the course. Heaps, they reappear in graph algorithms like Dijkstra's shortest path, which we covered in section 2. Greedy selection connects to backtracking, for example, in section 4, which explores all choices when greedy cannot be proven correct. The sort first principle connects back to 2 pointers on sorted arrays, which we covered in the previous course. Interval overlap detection connects forward to dynamic programming problems in section 5 that involve interval scheduling where greedy approach fails. And k-way merge is the generalization of merging of two sorted lists, which we have also covered previously. Now in the next section, section 4, we will be covering backtracking. While greedy algorithms commit to one choice and never reconsider, backtracking explores all possible choices by building a decision tree. It tries a choice, explores the consequences, undoes the choice, and tries the next option. It is a brute force approach made systematic. Now heap, intervals, and greedy problems collectively account for roughly 10 to 15% of LeetCode problems here that are asked into the interviews. So these are among the most pattern recognizable categories, which means the preparation here is definitely, I think personally would be useful. So once you recognize the signal, the solution structure follows almost mechanically. These should be, so now let's move to the next section, which is section number 4. In the previous section, we covered greedy algorithms. Greedy algorithms work, when there is optimal local choice at every step. But many problems, they do not have that property. When the problem asks for all possible combinations, all valid arrangements, or every subset that satisfies the condition, there is no shortcut. The only way to find the answer is to systematically explore every possibility. This is what backtracking does. So backtracking builds a solution one choice at a time. After each choice, it explores the consequences by going deeper. If it reaches a dead end, it undo the last choice and tries the next option. This cycle of try, explore, and undo is the heartbeat of every backtracking algorithm. It is brute force, but is organized brute force. Now here's a mental model that makes backtracking click. Every backtracking problem can be visualized as a decision tree. Each node in the tree represents a partial solution, so each branch represents a choice. The leaves are either complete solutions or dead end. Backtracking is simply depth first search on a decision tree. If that connection to DFS from section 2 feels familiar, then that's absolutely the case here. The recursive structure is identical, so the difference is that the tree is not given to you explicitly. The tree is implied by the choices the problem offers at each step, and your code builds it as it runs. Now, in this section, we will cover the decision tree, a mental model here, the choose, explore, unchoose framework that every backtracking algorithm follows, and a universal template that handles most problems, and then apply it to subsets, permutations, combination sum, and word search on a grid. We'll also cover how to handle duplicates in the input and how to prune branches to reduce the search space. So the core idea to carry through this entire section is this: backtracking explores a decision tree and abandons paths that cannot lead to valid answers. Every backtracking problem follows the same structure, which is choose, explore, and unchoose. Now, every backtracking problem is essentially a tree. This is not a metaphor, it is the literal structure that algorithm traverses. At each level of the tree, the algorithm makes one decision. The branches at the level represent the available choices, so as the algorithm goes deeper, the partial solution grows. When it reaches a leaf where there are no more decisions to make, it has a complete candidate. If that candidate is valid, it gets recorded. Then the algorithm backtracks up to the parent and tries the next branch. Now let us make this concrete with a simple example, which is, let's say for example you have to generate all the subsets of an array containing 1, 2, and 3. At level 1, the decision is whether to include element 1 or exclude it. That gives us 2 branches. At level 2, the decision is whether to include element 2 or exclude it. Each of those branches split into 2 more. At level 3, the same decision for element 3 happens. The tree has a depth 3, 1 level per element, and 8 leaves. Each leaf is a unique subset, and the 8 leaves correspond to the 8 subsets of a 3 element set, which is exactly 2 to the power 3. Now this pattern generalizes to 3 types of decision trees that cover the vast majority of backtracking problems. For subset problems, the decision at each level is include or exclude element I. This gives 2 to the power of n leaves. For permutation problems, the decision at each level is, which unused element to place in the next position. The first level has n choices, the second has n-1, the third has n-2, and so on, giving us n factorial leaves. For combination problems, the decision is which of the remaining elements to pick next, constrained to choosing exactly k elements, which gives c of nk leaves. Now here's why this mental model is pretty important. If you can draw the decision tree for a backtracking problem, you can write the code. The tree structure tells you 3 things directly. First, what choices are available at each step. Those become the loop in your recursive function. Second, when to stop. That becomes your base case. And third, how the recursion branches out. And that becomes your recursive call. In an interview, drawing the decision tree on a whiteboard before writing any code is one of the strongest moves you can do. It shows the interviewer exactly how you think about the problem. It makes the code predictable because the code is just a traversal of the tree you already have drawn and gives you a visual tool to debug if something goes wrong. Now that we have the decision tree mental model, let's talk about the mechanical process the algorithm uses to traverse that tree. Every backtracking algorithm follows a three-step rhythm. Step 1 is choose. You make a decision. This could mean adding an element to the current path, marking a cell as visited in a grid, or placing a piece on a board. The key idea is that the algorithm commits to one option and modifies the state to reflect that commitment. The second step is explore. It recurs with the updated state. This is where the algorithm goes deeper into the tree, exploring all consequences of the choice it just made. The recursion handles everything downstream after that. Now the step 3 is unchoose, so you undo the decision. Removing the element from the path, unmark the cell, take the piece off the board. This step restores the state to exactly what it was before the choice was made, so the next branch starts from a clean slate. As you can see on the screen, in code this looks like a loop over available choices. For each choice, the algorithm checks if the choice is valid given the current state. If it is valid, it adds the choice to the state, recurses, and then removes the choice from the state. The unchoose step is where the most candidates make mistakes, and it is worth understanding deeply why it matters. Now, without undoing the choice, the state accumulates decisions from all branches. When the algorithm finishes exploring one branch and moves to the next branch starts with the leftover state from the previous branch mixed in. The results become completely incorrect, and the unchoose step guarantees that every branch begins from the same clean starting point. This three-step pattern maps to every type of backtracking problem, just with different concrete operations. For subsets, choose means append an element to the path, and unchoose means pop it off. For permutations, choose means swap an element into a position, and unchoosing means swapping it back. For word search on a grid, choosing means mark a cell as visited, and unchoose means you unmark it. For n queens, choose means placing a queen in a column, and unchoose means removing the queen. Now, the framework is pretty universal. If you internalize the three-step rhythm, which is choose, explore, unchoose, you can write backtracking solutions mechanically for the problems you have never seen before. The specific problem determines what choose and unchoose look like. The structure essentially remains the same. That covers approximately a huge majority of backtracking interview problems. So it is worth understanding every line because the same structure appears in subsets, combinations, combination sum, and most of the variant problems. Now the template has two functions. The outer function called solve, it initializes an empty result list, calls the recursive backtrack function, and returns the result. The inner function backtrack, it takes 4 parameters. The result list collects all the valid complete solutions. The path list holds the current partial solution being built. The start index tells the function where to begin choosing from, which prevents revisiting early elements and avoid duplicates. And the nums array is the input to choose from. Inside backtrack, the first thing that happens is the current path gets recorded. A copy of the path is appended to the result list. Then a loop runs from the start to the end of the array. For each index I, the algorithm appends the element at index I to the path, recurses with the start set to I+1, and then pops the element off the path. That is the choose, explore, unchoose cycle in 4 lines of code. Now adapting this template for different problem types requires changing only a few things. For subsets, the base case requires that every node, the loop runs from start to end, and the next start is I+1. So no extra logic is needed here. For combinations of exactly k elements problem, the only change is that the base case records only when the path length equals k, and there is an optional pruning step, which is if the remaining elements are fewer than needed, we skip ahead. Now for combination sum problem with reuse allowed, the base case records when the remaining targets equals 0 and the critical change is passing I instead of I+1 as the next start value. Passing I allows the same element to be chosen again. For permutations problem, the loop always runs from 0 to n. There is no start index at all, and instead a use array tracks which elements have already been placed. The base case records only when the path length equals n. Now this is usually something note down, which is that the differences between subsets, combinations, and permutations are smaller than they appear. Subsets records at every node, combination records only at depth k, permutations consider all unused elements at every level instead of using a start index. So the template is same, only the base case, the loop range, and the next start value change. You should memorize the subsets template and you can adapt it to each variant in a very short amount of time. Let us apply the template to the most fundamental backtracking problem, which is generating all subsets. Given an integer array with unique elements, you have to return all possible subsets, also known as a power set. For the input array, let's say containing 1, 2, and 3, the expected output is 8 subsets. The empty set, the set containing just 1, just 2, just 3, the pairs 1 and 2, the 1 and 3, 2 and 3, and then the full set 1, 2, and 3. Now the code follows the template exactly. You define a result list, define a recursive backtrack function that takes a start index and a path. At the top of the function, you append a copy of the path to the result. Then you loop from the start to the length of nums. For each index I, you append the element, recurse with I plus 1, and then you pop the element. Now there is one detail here that causes more bugs than any other single line in the backtracking code, and it deserves careful explanation. When recording the current path, the code uses path colon in square brackets, which is Python's slice syntax for creating a shallow copy. So why not just append the path directly? Because appending the path stores a reference to the same list object. As backtracking continues, that list object gets modified, elements get appended and popped over and over. By the time the algorithm finishes, every entry in the result list points to the same object, which has been modified back to an empty list. So the result looks like a list of empty lists. So using path colon creates a snapshot of the path at the exact moment, freezing it. The copy is independent of the future modifications. Now the time complexity is O of n times 2 to the n. So there are 2 to the n subsets, and copying each one takes O of n time. The space complexity is O of n for the recursion stack, not counting the output itself. So if you can write the solution from memory, permutations and combination sum problems also become just minor adaptations. So this is a very important foundation here. Let us trace through exactly how the recursion executes for the input 1, 2, and 3. Following this trace is the single most important skill for backtracking interviews, because if you can trace the execution, you can debug any backtracking solution. The algorithm starts by calling backtrack with start equal to 0 and an empty path. The first thing it does is record the empty path. This gives the first subset, which is the empty set. Then the loop begins at I equals 0. It depends 1 to the path, making the path equal to 1. It recurses with start equal to 1. Inside the recursive call, it records the path containing 1. That is our second subset. Then the loop runs with I equal to 1. It appends 2, making the path 1, 2. It recurses with start equal to 2. Inside it records 1, 2. Then I equals 2, it appends 3, and making the path 1, 2, and 3. It recurses with start equal to 3. Inside it records 1, 2, and 3. Now the loop range is empty because start equals the array length, so this call returns. Now here's where the unchoose step actually kicks in. After returning from the recursive call, the algorithm path pops off 3 of the path, restoring it to 1, 2. Then it pops 2, restoring the path to just 1. And now I advances 2, it appends to 3 and making the path 1, 3. It recurses, records 1, 3 and pops 3, then it pops 1, restoring the path to empty. The process continues with 2 as the first element, generating the subsets containing 2 and 2, 3. Finally, 3 is alone. The final result is here as the 8 subsets, exactly the power set. The start parameter is what prevents duplicate subsets. When processing the element at index I, the next recursive call starts at I plus 1. This ensures elements are always chosen in the forward order. Without this constraint, the algorithm would generate both 1, 2 and 2, 1 as separate subsets, which is incorrect for a subset problem where order does not matter. And here's something important for the interviews. If an interviewer asks you to trace through a backtracking solution, do not trace the entire tree. Trace 2 to 3 branches, show one branch going all the way down to a leaf, then show the unchoose step popping elements off, then show the next branch starting fresh. That demonstrates complete understanding without spending 5 minutes on a mechanical exercise. So we have covered subsets. The natural next question is, what changes when order matters? This is exactly what permutations are about. Given an array of distinct integers, return all the possible permutations. Let's say you have the input 1, 2, and 3, then the expected output would be 6 permutations: 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. The fundamental difference from subset is this. In subsets, the elements are always chosen in forward order. The start index moves forward, and the algorithm never looks backward. In permutations, any unused element can go in any position. At each level of the decision tree, every element is a candidate as long as it has not already been used in the current path. So this changes, two things in the code. First, the loop always runs from 0 to n, not from start to n. There is no start index, so you should keep that in mind. Second, instead of a start index to prevent going backward, a used array tracks which elements are currently in the path. Before choosing an element, the algorithm checks if it is already used. If it is, it skips to the next one. Now, the base case also changes. In subsets, the algorithm records at every node because every partial selection is a valid subset. In permutations, only completed arrangements are valid, so the algorithm records only when the path length equals n, the total number of elements. Now, these are the only differences. The choose, explore, unchoose rhythm is identical. You append the element, mark it as used, recurse, pop the element, and mark it as unused. Now the time complexity is O of n times n factorial. There are n factorial permutations, and copying each one takes O of n. The space complexity is O of n for the recursion stack and the use array. A common mistake is using a start index for permutations instead of a used array. A start index prevents elements from appearing out of the original order. That produces combinations, not permutations. Permutations require the freedom to consider every unused element at every position. This is why the used array exists. Permutation is a very commonly asked interview problem, so the key adaptation from subsets, replacing the start index with a used array, is the single most commonly tested backtracking concept. Now let us look at a problem where elements can be reused. Combination sum problem gives you an array of distinct integers called candidates and a target value. The task is to find all unique combinations where the chosen number is summed to the target and the same number can be used as many times as needed. For candidates 2, 3, 6, 7 with a target of 7, there are exactly two valid combinations. 2 plus 2 plus 3 equals 7 and 7 alone equals 7. The question that naturally comes up is this. Okay, how does this differ from regular subsets? So there are two ways that it differs in. First, elements can be reused. This means when the algorithm recurses, it passes I as the next start value, not as I plus 1. Passing I means the same candidate can be chosen again on the next recursive call. Passing I plus 1 would prevent reuse, which is a variant called combination sum 2 problem. This one character difference, I versus I plus 1, is the most frequently tested detail in the backtracking interviews. Now, second is the base case is different. Instead of recording at every node, the algorithm tracks a remaining value that starts at the target and decreases with every choice. When remaining reaches 0, a valid combination has been found. When remaining goes below 0, the current path has exceeded the target and the algorithm prunes that branch by returning immediately. So the code follows the same template. The backtrack function takes start, path, and remaining. If remaining equals 0, we record the path. If remaining is less than 0, we return. Otherwise, we loop from the start to the end of the candidates array, append the candidate, recurse with the same index I, and reduce remaining, and then pop the candidate. The time complexity varies deeply on the input, so in the worst case, it is exponential. The recursion depth is bounded by the target divided by the smallest candidate, which also determines the space complexity. This distinction between passing I for the reuse and I plus 1 for single use comes up in virtually every backtracking interview that involves combination problems. Understanding it clearly separates candidates who have memorized the code from candidates who understand the underlying mechanics. Let us trace through the execution for candidates 2, 3, 6, 7 with the target 7 because seeing the pruning in action makes optimization concrete. The algorithm starts with an empty path and remaining equal to 7. It picks a candidate 2, then picks 2 again, and then 2 again, and then 2 once more. The algorithm prunes and backtracks. It tries 3 after 3 twos, but remaining is -2. Still pruned, so all remaining candidates are even larger, so the entire branch is done. The algorithm backtracks to 2 twos and tries 3 next. 2 twos plus 3 equals 7. Remaining hits 0. That is our first valid combination, which is 2 to 3. Now the algorithm continues exploring. Part 2, 3 leaves remaining at 2. Then 2, 3, 3 gives remaining -1. That is pruned. So part 2, 6 gives remaining -1. That is pruned. Moving to candidate 3 as the first choice. 3 and then 3 gives remaining the 1. So but all remaining candidates are 3 or larger, so nothing fits. That is pruned as well. Eventually the algorithm reaches candidate 7 alone, which gives remaining 0. That is our second valid combination, just 7. So the final result is 2 to 3 and 7. Now this pruning optimization that significantly reduces the number of recursive calls. If the candidates array is sorted, the algorithm can break out of the loop early whenever a candidate exceeds the remaining value. Because the array is sorted, every candidate after that point is even larger and will also exceed remaining. So instead of exploring those branches and discovering they fail, the algorithm never enters them at all. Now the code change is small. We sort the candidates array first, then inside the loop we add a check. If the current candidate is greater than remaining, we break. The rest of the loop and the recursive structures stay analytical. Without this pruning, the algorithm explores many branches that inevitably fail because remaining goes negative. Sorting and breaking early eliminates these branches before they are entered. In practice, this can cut the number of recursive calls in half or more. Adding this optimization without being prompted shows the interviewer that you think about performance, not just correctness. It is a small addition that demonstrates engineering maturity. We have seen had unique elements in the input, but what happens when the input contains duplicates? This is the number one follow-up question in backtracking interviews. What if the input has duplicates? This gets asked in virtually pretty much every backtracking discussion, and having the answer ready is pretty important. Now here's the problem. If the input is 1, 2, 2, and we run the standard subsets algorithm, it treats the two copies of 2 as independent elements. That means the subset containing 1 and the first 2 looks identical to the subset containing 1 and the second 2. The algorithm generates 1, 2 twice. The output has duplicate sets here. So now when you move to the solution here, as you can see, it has two parts and both are required. First is to sort the input array. Second, during the backtracking loop, we add a skip condition. If the current elements equal the previous element and we are not at the first position of the current branching level, we skip it. In code, the skip condition is, okay, if I is greater than start and the element at the index I equals the element at index I minus 1, we continue. That one line eliminates all the duplicate subsets. Now let us break down the why both parts of the conditions matter. The check, which is I greater than start, it ensures that the first occurrence of a duplicate at each branching level is always allowed. Only subsequent occurrences at the same level get skipped. The check element at I equals element at I minus 1. This check identifies when we are looking at a duplicate value. Together, these two conditions mean, okay, we skip the duplicates at the same decision level, but allow the same value to appear at different levels of the tree. A subtle but critical detail. The condition uses I greater than start, not I greater than 0. Using I greater than 0 would skip duplicates globally, preventing the same value from ever appearing deeper in the tree. So now that would be too aggressive. We only want to prevent choosing the same value more than once at the same branching point. The start parameter scopes the comparison to the current level. Now, the same pattern applies across multiple problems. For subsets 2 problem, we add the skip line exactly as described. For combination sums 2 problem, we add the same skip line and also pass I plus 1 for single use. For permutations 2 problem, the skip logic is slightly different because there is no start index. Instead, we sort the array and skip when the current element equals the previous element and the previous element has not been used yet. So let us test the concept we have just covered with 3 practice problems that represent 3 distinct backtracking flavors. For each one, we try to identify the backtracking variant and the key adaptation before reading the answer. So the first practice problem is, okay, given n pairs of parentheses, we generate all the combinations of well-found parentheses. For let's say n equals 3, the output is 5 valid strings like open, 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 close, 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 and open, open, close, close, and so on. Think about what the choices are at each step. At each position in the string, the algorithm can either add an opening parenthesis or a closing parenthesis, but not freely. Two constraints apply here. The number of opening parentheses used cannot exceed n, and the number of closing parentheses cannot exceed the number of opening parentheses used so far. If the algorithm adds a closing parenthesis when there is no matching open one before it, the string becomes invalid. This is backtracking with the constraint-based pruning. The algorithm prunes any branch by adding a closed parenthesis would create an invalid prefix. Now let's talk about the second practice problem. So the second practice problem, given a collection of candidate numbers that may contain duplicates and a target value, we find all unique combinations that sum to the target where each number may only be used once. Now this is a combination sum 2 problem. It combines two adaptations we have already covered. First, we pass I plus 1 instead of I to prevent the reuse of the same element. Second, we add the duplicate skip logic. We sort the candidates first, then we skip when the current candidates equal the previous one at the same branching level. These are exactly the techniques from slide 70 and 71 applied together. Now the third problem, let's talk about that, which is also a very good one, is that given a string of digits from 2 to 9, we have to return all possible letter combinations those digits could represent on a phone keypad. Now this is pure enumeration. At each level of the decision tree, the algorithm picks one of the 3 or 4 letters mapped to the current digit. The tree has depth equal to the number of digits and a branching factor of 3 or 4 at each level. There are no duplicates to handle and no constraints to prune. Every path through the tree is valid. Now these 3 problems demonstrate constraint pruning, duplicate handling, and simple enumeration. Recognizing which flavor of problem belongs to is a key skill for backtracking interviews. Up to this point, every problem we have seen operates on a linear array. Now let us move to a grid. Word search problem is a very commonly asked interview LeetCode problem and combines grid traversal from section 2 with the choose, explore, unchoose framework from this section. So this is the problem. Given an m by n grid of characters and a target word, we have to determine if the word exists in the grid. The word must be constructed from adjacent cells horizontally or vertically, and the same cell cannot be used twice in a single path. For example, given a 3x4 grid and the word A, B, C, C, E, D, the answer is true because there is a path that spells out A, B, C, C, E, D through adjacent cells. The approach is grid backtracking. The outer function scans every cell in the grid, and finds the cell matching the first letter of the word. It starts with a depth-first backtracking search from that cell. At each step, the algorithm checks if the current cell matches the expected letter. If it does, it marks the cell as visited and then recurses to all 4 neighbors looking for the next letter. After the recursive call returns, it restores the cell to its original character. The choose step is replacing the cell's character with a special marker, like the hash symbol, to indicate it has been visited. The explore step is recursing to the 4 neighbors with the next character index. The unchoose step is restoring the original character back into the cell. This is the exact same 3-step rhythm applied to 2D grid instead of a 1D array. Now the base case here, it has 2 parts. So if the character index equals the length of the word, every length has been matched and the function returns true. If the current cell is out of bounds or its character does not match the expected letter, the function returns false. The time complexity is O of m times n times 4 to the power L, where L is the length of the word. For each of the m times n starting cells, the algorithm explores up to 4 directions at each of the L steps. The space complexity is O of L for the recursion stack. Now, the common approach is to use a separate visit set to track which cells have been used. While that works, it uses O of m times n extra space. Modifying the board character in place and restoring it after backtracking uses O of 1 extra space beyond the recursion stack. Interviewers, they generally prefer the in-place approach because it demonstrates awareness of the space efficiency. So this is a concept that comes up in almost every senior level interview when backtracking is discussed. Backtracking is inherently expensive, and understanding exactly why is important for both for choosing when to use it and for communicating about it during an interview. The time complexity of a backtracking algorithm is determined by the size of a decision tree. For subset problems, the tree has 2 to the n leaves because each element is either included or excluded. The total work is O of n times 2 to the n because copying each subset takes O of n. For permutation problems, the tree has n factorial leaves because the first position has n choices, the second has n minus 1, the third has n minus 2, and so on. The total work is O of n times n factorial. So for combinations of n choose k, the tree has C of nk leaves. For combination sum, the complexity depends on the target value and the candidate value, but it is always exponential. For word search problem, the complexity is O of m times n times 4 to the L, where L is the word length. For NQ's problem, the complexity is up to n factorial. Now, these are large numbers. 2 to the 20 power 20 is actually roughly 1 million. 10 factorial is 3.6 million. 20 factorial is about 2.4 times, like 10 to the 18. So these numbers, they do grow fast. Now here's the important nuance. The theoretical worst case is rarely hit in practice because pruning elements branches early. Now in combination sum problem, breaking the loop when a candidate exceeds the remaining target can eliminate half the tree or more. In NQ Queen's problem, checking column and diagonal conflicts prunes the vast majority of branches. And pruning does not change the worst case complexity class, but it does dramatically reduces the actual number of nodes explored. So when is exponential complexity acceptable? Backtracking is the right tool when the input is small, typically n less than or equal to 20 for subset problems and n less than or equal to 10 for permutation problems, and when no polynomial algorithm exists. The constraints in the problem statement are your signal. If n is 15, backtracking is viable. If n is 1000, backtracking will not finish in time and you need a different approach, usually which is dynamic programming. When presenting a backtracking solution in an interview, always state the time complexity and acknowledge that it is exponential. Then explain what pruning you added to reduce this constant factor. This shows the interviewer that you understand the cost and have taken steps to mitigate it. And this connects directly to what comes next, which is if the input is too large for backtracking but the decision tree has overlapping subproblems, dynamic programming in section 5 converts exponential backtracking into polynomial time by caching results. Before we wrap up this section, let us go through the mistakes that cause most candidates to not do ideally well in the backtracking interviews. These are the patterns I have seen repeatedly, and each one is avoidable with a small amount of discipline. Now, the first and most common mistake is not copying the path before storing it. Writing result.append of path instead of result.append of path : stores a reference to the same list object. As backtracking continues, that object gets modified. By the end, every entry in the result list points to the same empty list, or every entry is identical to the last path that was recorded. The fix is pretty simple. Always create a copy using path : or by wrapping path in the list constructor. Now the second mistake is forgetting the unchoose step. Every append must have a matching pop. Every time a cell is marked as visited, it must be unmarked after the recursive call returns. Without the unchoose step, state from one branch leaks into the next, and the results become incorrect in ways that are difficult to debug. The third mistake is using i+1 when the problem allows reuse. In combination sub, passing i+1 prevents the same element from being chosen again, which is wrong behavior. The fix is to pass I instead. Conversely, passing I when the problem requires single-use generate combinations with repeated elements that should not appear. And the fourth mistake is skipping this sort before duplicate handling. So the skip condition that checks if the current element equals the previous element only works when the array is sorted. On unsorted input, equal elements are not adjacent, so the condition never triggers and duplicates slip through. And the fifth mistake is not defining the base case before writing the loop. Without a clear base case, the recursion either never terminates or requires incomplete solutions. Before writing any backtracking code, the base case should be the first thing to define. Now here's something important for interviews. Before writing backtracking code, answer 4 questions. First, what are the choices at each step? Second, when is the solution complete? That is the base case. Third, when should a branch be pruned? Fourth, does the input have duplicates? Answering these 4 questions takes about 60 seconds, eliminates the most common backtracking bugs before they appear in your code. Reference card for this entire section. The slide is essentially, the goal is to use the slide for quick revision before your interviews. So the subsets template loops from start to end, appends the element, recurses I+1 and pops. It records at every node. For subsets with duplicates, sort the array first and add the skip condition. If I is greater than start and the current element equals the previous element, you continue. The permutations template uses a use boolean array instead of a start index. The loop runs from 0 to n. For each element, if it is already used, we skip it. Otherwise, you mark it as used, append it, recurse, pop it, and mark it as unused. Record only when the path length equals n. The combination sum template we reuse tracks the remaining value. When remaining hits 0, we record. When it goes below 0, we return. The loop appends each candidate, recurses with the same index I and reduced remaining, and then pops. Passing I is what enables reuse. Now grid backtracking for word search problem follows the same rhythm on a 2D grid. You mark the cell as visited, recurse to 4 neighbors, and mark the cell. So the key complexities to remember are these. Subsets is O of n times 2 to the power n time complexity and O of n stack space. Permutation problem is actually O of n times n factorial with O of n stack. The combinations of problem of n chooses k is O of k times C of nk with O of k stack. The combination sum is exponential with the stack depth bounded by the target divided by the smallest candidate. And the word search is O of m times n times to the 4 to the power l with the O of l stack. Now every template follows the same rhythm which we have discussed, like choose, which is step 1 is choose, step 2 is explore, and step 3 is unchoose. The only difference between them are the base case, the loop range, and whether the next recursive call passes I or I+1. If you memorize the subsets template, and you will be able to adapt them for each variant easily. Okay, now let us take a step back and look at everything we have covered in this section and how to recognize when each pattern applies. For subsets, the recognition signal is any problem that asks to generate all subsets of the power set. The key insight is making an include or exclude decision for each element and recording the path at every node. For permutation pattern, the signal is generating all arrangements or all orderings. The key insight is using a used array and recording only at complete solutions. For combination sum pattern, the signal is finding combinations that sum to a target. The key adaptation is passing I for reuse or I+1 for a single use. For duplicate handling pattern, the signal is the input containing duplicate elements. The key technique is sorting first, then skipping when the current element equals the previous one at the same branching level. For grid backtracking pattern, the signal is finding a path or word in the grid. The technique is marking cells as visited, recursing to neighbors, and unmarking. For the pruning pattern, the signal is anytime you can determine early that remaining choices cannot lead to a valid solution. The technique is breaking or entering branches that will inevitably fail. So now these patterns, they connect directly to concepts in other sections. So the decision tree structure reappears in section 5, where dynamic programming problems also have decision trees. But the dynamic programming caches results at each node to avoid recomputation. The choose, explore, unchoose framework is structurally identical to DFS on graphs from section 2. Pruning invalid branches related to binary search or an answer from the previous course, where half the search space is eliminated at each step. Now, in section 5, we will be covering dynamic programming next. And here's the bridge between these two sections. Backtracking and dynamic programming, they solve overlapping problem types. If the decision tree has overlapping subproblems where the same state is reached through different paths, backtracking recomputes those states every time it encounters them. Dynamic programming caches the results of each state so it computed only once. This converts exponential backtracking into polynomial time. Dynamic programming is not fundamentally a different technique. It is backtracking essentially with a memory. So Backtracking problems account for roughly 8 to 10 of LeetCode interview problems, and they are considered medium to hard difficulty and are the last major category before dynamic programming. Mastering backtracking is a prerequisite for understanding dynamic programming, and because dynamic programming starts exactly where backtracking becomes too slow. So in this section, we're going to cover dynamic programming. In the previous section, section 4, we covered backtracking, which explores the decision tree exhaustively. Dynamic programming is what happens when that decision tree has repeated work. The same subproblem gets solved again and again through different branches, so dynamic programming eliminates that redundancy by storing the result of each subproblem the first time it's computed and reusing it every time it's needed again. That single idea, which is to cache the results to avoid redundant computation, is what converts an exponential time backtracking solution into a polynomial time dynamic programming solution. And the difference is enormous. Problems that would have taken on paper millions a year with brute force approach, now they become solvable in like milliseconds and like much faster time complexity. So in this section, we'll cover everything we need to do for dynamic programming problems. So we'll first start with the two properties that make a problem a dynamic programming problem. So that is overlapping subproblems and optimal substructure. Then we'll walk through the progression from plain recursion to memoization to devolution, which is a workflow you should follow for every dynamic programming problem. From there, we'll solve the most important dynamic programming problems category by category. First, we'll solve 1D DP problems like climbing stairs, house robber, and coin change problem. Then we'll work on 2D DB problems like unique paths and longest common subsequence. Then sequence dynamic programming problems with problems like longest increasing subsequence. And finally, a knapsack style dynamic programming, which shows up in disguise more often than people realize. So we'll also cover a 5-step framework that works on any dynamic programming problem, even the ones you have never have seen before, and a space optimization technique that interviewers love to ask about as a follow-up. So before solving any dynamic programming problem, you need to know how to recognize one. There are exactly two properties that a problem must solve for dynamic programming to apply. If both are present, we use dynamic programming. If either is missing, dynamic programming is the wrong tool. The first property is overlapping subproblems. This means that during recursion, the same subproblem gets solved multiple times. Think about computing Fibonacci of 5. To get Fibonacci of 5, you need Fibonacci of 4 and Fibonacci of 3. But Fibonacci of 4 itself needs a Fibonacci of 3. So Fibonacci of 3 gets computed twice. Now for larger inputs, this redundancy just explodes exponentially. Every time you see the same computation happening through different recursive paths, that is the overlapping problems. Now the second property is optimal substructure. This means the optimal solution to the whole problem can be constructed from optimal solutions to its subproblems. For example, if you want the shortest path from city A to city C through the city B, that shortest path is the shortest path from A to B combined with the shortest path from B to C. The global optimum is built from the local optima. Now, how do you recognize dynamic programming problems in interviews? There are reliable signals in the problem statement. When the problem asks you phrases like, okay, how many ways to do something, that is counting paths through a decision tree, and those paths almost always overlap. When the problem statements ask you, for like the maximum and minimum cost to achieve something, that is optimization over overlapping subproblems. When the problem asks you like things like, okay, can you reach or achieve X, that is a feasibility problem with dependent choices. And when it mentions the longest or shortest subsequence or substring, that is a sequence optimization. And when the constraints are moderate, say let's say n is at most 1000 or 10,000, that is a strong hint that a polynomial dynamic programming solution is expected because brute force would be too slow. Now, there are common misconceptions worth clearing up. So dynamic programming is not always about filling tables. Memorized recursion, which is top-down dynamic programming, is equally valid and often easier to write. Dynamic programming is not only for optimization, it also counts paths, checks feasibility, and builds sequences. And not every optimization problem is dynamic programming. Greedy problems have optimal substructure but do not have overlapping subproblems. That distinction between greedy and dynamic programming is critical, and we'll revisit that later in this section. Now here's another thing to keep in mind for the interviews. The first 30 seconds of any dynamic programming problem should be spent confirming that both properties hold. If they do, then you commit to dynamic programming. If overlapping subproblems are absent, step back and then consider whether greedy is the right approach instead. So let us go deeper into these two properties because understanding them is super important. Now first is overlapping subproblems. Consider the call tree for Fibonacci of 5 without any caching. Fibonacci of 5 calls Fibonacci of 4 and Fibonacci of 3. Fibonacci of 4 calls Fibonacci of 3 and Fibonacci of 2. Fibonacci of 3 calls Fibonacci of 2 and Fibonacci of 1. Already you can see that Fibonacci of 3 is being computed twice, once from the left branch and once from the right branch. Fibonacci of 2 is computed 3 times, so without caching the total number of calls grows exponentially at O of 2 to the power n. So with caching, each value is computed exactly once, so the total work drops to O of n. So that is the power of recognizing overlapping subproblems. Now optimal substructure, let's consider that. Now consider the problem of finding the minimum cost to reach step n, where at each step you can climb 1 or 2 stairs and each step has a cost. The minimum cost to reach steps n equals the cost of step n plus the smaller of the minimum cost to reach step n minus 1 and the minimum cost to reach step n minus 2. The key insight is that the optimal solution at step n depends only on the optimal solutions at step n minus 1 and n minus 2. You do not need to know the full path that led to those earlier steps, just the optimal values. That is optimal substructure. The global optimum is composed of local optima. So how do you test for these properties in practice? For optimal substructure, you should ask yourself, okay, if I know the best answer for all smaller subproblems, can I compute the best answer for the current problem from them? If the answer is yes, optimal substructure holds. For overlapping subproblems, draw the recursion tree for a small input. If any node appears more than once in the tree, the subproblems overlap. Alternatively, ask whether different sequences of decisions can lead to the same state. If they can, caching that state will work. Now these two tests work on any dynamic programming problem, including ones you have encountered for the first time in an interview. That is why understanding the properties matters much more than memorizing solutions. So now that we know when dynamic programming applies, let us talk about how to actually build a dynamic programming solution. The approach is a 3-step progression and it works for every DP problem. Step 1 is to write the pure recursive solution. Start with the brute force recursion that solves the problem correctly but slowly. Do not worry about efficiency at this point. The goal is correctness. The recursive solution directly expresses the recurrence relation, which is the mathematical relationship between the current problem and its subproblems. It is much easier to think about, okay, what does this state depend on, than to think about in what order should I fill a table. So you should first work on getting that logic right. Now step 2 is to add memorization. This converts your recursive solution into a top-down dynamic programming. You add a cache, which is typically a dictionary or an array, that stores the result of each state the first time it is computed. Before doing any computation, you check, is this result already in the cache? If yes, you return it immediately. If you know, then you compute it, store it in the cache, and then return it. This one change, adding a cache, is what eliminates all the redundant work. It transforms the exponential time into polynomial time. Now step 3 is optional but valuable. Convert the memorized recursion into tabulation, which is bottom-up dynamic programming. Instead of starting from the final state and recursing downward, you start from the base cases and build upward using iteration. You fill a table from the smallest subproblems to the largest. This eliminates recursion overhead and avoids stack depth concerns, which matters for problems with large inputs. The reason this progression works so well is that each step builds on the previous one. The recursive solution gives you the correct recurrence, memorization makes it efficient, and tabulation makes it even more efficient and opens the door to space optimization. The memoization template follows a consistent pattern. The function takes the state as input, It checks whether the state is already in the memo dictionary. If it is, it returns the cache result. If the state is a base case, it returns the base value. Otherwise, you compute the result using a recurrence, store it in the memo, and return it. This template applies to every dynamic programming problem with almost no modification. And here's something you should also remember for our interviews as well. So many interviewers actually prefer the top-down, memorized approach because it maps directly to the recurrence and is easier to explain verbally. Others, they prefer bottom-up tabulation for its efficiency. The safest strategy is to know both and ask the interviewer which one they prefer during the interview. Now let us make memoization concrete with a Fibonacci example. The function takes n and a memo dictionary. If n is already in the memo, return the cache value immediately. If n is 0 or 1, those are yet the base cases and return n directly. Otherwise, you compute Fibonacci of n minus 1 plus Fibonacci of n minus 2, store the result in the memo under the key n, and return it. Now let us trace the call tree for Fibonacci of 5 with memoization. The function calls Fibonacci of 5, which calls Fibonacci of 4, which calls Fibonacci of 3, which calls Fibonacci of 2, which calls Fibonacci of 1, and Fibonacci of 0. So those are base cases returning 1 and 0. So Fibonacci of 2 returns 1, store it in the memo. We back up in the Fibonacci of 3. The second call is Fibonacci of 1, which is base case returning 1. So Fibonacci of 3 returns 2 and gets stored in the memo. Now back in the Fibonacci of 4, the second call is Fibonacci on 2, but Fibonacci on 2 is already in the memo. That is the memo hit, so it returns 1 immediately without any further recursion. So Fibonacci of 4 returns 3 and gets stored. Finally, back at the top level, Fibonacci of 5 needs Fibonacci of 3, which is also a memo hit, returning 2 immediately. The final result is 5. Without memoization, the same computation would have required 15 function calls. With memoization, it requires only 9, and 6 of those are instant memo lookups. For small n, the savings, they seem modest, but as the n grows, the difference becomes pretty dramatic. Without memoization, the time complexity is actually 2 to the power n. With memoization, it is O of n. For n equals 50, that is the difference between computing over a trillion calls versus just 50. The space cost of memoization is the call stack, which is O of n deep, plus the memo dictionary, which stores O of n entries. That is worthwhile trade for the exponential speed up. And here's something important for interviews as well. When presenting a dynamic programming solution, you should start by writing the pure recursive version. Then add the memo dictionary, and you should say something like this to the interviewer. Like that, okay, this is a recursive solution. Let me add memoization to avoid recomputing states. This progression will show the interviewer that, okay, your thought process is much more clear, and it makes it easier for the interviewer to follow your thinking and reasoning. It also minimizes the chance of getting the recurrence wrong because you verify the correctness first with the plain recursive version and then you optimize. Now let us work on the next problem, which is climbing stairs problem, which is LeetCode problem number 70. In this problem, you are climbing a staircase with n steps. Each time you can climb either 1 step or 2 steps. Now the question is that, okay, how many distinct ways you can reach the top? So the key insight is this: to reach step n, you must have come from either step n minus 1 by taking 1 step or step n minus 2 by taking 2 steps. Now there is no other way to arrive at step n, so those are the only 2 ways. So the total number of ways to reach step n becomes the sum of the ways to reach step n minus 1 and the ways to reach step n minus 2. So that gives us the recurrence. Dynamic programming, dp of n equals dp of n minus 1 plus dp of n minus 2. Now, the base cases here are essentially dp of 0 equals 1, meaning that there is only one way to stay at 1 at the ground, which is to do nothing, and dp of 1 equals 1, meaning there's exactly one way to reach step 1, which is take 1 step. Now, if this recurrence looks familiar, it should, because it is exactly the Fibonacci sequence. Climbing stairs is essentially Fibonacci in disguise. The memoized recursion version is pretty straightforward, so the function essentially checks if n is in the memo. If n is 0 or 1, we return 1. Otherwise, we compute the sum of climbing n-1 stairs and climbing n-2 stairs, store it, and then we return it. Now the tabulation version fills an array from left to right. It creates an array of size n+1, sets dp of 0 and dp of 1 both to 1, and then it, for each step I from 2 to up to n, it set the dp of I to dp of I minus 1 plus dp of I minus 2. The answer is dp of n. Now the time complexity is O of n for both approaches. The space complexity is O of n for the table, but as we see shortly, it can be reduced to O of 1 since each state only depends on the previous two. Climbing stairs is worth understanding deeply because every concept it teaches, which is defining the state, rewriting the recurrence, establishing base cases, and choosing between top-down and bottom-up, applies to essentially every dynamic programming in the rest of the section. Now let us look at all the three approaches side by side and trace the actual values. For a staircase with 5 steps, the number of ways for each step is: step 0 has 1 way, step 1 has 1 way, step 2 has 2 ways, step 3 has 3 ways, step 4 has 5 ways, and step 5 has 8 ways. With pure recursion and no caching, computing the answer for step 5 calls step 4 plus step 3. Step 4 calls step 3 plus step 2. Step 3 calls step 2 plus step 1, and each of those branches continues splitting. The total number of calls grows at 2 of 2 to the power n. So for n equals 40, that is over a billion calls. For n equals 50, it becomes pretty impractical on any computer. Now with the memoized recursion, each value is computed exactly once and stored. Every subsequent request for that value is an instant lookup. The total work is O of n time with O of n space for the memo dictionary plus the recursion call stack. With tabulation, you fill the array left to right, starting from the base cases. There is no recursion at all, no function call overhead, and no risk of hitting a stack depth limit. So the total work is the same O of n time, O of n space. Now we can go a step further. Since dp of I only depends on the dp of I minus 1 and dp of I minus 2, we do not need the entire array. We only need two variables, one to hold the previous value and one to hold the value before that. At each step, we compute the current value as the sum of those two, then shift them forward. This brings the space complexity to O of 1. Now this is something you should definitely note it down, that the progression is always the same for every dynamic programming problem. First, you write the recursive solution for correctness. Second, add the memoization to get the O of n time. Third, you convert to tabulation to eliminate recursion overhead. Fourth, you optimize the space if the current state only depends on a few previous states. This 4-step progression is a workflow you should follow on every DP problem in this section and most likely all the interviews for dynamic programming problems. Now that we have seen both approaches on climbing stairs, let us talk about when and why you would convert from memoization to tabulation. Now memoization uses recursion, and recursion has two costs. First, every recursive call adds a frame to the call stack which consumes memory. For a problem with a state space of let's say 100,000, that is 100,000 stack frames. Many languages have a default recursion limit well below that. Second is function call overheads, it adds up. Each call has the cost of pushing arguments, saving registers, and returning values. Tabulation replaces all of that with a simple loop. It starts from the base cases and builds the table upward using iteration. There is no call stack, no recursion limit, and no function call overhead. The conversion process is pretty mechanical. So for example, you have to first identify the base cases, which is the smallest subproblems with known answers. Second, you create a table with the same dimensions as the memo would have. Third, you fill in the base cases in the table. And fourth, you determine the fill order. States must be computed before any state that depends on them. For most 1D problems, that is left to right. For most 2D problems, that is top to bottom, left to right. And fifth, you replace each recursive call with a direct table lookup. So when is each approach better? Memoization is better when not all states are needed. It only computes the states that are actually requested through the recursion, skipping unreachable states. Tabulation is better when all states will be needed anyway because it avoids the recursion overhead. Memoization is also better when the state space is very large but only a sparse subset is reachable. Tabulation is better when you want to optimize space because it is easier to see which rows of variables you actually need. And under interview pressure, memoization is generally simpler to get right because it follows the recurrence directly. Now the practical advice for interview is this. If you are unsure, you should start with memoization. It is hard to get wrong, then offer to convert to tabulization, if the interviewers ask for it. Knowing both approaches and being able to switch between them on demand is the mark of a well-prepared candidate. What do you have covered so far? For each of the following problems, the question is this. Should these be solved with dynamic programming, greedy approach, or backtracking? So the first practice problem is this. Given a set of coin denominations and a target amount, we have to find the minimum number of coins needed to make the target. Think about this for a moment. The answer is dynamic programming, because the greedy approach, which is to always pick the largest coin, fails for the arbitrary denominations. Consider the coins of values 1, 3, and 4 with a target of 6. Greedy picks the 4 coin first, then 2 1 coins for a total of 3 coins. But the optimal solution is 2 3 coins, which uses only 2 coins. The problem has overlapping subproblems because many different combinations of coins can reach the same remaining amount. It has the optimal substructure because the minimum coins for amount n depends on the minimum coins for smaller amounts, so the both properties hold, so dynamic programming is correct. Now let's work on the second practice problem. Now given an array of non-overlapping intervals, you have to sorted by the start time. We have to insert a new interval and merge if necessary. So for this, the answer is greedy. A single left to right scan handle all cases. There are no overlapping subproblems. Each interval is processed once, and the decision at each step is straightforward. DB would be unnecessary complexity here. Now let's work on the third practice problem. So which is, we have to generate all the valid arrangements of n queens on an n by n chessboard. The answer is backtracking. And the problem asks for all valid arrangements, not the count of them or the optimal one. Each board state is unique, so there are no overlapping subproblems. Backtracking is the right approach, because it systematically explores all placements and prunes the invalid ones. Now the decision rule to remember is this. If the problem asks for a count, a minimum, or a maximum, and the same state can be reached through multiple paths, you should use dynamic programming. If a locally optimal choice is probably correct at every step, you should use greedy. If you need all valid solutions enumerated, you should use backtracking. Okay, now let us talk about the most common category of dynamic programming problems in interviews, which is 1D dynamic programming. So now the recognition signal is pretty simple. The state can be described by a single variable. That variable is usually an index into the input array or an amount you are trying to reach. The answer of state I depends on the answers for one or more previous states. The general form is this. dp of I equals some function of dp of I minus 1, dp of I minus 2, and potentially other earlier states. Now let me walk you through the most important 1D dynamic programming problems because these are the ones you'll see in interviews pretty often. In climbing stairs, dp of I represents the number of ways to reach step I, and the recurrence of is dp of I equals dp of I minus 1 plus dp of I minus 2. In house robber problem, dp of I represents the maximum money you can rob from a house 0 through I, and the recurrence of dp of I equals the larger of dp of I minus 1 and dp of I minus 2 plus nums of I. In coin change problem, dp of I represents the minimum coins needed for amount I, and the recurrence of dp of I equals the minimum of dp of I minus c plus 1, where you would try every coin c. In word break problem, dp of I is the true if the first I characters of the string can be segmented into dictionary words. And in decode ways problem, dp of I counts how many ways to decode the first I digits. And the maximum subarray problem, dp of I is the maximum sum of a subarray ending at index I. Now the template for 1D dynamic programming problem is pretty consistent. You create an array of size n plus 1, fill in the base cases for dp of 0 and dp of 1, then loop from 2 to n, computing each state from its dependencies. Then you return dp of n. If you can define the state, write the recurrence for those 6 problems, you can handle the vast majority of 1D dynamic programming questions that appear in LeetCode interviews. Now we're going to walk through the very important problem in the next slide. So let's cover that. Now let's cover the house robber problem, which is the LeetCode problem number 198. Now in this problem, assume that you're planning to rob houses along a street. Each house has a certain amount of money. The constraint is that adjacent houses have connected alarm systems. If you rob 2 houses that are next to each other, the alarm triggers. The goal is to find the maximum amount of money you can rob without triggering any alarms. Now let us work through a concrete example. Let's say given the array 27931, the expected answer is 12, which comes from robbing houses at position 0, 2, and 4. That would be, total of 2 plus 9 plus 1. So the key insight is that each house I, you face exactly 2 choices. Choice 1, you skip house I. In that house, your best total through house I is the same as your best total through house I minus 1. Choice 2, you rob house I. In that case, you cannot rob house I minus 1 because of the alarm, so your best total is the money in house I plus your best total through house I minus 2. Now you take whichever choice gives you more money. That gives the recurrence, dp of I equals the larger of dp of I minus 1 and dp of I minus 2 plus nums of I. Now the base cases are essentially dp of 0 equals nums of 0, because only one house available, so you have to rob it, and dp of 1 equals the larger of nums 0 and nums 1, because you pick the better of the first 2 houses. The code here, it creates an array, fills in these base cases, loops from house 2 to the end, applying the recurrence, and returns the last element of the array. The time complexity is O of n and space complexity is O of n as well. Now this include exclude pattern is not unique to house robber. It reappears in 0 and 1 knapsack problem, in stock trading problems with cooldowns, and many other dynamic programming problems. Learning to recognize it here means that you will recognize it in those problems as well. Let's trace through the recurrence step by step to make sure the logic is clear. Given the array 27931, dp of 0 is 2 because only house 0 is available and its value is 2. dp of 1 is the larger of 2 and 7, which is 7. We pick the best of the first 2 houses. Now dp of 2, we choose the larger of dp of 1, which is 7, meaning we skip house 2. And dp of 0 plus 9, which is 2 plus 9 equals 11, meaning we rob house 2. 11 is larger, so dp of 2 equals 11. Now dp of 3, we choose the larger of dp of 2, which is 11, skip house 3, and dp of 1 plus 3, which is 7 plus 3 equals 10, rob house 3. 11 is larger, so dp of 3 equals 11, we skip house 3. Now dp of 4, we choose the larger of dp of 3, which is 11, skip house 4, and dp of 2 plus 1, which is 11, plus 1 equals 12, we rob house 4. And 12 is larger, so dp of 4 equals 12, the final answer is 12. Now there is a subtle detail in the base case that is worth understanding. Why is dp of 1 the larger of nums of 0 and nums of 1 and not just the nums of 1? Because at house 1 you have a choice. You rob house 0 or rob house 1. You cannot rob both since they are adjacent. If you set dp of 1 to just nums of 1, you would miss the case where house 0 has more money than house 1. Now for the space optimized version, notice that dp of I only depends on dp of I minus 1 and dp of I minus 2. So you can replace the entire array with just 2 variables. Previous one holding dp of I minus 1 and previous 2 holding dp of I minus 2. At each step, compute the current value, then shift both variables forward. This brings space complexity down to O of 1. And here's something important for interviews. After presenting the O of n space solution, immediately offer the O of 1 optimization. You should say something like, since each state only depends on the previous 2, I can use 2 variables instead of an array. This is the expected follow-up for nearly every 1D TP dynamic programming problem, and offering it proactively shows confidence to the interviewer. The include or exclude recurrence dp of I equals the larger of dp of I minus 1 and dp of I minus 2 plus nums of I. This is the most fundamental dp recurrence that there is. You should master it well, and you'll recognize it in knapsack problem, stock trading problem, and many other problems as well. The coin change problem is LeetCode problem number 322, and it's a very commonly asked dynamic programming problem in interviews. It is also the most important example of why greedy approach fails and why dynamic programming is necessary. The problem gives you a set of coin denominations and a target amount. You return the minimum number of coins needed to make that amount. If it is impossible, you return -1. Let us work with coins of values 1, 3, and 4 and a target amount of 6. The expected answer is 2 using 2 coins of value 3. Now here's why greedy approach fails on this problem. The greedy approach picks the largest coin first, 4 plus 1 plus 1, which uses 3 coins, but the optimal is 3 plus 3, which uses only 2 coins. The greedy choice of taking the largest coin is not always optimal because using a smaller coin now can lead to fewer total coins later. This is exactly the situation where overlapping subproblems and optimal substructure both hold, making the dynamic programming the right approach. The recurrence works as follows. So for example, for each amount I from 1 to up to the target, you try every coin C. If using coin C is valid, meaning I minus C is non-negative and dp of I minus C is not infinity, then dp of I equals the minimum of its current value and dp of I minus C plus 1. The plus 1 accounts for the one coin that you have just used. Now, the base case here is the dp of 0 equals 0, so it takes 0 coins to make amount 0. Every other entry starts at infinity, meaning not yet achievable. The code creates an array of size amount plus 1, initializes everything to infinity except dp of 0, then loops through each amount, trying each coin. The time complexity is O of amount times the number of coins, and the space complexity is O of amount. Now, being able to explain clearly why greedy fails on coin change and why dp is needed here is something interviewers specifically look for. It demonstrates that you understand the fundamental difference between the two approaches. Let us trace the entire tabulation step by step for coins 1, 3, 4 and amount 6. We start with the array 0, infinity, 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 infinity. So the dp of 0 is 0 and everything else is infinity. For amount 1, we try coin 1. dp of 1 equals the minimum of infinity and dp of 0 plus 1, which is 1. Coins 3 and 4 are larger than 1, so we skip them. dp of 1 is 1. For amount 2, we try coin 1. dp of 2 equals the minimum of infinity and dp of 1 plus 1, which is 2. So dp of 2 is 2. Now for amount 3 here, we try coin 1. dp of 3 equals the minimum of infinity and dp of 2 plus 1, which is 3. Then we try coin 3. dp of 3 equals the minimum of 3 and dp of 0 plus 1, which is 1. So dp of 3 drops from 3 to 1. So that makes sense, because one value of value 3 is better than 3 coins of value 1. Now for amount 4, we try coin 1. dp of 4 becomes 2. Then coin 3. dp of 4 stays at 2. Then coin 4. dp of 4 equals the minimum of 2 and dp of 0 plus 1, which is 1. So dp of 4 is 1. For amount 5, we try coin 1. dp of 5 becomes 2. Coin 3 and 4 also give 2. So dp of 5 is 2. For amount 6, we try coin 1. dp of 6 becomes 3. Then coin 3. dp of 6 equals the minimum of 3 and dp of 3 plus 1, which is 2. So dp of 6 drops to 2. The final answer is 2. Now, reading this table over here, dp of I tells you the minimum order of coins needed to make the amount I. If dp of I remains at infinity, it means amount of I is impossible with the given coins. One common mistake to watch out for is this: initializing dp of 0 as infinity instead of 0. dp of 0 must be 0 because it takes 0 coins to make amount 0. Without this, no state can compute this value from the base case and everything stays at infinity. Now, being able to trace the tabulation step by step on a whiteboard is one of the strongest ways to demonstrate understanding of dynamic programming. Interviewers often ask you to walk through 3 or 4 entries to verify your recurrence approach is correct. Let's test what we have covered with 3 1D DB problems. For each one, we try to define the state and recurrence before reading the answer. So here's the practice problem 1. Given a string and a dictionary of words, determine if the string can be split into a sequence of dictionary words. For example, the string LeetCode with dictionary leet and code returns true. The state is dp of I, which is true if the first I character of the string can be segmented. The recurrence checks, every possible split point j before I. dp of I is true if there exists some j where dp of j is true and the substring from position j to position I is in the dictionary. The base case is dp of 0 equals true, representing the empty string. The time complexity is O of n squared, or O of n times m, where m is the maximum word length. Now here's a practice problem 2. You have n houses in row. Each can be painted red, blue, or green with different costs. No two adjacent houses can be of the same color. You have to find the minimum total cost. The state is dp of I for each color C, meaning the minimum cost to paint houses 0 through I with house I painted color C. So the recurrence is this. dp of I for color C equals the cost of painting house I with color C plus the minimum of dp of I minus 1 for the other two colors. This is essentially 1D dp problem with a small second dimension of 3 colors. Now let's look at practice problem number 3. So in that, given a string of digits, you have to return the number of ways to decode it, where A is 1, B is 2, through Z or Z, is 26. The state of dpi, the number of ways to decode the first I characters. So if the single digit at the position I minus 1 is between 1 and 9, you add dp of I minus 1. If the two digits at position I minus 2 and I minus 1 form a number between 10 and 26, you add dp of I minus 2. The base case is dp of 0 equals 1. So all three problems, they follow the same 1D dp structure. You define dp of I, then you write the recurrence, fill the table left to right. The core skill is translating the problem description into a precise state definition. Now that we have covered 1D dp, let us move into the problems where a single variable is not enough to describe the state. In 2D dp, the state requires two variables. Now the recognition signal is that you need two pieces of information to describe a subproblem. That could be two indices into two different things, a row, a column position in a grid, or an item index combined with the remaining capacity. The answer for state ij depends, on answers for nearby states in the 2D table. Now the general form is this. dp of ij equals some function of dp of I minus 1 for j, dp of I for j minus 1, dp of I minus 1 for j minus 1, or some combination of these. Now, the most common 2D dp problems are problems like unique path problems, where dp of ij is the number of ways to reach cell ij in a grid. Minimum path sum problem, where dp of ij is the minimum cost to reach cell ij. Longest common subsequence problem, where dp of ij is the LCS length for the first I characters of one string and the first j characters of another. Edit distance problem, where dp of ij is the minimum edits to transform one string prefix to another. And 0-1 knapsack problem, where dp of I w is the maximum value using the first I items with the capacity w. Now the template for all these problems is actually pretty consistent. You create a 2D array with dimensions n plus 1 by n plus 1. You fill the base cases for the first row and the first column. Then you fill the rest of the table using nested loops, top to bottom and left to right, applying the recurrence at each cell. The answer is at the dp of mn. Now the key skill for 2D dp problems is identifying what the two dimensions represent and determining the fill order. Once you have those, writing the code is pretty mechanical. Now unique paths problem is a LeetCode problem 62 and is the simplest, one of the most commonly asked dp problem. Now the problem is this. A robot starts at top left corner of an m by n grid. It can only move right or down. So how many unique paths exist to reach the bottom right corner? The insight is same as climbing stairs problem, but now in 2 dimensions. To reach cell ij, the robot must have come from either the cell directly above, which is I minus 1 j, or the cell directly to the left, which is I j minus 1. So the number of paths to cell ij is the sum of paths to those two cells. So the recurrence is dp of I and j equals dp of I minus 1, j plus dp of I, j minus 1. Now the base cases, they follow pretty naturally. The entire first row is all ones because the only way to reach any cell in the first row is to go right the whole way. The entire first column is all ones because the only way to reach any cell in the first column is to go down the whole way. Now let us trace a small example with 3 rows and 4 columns. Now the first row is 1, 1, 1, 1. The first column is 1, 1, 1. The cell at row 1, column 1 is 1 plus 1 equals 2. Row 1, column 2 is 1 plus 2 equals 3. Row 1, column 3 is 1 plus 3 equals 4. Row 2, column 1 is 1 plus 2 equals 3. Row 2, column 2 is 3 plus 3 equals 6. And row 2, column 3 is 4 plus 6 equals 10. So there are 10 unique paths in a 3 by 4 grid. Now the time complexity for this is O of m times n, and the space complexity is O of m times n for the full table, but as we will see, it can be reduced to O of n by only keeping one row at a time. Now the unique paths problem here directly demonstrates how grid dynamic programming works. You fill top to bottom, left to right. Each cell depends on its top and left neighbors. The foundation applies to problems like minimum path sum problem, unique paths 2 problem with obstacles, and many other grid dynamic programming problems. Now there is a concept that underpins every grid dynamic programming problem, and getting it wrong is now one of the most commonly source of bugs. Now in grid DP, each cell depends on cells that have already been computed. For the recurrence dp of ij equals dp of I minus 1, j plus dp of I, j minus 1, cell ij depends on the cell directly above it and the cell directly to the left. Both of those cells must have the correct values before we compute ij. Now this is why the fill order matters. If you fill the grid top to bottom, left to right, also called row major order, then by the time you reach cell ij, the cell above, which is row I minus 1, and the cell to the left, which is column j minus 1, have both already been filled. The dependency is always satisfied if you do it this way. Now here's the space optimization. So since each row only depends on the row directly above it, you do not need to keep the entire 2D table in memory. A single 1D array of length n is enough. The trick is that when you are updating dp of j, the value of dp of j currently holds the value from the previous row, which is dp of I minus 1 j. And dp of j minus 1 has already been updated for the current row, which gives you dp of ij minus 1. Adding them gives you a dp of I, j, so you override the dp of j with this new value and then you move on. Now this reduces the space complexity from O of m times n to O of n. For a grid with 1000 rows and 1000 columns, that is the difference between storing 1 million values and storing 1000 values. Now there are the variation of grid DP that changes the dependencies. In minimum path sum problem, the dependency is the same top and left, but instead of adding the counts, you take the minimum and add the current cell's cost. In unique paths 2 problem, some cells obstacles and contribute 0 paths. In dungeon game problem, the dependencies are reversed. Each cell depends on the cell below and to the right, so you fill the grid bottom to top. Now understanding the fill order and being able to optimize space from O of m times n to O of n is essential because interviewers are constantly asking for this optimization as a follow-up question. Now let's talk about the longest common subsequence problem, which is LeetCode number problem 1143. It is a very commonly asked dynamic programming problem as well. So if you understand LCS, you can essentially solve edit distance problem, shortest common subsequence problem, and other string transformation problems with minimal additional effort. Now this problem gives you 2 strings and asks for the length of their longest common subsequence. A subsequence is derived by deleting some or no characters without changing the relative order of the remaining characters. Now given text 1 equals, let's say, A, B, C, D, E, and text 2 equals A, C, E, the expected answer is 3 because the LCS is A, C, E. The recurrence is built on a simple comparison, so consider the characters at positions I and j in 2 strings. If they match, both characters contribute to the LCS, so we take the LCS of the strings without those characters and add 1, which will be dp of ij equals dp of I minus 1, j minus 1 plus 1. Now if they do not match, one of the characters does not contribute. So we take the better of two options, which is to skip a character from the first string, which is dp of I minus 1j, or skip a character from the second string, which is dp of I j minus 1. dp of I j equals the larger of those two. Now the base cases of the first row and the first column are all zeros, representing comparison against an empty string. The LCS of any string with an empty string is 0. The code here creates a 2D array of size m plus 1 by n plus 1, initialize it to zeros, and fill it with nested loops. For each pair of positions, we check if the characters match. If they do, we go diagonal plus 1. If they do not, we take the larger of up or left, and the answer is at the dp of m by n. Now the time complexity is O of m times n, where m and n are the lengths of two strings. Space complexity is O of m times n, which can be optimized to O of n using the row compression technique. Now LCS is foundational because the two-case structure match, it goes diagonal, and mismatch takes the better of up or left, reappears in the edit distance problem, shortest common subsequence problem, and diff algorithms used in version control systems. Now let us trace the full table for text1 equals ABCDE and text2 equals ACE. The table has 6 rows for characters, empty ABCDE of text1, and 4 columns for characters, empty ACE of text2. The first row and first column are all zeros. At position 1, one text, one character A matches the text2 character A. So we go diagonal, dp of 0, 0 plus 1 equals 1. At position 1, 2, text 1 character A does not match to text 2 character C. Take the larger of dp of 0, 2, which is 0, and dp of 1, 1, which is 1. So the dp of 1, 2 equals 1. Now row 2 through 4 shows no new matches, so the values they just carry forward. The important cells are at the position 3, 2. So text 1 character C matches text 2 character C. So then you go diagonal, dp of 2, 1 plus 1 equals 2, and at position 5, 3, text 1 character E matches text 2 character E. So you go diagonal, dp of 4, 2 plus 1 equals 3. The final answer is 3. Now here's a common follow-up question. How do you recover the actual subsequence, not just its length? Now the technique is called traceback. You start at the dp of mn and work backward. At each cell, if the characters at positions I and j match, include that character in the result and move diagonally to dp of I minus 1 and j minus 1. If they do not match, move toward the larger value, either up to dp of I minus 1, 1j, or left to dp of ij minus 1. Following this path gives the characters in reverse order, so reverse the result at the end. Now for our example, the traceback goes from dp of 5, 3, where E matches, included, to dp of 4, 2, then up to dp of 3, 2, C matches, included, then dp, it goes to the dp of 2, 1, and up to dp of 1, 1, where A matches and included, and then to dp of 0, 0. So the reverse result is ACE. Now this you should something note down. So for example, the LCS recurrence has two cases. Match takes the diagonal plus 1, mismatch takes the maximum of left or up. These two case structures appear in the edit distance problem, shortest common subsequence problem, and many other string dynamic programming problems. So you should definitely remember this pattern. Practice with 3 2D dynamic programming practice problems. So we try to define the state and recurrence before really going over the answer. So the first practice problem is, given two strings, we have to find the minimum number of operations, which could be insert, delete, or replace, to transform one into the other. This is the edit distance problem, LeetCode problem number 72. The state is dp of ij, meaning the minimum number of edits to transform the first I characters of string 1 into the first j characters of string 2. If the characters at positions I and j match, no edit is needed. dp of I comma j equals means dp of I minus 1 and j minus 1. If they do not match, you take the minimum of 3 options: dp of I minus 1 j for dp and delete, dp of I j minus 1 for insert, and dp of I minus 1 j minus 1 for replace. You add 1 to whichever is smallest. The base cases are of dp of I 0 equals I, which is deleting all characters, and dp of dp of 0, comma j equals j, inserting all characters. Now let's look at the practice problem number 2, which is given a grid of non-negative numbers. We have to find a path from the top left to the bottom right that minimizes the sum of numbers along the path. This is a minimum path sum, LeetCode problem number 64. It has the same structure as unique paths problem. The only difference is that instead of adding counts, you take the minimum of the cell above and the cell to the left, then add the current cell's value. dp of ij equals grid value at ij plus the minimum of dp of I minus 1, j, and dp of I, j minus 1. Now the practice problem number 3 is, given a string, you have to find the length of the longest palindromic subsequence. This is LeetCode problem 516. So the state is dp of ij, the length of the longest palindromic subsequence in the substring from index I to j. If the characters at positions I and j match, dp of I and j equals dp of I plus 1, j minus 1 plus 2. If they do not match, dp of ij equals the larger dp of I plus 1, j, and dp of ij minus 1. The fill order is different here, so you fill diagonally, processing smaller substrings before larger ones. So these three practice problems represent the three main flavors of 2D dynamic programming, which is string transformation, grid traversal, and substring or subsequence analysis. Now the recurrent structure is similar across all three problems. And this is exactly where sequence DP comes in. So it's a specific sub-pattern of dynamic programming where the state is defined at each position in a sequence and the transition considers all previous positions, not just a fixed set of neighbors. Now the recognition signal is that the problem asks about the longest, shortest, or count to subsequence or subarrays that satisfy a specific property. In grid dynamic programming, each cell depends on a fixed set of neighbors like top and left. In sequence DB, each position may depend on its every previous position. This gives a characteristic of n squared time complexity, an outer loop over each position I, and an inner loop checking all the positions j less than I. Now, the most common sequence dynamic programming problems is the longest increasing subsequence, where dp of I is the length of the longest increasing subsequence ending at index I. The transition, it checks all the previous positions j. If the element at j is smaller than the element I, then dp of I could be dp of j plus 1. You take the maximum across all valid j. Other sequence dp problems include maximum length of pair chain problem, number of longest increasing subsequence problem, and longest divisible subset problem. They all share the same two nested loop structure, just for different conditions on when positions j and I are compatible. Now, recognizing the for each I check all j less than I structure, this immediately tells you that you're looking at a sequence dynamic programming problem and narrows your approach. So longest increasing subsequence, or LIS, is LeetCode problem number 300 and a very commonly asked interview problem. So let us walk through it carefully. Let's say you're given the array 10, 9, 2, 5, 3, 7, 101, 18. The expected answer is 4. One valid LIS is 237, 101. Another one is 257, 101. There can be multiple longest increasing subsequence of the same length. Now the state is dp of I, which represents the length of the longest increasing subsequence that ends at index I. Every element by itself is an increasing subsequence of length 1, so all dp values start at 1. Now the recurrence is this: for each position I, you check every previous position j. If the value at position j is less than the value at position I, that means we can extend the subsequence ending at j by appending the element at I. So dp of I equals the maximum of dp of I and dp of j plus 1. After processing all positions, the answer is the maximum value in the entire dp array because the LIS might end at any position. Now let us trace through it. dp of 0 is 1 for element 10. dp of 1 is 1 for element 9. So because no earlier element is smaller. dp of 2 is 1 for element 2, same reason. dp of 3 for element 5, element 2 at index 2 is smaller. So dp of 3 equals and dp of 2 plus 1 equals 2. dp of 4 for element 3, element 2 at index 2 is smaller. So dp of 4 equals 2. dp of 5 for element 7, elements 2, 5, and 3 are all smaller. giving DP values of 2, 3, and 3 respectively. DP of 5 equals 3 and DP of 6 for element 101. Element 7 at index 5 gives you the DP of 5 plus 1 equals 4. DP of 7 for elements 18, element 7 at index 5 gives you DP of 5 plus 1 equals 4. The maximum in the DP array is 4, so time is O of n squared and space is O of n. This O n squared approach is an expected baseline solution. Most interviewers are satisfied with it unless the constraint specifically requires something faster. There is a faster way to solve LIS using binary search, and it brings the time complexity from O of n squared to O of n log n. The idea is to maintain a list called tails, let's say where tails of I holds the smallest possible tail element of any increasing subsequence of length I plus 1. For each new element, you use binary search to find its position in the tails array. If the element is larger than everything in the tails, you append it, which means we have found a longer subsequence. If it is not, you replace the first element in tails that is greater than or equal to it. This replacement keeps tails as small as possible, preserving the potential for future extensions. Now let us trace through the array here. So it's 10, 9, 2, 5, 3, 7, 101, 18. So we start with an empty tails array. Element 10, tails is empty, we append. Tails is, there's a 10 in there. That's the only element so far in the array. So now element 9, you binary search finds the position 0, replace 10 with 9. Tails is 9. Element 2, you position 0, replace 9 with 2. Tails is 2. Element 5, position 1, pass the end of the single element array, we append. Tails is now 2, 5. Element 3, position 1, we replace 5 with 3. Tails is 2, 3. Element 7, position 2, we append. Tails is 2, 7. Element 101, position 3, we append. Tails is 2, 7, 101. Element 18, position 3, replace 101 with 18. So tails is 2, 7, 18. The length of tails is 4, which is the LIS length. Now, one important detail to remember is that the tails array is not the actual LIS. It is a helper structure that tracks the smallest possible endings. Its length equals LIS length, but its contents may not form a valid subsequence of the original array. The practical advice for interviews is to present the O of n squared DP solution first. It is easier to explain and easier to get right. If the interviewer asks for optimization, or if the constraints have n above, let's say 10,000, then you pivot to the binary search approach. Knowing both shows depth, so the solution actually combines DP thinking with binary search from part 1 of the course, making it one of the very elegant algorithm optimizations that you can demonstrate in an interview. So we have covered 1D dynamic programming, 2D grid dynamic programming, 2D string dynamic programming, and sequence dynamic programming problems so far. The last major DB sub-pattern is Knapsack, and it shows up in disguise more often than people expect. Now the recognition signal is this. You have a set of items, each with a weight or cost and a value. And you need to select items to maximize the value without exceeding a capacity. In the 0-1 knapsack variant, each item can be used at most once. In the unbounded variant, each item can be used unlimited times. Now, the 0-1 knapsack recurrence follows the same include or exclude logic we saw in the house robber problem. At each item I with remaining capacity W, you have two choices. Exclude the item, which is to take the DP of I minus 1 W. Include the item if it fits, that will be taking the item's value plus DP of I minus 1 W minus the item's weight. You take whichever gives you more value. Now the code here, as you can see on the screen, it uses a 2D table of size n plus 1 by capacity plus 1. For each item and each possible capacity, you copy the exclude value, then check if the including the item would be better. Time complexity is O of n times capacity, and space complexity is O of n times capacity. Now here's why knapsack matters beyond the textbook version. Many interview problems are knapsack in disguise. So for example, partition equals subset sum problem asks whether you can split an array into two subsets with equal sums. That is a 0-1 knapsack where the capacity is half the total sum and you're checking feasibility instead of maximizing value. Target sum asks how many ways to assign plus or minus signs to reach a target, which is a counting knapsack problem. Now, then coin change problem is an unbounded knapsack problem where each coin can be used multiple times. And last stone weight 2 problem is a knapsack problem where you're minimizing the remaining weight. Recognizing that a problem is knapsack is, in disguise saves significant time because the recurring template is already known. You just need to map the problem's items, weights, values, and capacity onto the knapsack framework. Now this is the concept that ties everything in this section together. We have seen 1D DP, 2D DP, sequence DP, and knapsack. They all follow the same 5-step process. If you internalize this framework, you can approach any dynamic programming problem systematically, even the ones you have never seen before. So step 1 is define the state. So what does dp of I or dp of ij represent? This is the single most important step. If your state definition is wrong, nothing that follows can be correct. The state should capture all the information needed to make the next decision. Now step 2 is to write the recurrence. How does dp of I depend on smaller states? What are the choices at state I and how do they map to the previous states? This is where you think about what decisions you can make at each state and what decision it leads to. Now step 3 is to identify the base cases. So what are the smallest sub-problems that you can solve without recursion? These are the starting values that bootstrap the entire computation. And step 4 is to determine the fill order. In what order must states be computed so that every dependency is ready before it is needed? For 1D problems, that is almost always left to right. For 2D problems, it is usually top to bottom, left to right. For substring problems like longest palindrome subsequence, it is diagonal. And step 5 is to extract the answer. So where in the table is the final answer? It might be dp of n or dp of mn or the maximum value in the entire dp array, depending on the problem. Now let us apply this to a house robber problem as a concrete example. So for the state, the dp of I equals the maximum money robbing houses 0 through I. Recons would be dp of I equals the larger of dp of I minus 1 and dp of I minus 2 plus nums of I. Base cases would be dp of 0 equals the nums of 0, dp of 1 equals the larger of nums of 0 and nums of 1. Fill order would be left to right from I equals 2 to n minus 1. And the answer would be dp of n minus 1. Now writing these 5 steps on paper before writing any code is a single best practice you can do for DP interviews. It prevents the most common mistake, which is starting to code before this state and recurrence are clearly defined in front of the interviewer. So of those 5 steps, defining the state is by far the hardest. If dp of I is wrong, no amount of clever coding can produce a correct solution. So let us go deeper into how to find the right state. The guiding question is this: what information do I need to make the decision at this step? For climbing stairs problem, you need to know which step you are on. So the state is dp of I equals the number of ways to reach step I. For house robber problem, you need to know which house you are at. So the state is dp of I equals the maximum money through house I. For coin change problem, you need to know how much the amount remains. So the state is dp of I equals the minimum coins for amount I. For LCS, you need to know where you are in both strings. So the state is dp of ij equals the LCS of the first I characters of string 1 and the first j characters of string 2. For knapsack problems, you need to know which item you are considering and how much capacity remains. So the state is dp of iw equals the maximum value using item 0 through the I with capacity w. Now, once you have the state, finding the recurrence becomes a matter of listing the choices. You should be asking something like, okay, what are my choices at this state? For each choice, you write down that what subproblem it leads to, then combine the choices with min, max, sub, or logical OR, depending on what the problem asks for. For base cases, you should ask, okay, what is the smallest subproblem I can solve without any recursion? That is usually dp of 0 for 1D problems, or dp of I0 and dp of 0j for 2D problems. Now there is a common mistake that trips up, even experienced engineers in interviews. So it is defining the state as the answer for the first elements, when it should be actually the answer ending at element I. For LIS, dp of I is the length of the LIS ending at index I, not the LIS of the first I elements. This distinction matters because the longest increasing subsequence might end anywhere, So the final answer is the maximum across all DP values, not DP of n. So when you're stuck on a DP problem in an interview, you should say something like, okay, let me define my state carefully. Then write the DP of I equals on the board with a clear English description of what it means. So this structured approach demonstrates, algorithmic maturity and gives you a solid foundation to build on during the interviews. Now that we have covered all the major DB patterns, let us step back and address the question that should come first in every problem. Is this even a dynamic programming problem? So the decision framework has a clear sequence of questions. First, you should ask, okay, does a locally optimal choice always lead to a global optimum? If you can prove that, then greedy approach is correct and simpler. Do not use dynamic programming when greedy approach works. It overcomplicates the solution and will waste your time in the interview. Second, you should ask that, okay, are there any overlapping subproblems? It is the same state can be reached, through multiple decision paths, then DP caches results and avoid the recomputation, so then it's ideal. Third is to ask, okay, does the problem need all valid solutions or not just the count or the optimal one? If yes, then you must explore all the branches, which means backtracking. And also consider the input size. If n is at most 15 to 20, exponential time is acceptable, so backtracking or even bitmask DP works. If n is in the range of 1000 to 10,000, O of n squared or O of n times capacity, DP is feasible. So now the three approaches are deeply related. So for example, backtracking explores the full decision tree, and DP explores the same tree but caches results, so each unique state is computed only once. Greedy walks a single path through the tree, choosing the locally best branch at each node without ever looking back. And then DP is always at least as good as backtracking in terms of correctness and usually much better in time complexity. Greedy is faster than DP, but it's only correct when the greedy choice property holds. Now in the production systems, you will often see that, okay, the same kind of decision framework applies. You do not reach for the most complex tool first. You check whether the simpler approach works and only escalate when it does not. Being able to articulate why you choose DP over greedy or vice versa in the first few minutes of the problem is very important during interviews. It demonstrates the algorithmic maturity and saves you from going down the wrong path, which might lead to not clearing the interview. So that is not good. So yeah, please keep this in mind. This is one of the most common DB follow-up questions in the interviews, and having the technique ready will earn consistent bonus points, so you should keep this in mind. So the general principle is pretty straightforward. If DP of I only depends on DP of I minus 1 and possibly DP of I minus 2, you do not need the entire table. You keep only the rows or variables you actually need. For 1D DP problems like climbing stairs or house robber problem, the full array has O of n space. But since each state only depends on the previous two values, you can replace the entire array with two variables, previous 2 and previous 1. At each step, you compute the current value from those two and then shift them forward. The space complexity drops from O of n to O of 1. Then for 2D DB problems like unique paths, the full table has O of m times n space. But since each row only depends on the previous row, a single 1D array of size n is enough. When updating DB of j, the value it currently holds is from the same previous row, acting as the DP of I minus 1, j, and DP of j minus 1 has already been updated for the current row, which acts as the DP of ij minus 1. In that case, space complexity drops from O of m times n to O of n. Now, there is one case where space optimization requires extra care. So if DP of ij depends on DP of I minus 1, j minus 1, which is a diagonal, you need to save that diagonal value before it gets overridden by the current row's computation. This is still doable with one extra variable, but you need to be careful about the order of operations. And here's something important for interviews as well. Always present the unoptimized version first. The interviewer needs to understand your logic clearly, and the full table makes that easier. Then offer the space optimizations, so you can say something like, okay, this uses O of m times n space, but since each row only depends on the previous row, I can reduce it to O of n. Presenting both versions in the interview with the optimization offered proactively, is exactly what the interviewers would like to see. Dynamic programming has the highest failure rate of any interview topic. The mistakes we are about to cover account for the majority of those failures. Eliminating them gives you a significant edge. So the first mistake is starting with the table before defining the state. If you jump straight to thinking about table dimensions and fill order without first writing down what dp of I means in the plain language, the entire solution can be built on a shaky foundation. You should always write something like, okay, dp of I equals, so with a clear English description before touching any code on the whiteboard. The second mistake is getting the recurrence wrong by missing a case. If there are 3 choices at each state and you only account for the 2, the solution produces incorrect results for any input that triggers the missing case. The fix is to explicitly list all choices at each state and make sure every choice maps to a transition in the recurrence. The third mistake is wrong base cases. If dp of 0 or dp of 1 has an incorrect value, that error propagates through the entire table. The fix is to identify the smallest subproblems and manually verify them with a concrete example. The fourth mistake is off by 1 errors in table dimensions. Accessing dp of -1 or dp of n plus 1 or missing the last state entirely, the fix is to use consistent conventions. N plus 1 size for the amount of base dp and n size for index bit dp. The fifth mistake is using dp when greedy approach works. So this overcomplicates the solution and wastes precious interview time. Spend 30 seconds before checking whether a greedy approach is sufficient before you actually come into the dynamic programming approach. Now, when you're stuck, let's say on a DP problem, you should follow this sequence. First, you should draw the decision tree for a small example. Second, you should identify repeated subproblems in the tree. Third, you define the state as the information that makes each subproblem unique. Fourth, you write the recurrence from the tree structure. Fifth, you identify the base cases from the leaves of the tree. So this process works on any DB problem, including ones you have never encountered before. Here's a reference card for this entire section. This slide is designed to be screenshotted and essentially used for quick revision before the interviews. Let me walk you through the key templates. For 1D DP, you create an array of size n plus 1, set the base case at dp of 0, and fill left to right using the recurrence. This covers climbing stairs problem, house robber problem, coin change problem, and similar problems. For 2D grid DP, you create a 2D array with rows and columns, fill the base row and column, then fill top to bottom, left to right. Each cell depends on the cell above and the cell to the left. This covers unique paths and minimum path sum. For 2D string DP, you create a 2D array of size m plus 1 by n plus 1. For each pair of positions, if the characters match, you go diagonal plus 1. If they do not match, you take the larger of up or left. This covers problems like LCS and edit distance problem. For sequence DP pattern, initialize all the DP values to 1. For each position I, you check all the previous positions j. If the condition between j and I holds, you update the DP of I. This covers LIS and similar problems. For 0 to 1 knapsack, you trade over items and capacities. For each item, you either exclude it, which is to carry forward the previous row, or you include it, which means adding the item's value to the best for the remaining capacity. And then you take the maximum. For memoization, you check if the state is cached, return if so, compute and cache, if it's not. This template works for the top-down version of any of these patterns. Now the key complexities to remember are 1D DP runs in O of n time and can be optimized to O of 1 space. Coin change runs in O of amount times coins time with O of amount space. Grid DP runs in O of m times n time complexity with O of n optimized space. LCS and edit distance problems are also O of m times n with O of n optimized space. LIS is O of n squared with the DP approach and O of n log n with the binary search. Knapsack is O of n times capacity with O of capacity optimized space. Now if your DP solution has exponential time complexity, either you miss the DP structure in the problem or the problem actually requires backtracking. You should check the constraints to decide which. Now let us bring everything together. In this section we covered 8 distinct DP concepts and patterns. So memoization is a technique of caching recursive results in a dictionary. You use it when a recursive solution has repeated subproblems. Tabulation replaces the recursion with an iterative table fill, eliminating recursion overhead. 1D DB problems, they handle problems like where the state is described by one variable, either an index or an amount. The dependencies are on dp of I minus 1, dp of I minus 2, and all of dp of j for j less than I. 2D grid DP handles path or cost through a grid where each cell depends on the cell above and the cell to the left. 2D string DP handles comparing or transforming two sequences, so the key decision at each cell is whether the characters match, which is to go diagonal, or mismatch, which is to choose between left and up. Sequence DP handles longest or shortest subsequence with a property using the characteristics, for example, for each I, check all j less than I structure. Knapsack handles selection problems with a capacity constraint using the include or exclude decision at each item. And space optimization, it replaces full tables with one or two rows or variables when the current state depends only on the immediately previous state. So these patterns connect directly to the earlier sections. DP is backtracking with memory from section 4. Coin change problem shows where greedy approach fails from section 3. Grid DP relates to BFS on grids from section 2 but counts for optimized paths instead of finding the shortest one. The binary search in the LIS optimization comes from part 1 of the course, and the include or exclude recurrence mirrors the subset generation approach from section 4, but this time with caching. Now in section 6, we'll present the final pattern recognition cheat sheet. It consolidates all the sections from both parts of the course into a single decision framework, which is to given an unfamiliar problem, how do you classify it, how do you choose the right pattern, and how do you apply the right template in the first 60 seconds of an interview. Now dynamic programming problems, they account for roughly 15 to 20% of LeetCode interviews, and they are considered generally a very hard problem to be given an interview. But with the 5-step framework that we have just covered, and the 6 DP sub-patterns, and the space optimization techniques in this section that we have described and covered, you now have a systematic approach that works on both familiar and unfamiliar problems. Combined with everything from previous sections, you should have now tools to cover majority of the LeetCode problems. So now let's wrap up this course with covering the final section in which we bring everything together. For the previous 5 sections of this course, we have covered every major pattern that appears in LeetCode interviews and DSA interviews at this level. Tree traversal with DFS and BFS, graph search with connected components and topological ordering, heaps for top key extraction, interval merging and scheduling, greedy algorithms with provable optimality, backtracking for exhaustive search, and dynamic programming for optimization with overlapping subproblems. So we have covered these sections, which covers a family of patterns in depth. However, in real interviews, the problem essentially does not come with where the patterns are more obvious. So, for example, they won't be saying that, okay, you should use a topological sort, or this is a knapsack DP problem. The problem actually just arrives as a paragraph of text, and the very first thing you need to do is to classify it. That classification step, getting it right within the first 60 seconds, is often what will make you succeed in interviews. So now the final section is about putting everything together. So we'll build a decision tree that covers every pattern in this course and lets you classify problems quickly. We'll map the specific single phrases that appear in the problem statements to the patterns they point to. We'll consolidate time and space complexity for every pattern into a single reference. We'll work through the 3 rounds of mixed pattern practice problems where you will not know which pattern applies until you have analyzed the problem yourself. And we'll look at at how these problems combine when a single pattern is not enough, the most common mistake across all sections, and then close with cheat sheets for every section with a clear roadmap on what to practice next. So let us build a mental framework for classifying any problem you encounter. This is a decision tree you run in your head every time you see an unfamiliar problem. With practice, it takes under 30 seconds. The first question to ask is, okay, is this input a tree? If it is, the follow-up questions narrow it down quickly. If you need to process nodes level by level, that is BFS with level size trick. If you need to compute something from subtrees like height, diameter, or whether a subtree is balanced, that is DFS with a post-order traversal where you return values upward. If the tree is a binary search tree, you should exploit the sorted in order property, which lets you validate ranges or find the kth smallest element efficiently. If the problem involves a path from root to leaf, you pass the value downward through the recursion parameters. And if the problem asks you for the lowest common ancestor, that is the LCA pattern where you search both subtrees and combine the results. Now, if the input is not a tree, the next question is it a graph or a grid? So for shortest path in an unweighted graph, you should use BFS. For connected components or counting regions problems, you should use DFS or BFS. If something spreads from multiple sources simultaneously, like rotting oranges problem, spreading to orange fresh ones, that is a multi-source BFS where you initialize the queue with all sources at once. If the problem mentions dependencies or prerequisites, that signals topological sort with Kahn's algorithm. If you need to dynamically group or merge elements based on connectivity, that is union find. And if you need to detect cycles in a directed graph, the three-color DFS approach distinguishes between nodes that are unvisited, currently being processed, and fully processed. Now, what if it's not a tree or a graph problem? Then you should ask, okay, does it need top k elements or repeated extraction of minimums or maximums? If the answer is yes, that is a heap. If you need to merge k sorted sequences into one, that is the k-way merge pattern using a heap. And the next question is the problem about overlapping time ranges? If you need to merge overlapping intervals, sort by start time, and merge as you go, if you need to, need the maximum number of concurrent events or the minimum number of rooms, use the, event splitting technique where each interval becomes a start event and an end event. If we need to, for example, remove the minimum number of intervals to eliminate all the overlaps, you sort by end time and apply the greedy selection. And then you should ask, for example, okay, does the problem ask for all combinations, all permutations, or all subsets? If it asks for all subsets, that is backtracking, where you record the path at every node of the decision tree. If it asks for all permutations, that is backtracking with a used array to track which elements have been placed. If it asks for combinations that sum to a target, that is backtracking with pruning to cut branches early. If it asks you to find a word or path in a grid, that is grid backtracking with the choose, explore, and choose framework. And finally, does the problem ask for a count, a minimum, or a maximum, or does it have overlapping subproblems? If the state is a single variable like an index or an amount, that is 1 DDP. If the state is a position in a grid, that is 2 grid DP. If the state involves 2 positions in 2 strings, that is 2D string DP. And the pattern is, for example, let's say, for each index I, you have to check all indices j less than I, that is sequence DP. Now, if the problem involves including or excluding items under a capacity constraint, that is a knapsack DB. But before committing to DP, spend a moment checking whether a local greedy choice can be proven optimal. If it can be, grading approach is more simpler and more efficient. Now, this decision tree is not a rigid script to follow mechanically. It is a mental checklist. The goal is to make pattern recognition automatic so that by the time you finish reading the problem for the second time, you already have a strong hypothesis about which approach to use. And the practical benefit is enormous. Picking the wrong pattern and spending 15 minutes before realizing you need to restart is one of the most common mistakes in interviews. If you spend, first few minutes on classification using this framework at the start, it will prevent that mistake entirely and you will, do better interviews as well. The decision tree classifies problems based on the type of input and what the problem asks for. But there is an even faster shortcut, specific phrases in the problem statements that map directly to patterns. Think of these as trigger words that should immediately activate a pattern in your mind. Let me walk you through section by section now. For tree problems, when you see keywords in the problem statement like height, depth, or diameter, that signals DFS, returning values upward. The key insight is always the same. You compute the answer on both subtrees, combine them at the current node, and return the result upward. When you see keywords in problem statement like, let's say, level order, right side view, or zigzag, that signals BFS with level size trick, where you process all the nodes at the current level before moving to the next. When you see keywords like validate BST or k at smallest in BST, that signals range-based DFS or in-order traversal, exploiting the sorted property of binary search tree. And when you see keywords like lowest common ancestor, it signals the LCA pattern where you search both subtrees and return the current node when both sides find a target. Now for graph problems, when you see keywords like number of islands or connected regions, that signals DFS or BFS on a grid. When you see keywords like rotting oranges or any problem where something spreads from multiple sources simultaneously, that signals multi-source BFS. When you see keywords like course prerequisites or task dependencies, that signals topological sort using Kahn's algorithm. And when you see keywords like merge accounts or group by connectivity, that signals union find. Now for heap problems, when you see keywords like top k or kth largest signals, they signal a min heap of size k. When you see keywords like merge k sorted list, that signals a k-way merge pattern with a heap. For interval problems, such keywords like overlapping intervals or meeting rooms signal sorting intervals and sweeping through them. And keywords like removing minimum to eliminate conflicts, they signals sorting by end time and applying a greedy selection. Now keywords like all subsets, all permutations, or all combinations, they all signal backtracking. And phrases like finding a word in a grid signals grid backtracking. For dynamic programming, you should be looking for keywords like minimum coins or number of ways. They signal a DP formulation. Phrases like common lowest, longest common subsequence, they signal 2D string DP. And again, for example, the phrase like longest increasing subsequence signals, sequence DP, and keywords like knapsack or partitioning into equal subsets, they signals knapsack DP. The reasoning this mapping is so valuable that in a real interview, you do not see a problem tagged with a pattern name. You do see a paragraph or essentially, English text, and your ability to extract these single phrases and keywords and immediately connect them to the right pattern is what gives you speed in the first 2 minutes. And every minute you save on classification in a minute, is a minute you can spend on implementation and testing. Now, once you identify the right pattern, you need to know two things: what complexity it gives you and whether that complexity is fast enough for the given input size. Let me walk you through every pattern in this course. So tree DFS in any traversal order visits every node exactly once, so it runs in O of n time. The space is O of h for the recursion stack, where h is the height of the tree. For a balanced tree, h is O of log n. For a skewed tree, h is O of n. Tree BFS is also O of n time, and with O of w space for the queue, where w is the maximum width of any level. BST search runs in O of h time because you follow one path from the root to the target, eliminating half the tree at each step in a balanced tree. Now graph BFS and DFS, they run in O of v plus e time, where v is the number of vertices and e is the number of edges. The space is complexity is O of v for the vested set, and the queue or the recursion stack. Topological sort with the Kahn's algorithm has the same O of complexity of O of v plus e for time complexity with O of v plus e space to store the adjacent list and the indexes. Now union find with path compression and union by rank is effectively O of n because the inverse Ackermann function grows so slowly it is practically constant per option. Now grid traversal visits every cell once, so it is O of row times calls for both time and space. For heaps, the top k pattern runs in O of n log k, time complexity, and O of k space. This is better than the sorting when k is much smaller than n. So k-way merge, it runs in O of n log k time, where n is the total number of elements across all lists, and the space is O of k for the heap. The merge intervals, it runs in O of n log n time because the sorting step dominates, where O of n space for the output. Backtracking is where complexity jumps significantly, so generating all subset is O of n times 2 to the n, generating all permutations O of n times n factorial, and these are the exponential, which is expected because the output itself is exponential in size. For dynamic programming, 1D DP is typically O of n time and can be optimized to O of 1 space, where only the previous one or two states are needed. 2D DP over a grid or two strings is O of m times n time and can be optimized to O of n space by processing one row at a time. Sequence DP, like the longest increasing subsequence, is O of n squared with the standard approach. Knapsack DP is O of n times capacity and can be optimized to O of capacity space. Now the practical application. The input constraints tell you which complexity class your solution needs to be in. If n is at most 20, even O of 2 to the power n or O of n factorial approaches are viable. So backtracking is back on the table. If n is at most 1000, O of n squared is fine, which means sequence DP and knapsack are both viable. If n is at most 100,000, you need O of n log n or better, so sort-based approaches, heaps, and greedy will work. If n is at most 1 million, you need O of n, which means DFS, BFS, or hash map based solutions. Now, checking the constraints before committing to an approach saves you from proposing a solution that cannot possibly run in time. If n can be 100,000 and your solution is O of n squared, that is 10 billion operations, and that is not ideal for interviews. Now, knowing the patterns and knowing the complexities is necessary, but you also need a repeatable process for the first 5 minutes of every interview problem. Now, these 5 minutes, set the trajectory for the entire interview. In the first minute, you should read the problem completely and ask clarifying questions. You read the entire problem statement before you start thinking about solutions. Then you ask, okay, what are the constraints on n? Can there be duplicates? Can values be negative? What should I return for edge cases like empty input or a single node? These questions give you information that narrows down the right approach, and they show the interviewer that you think carefully before acting. In minute 2, you identify the pattern. This is where the decision tree and signal table come in. What data structure is the input in? Is it a tree, a graph, a grid, or an array? What does the problem ask for? A count, a minimum, a maximum, or all valid solutions? And what signal phrases appear in the problem statement? Running through these questions should point you to 1 or 2 possible candidate patterns. Then in minute 3, you state the brute force approach and its time and space complexity. Even if you see the optimal solution immediately, always mention the brute force approach first. For example, you can say things like, okay, the brute force tries all subsets, which is O of 2 to the power n, but I notice overlapping subproblems, so I can use DP to reduce this to O of n times capacity. When you say that in the interview, this shows the interviewer that, okay, you understand the problem and gives you a baseline to optimize against. Now in minute 4, you apply the pattern and state the optimization. You explain the key insight that enables the optimization, state the new time and space complexity explicitly. And in minute 5, you plan before coding. Outline your approach in 2 to 3 sentences. If it is a dynamic programming, state the reconciliation and the base cases. If it is backtracking, describe the decision tree and what are the choices are each level. If it is a graph problem, describe the traversal strategy and what you are tracking in the visited set. Only after this plan is clear should you write the starting code. And here's what some things to not do in the interviews. Do not start coding immediately. Jumping into code without a plan leads to confused implementations that will waste your time. Do not also jump to the optimal solution without mentioning the brute force. Interviewers, they want to see your reasoning process, so make sure you start with the brute force and then you move to the optimal solution. And do not stay silent while thinking. If you are considering whether this problem has overlapping subproblems, you should be saying out loud your thinking thought process. Narrating your thought process is how you earn credit for your problem-solving ability, even if you do not reach the perfect solution in the given time frame.